Hi, everybody. I think we are live now. Welcome to this 2021 edition of the OCaml workshop. I'm glad to see so many people already. Thank you very much. This year, we were pleased to receive many presentations, so that makes a long program. It will be a long day. This workshop will also be streamed on YouTube. I will share the link as soon as possible, probably share it on Discuss too, so you will be able to invite your friend who were not able to register. And without further delay, I will let Yu chair the first session. So thank you very much, Yu, for accepting.
Okay. Hi, everyone. Welcome to the first session of the OCaml workshop. So in this session, we will have 3 talks, and all the talks are pre-recorded, and you are welcome to send your question during the talks by opening the QA tab. Okay, and our first speaker is Kiran. He will be telling us about a structural editor for OCaml. So please start.
Structural editor for OCaml. Now, before we begin, let me ask you a little question. Have you ever struggled with your editor to express complex transformations of OCaml source code in terms of simple, low-level lexical operations? Have you ever sought to search through a large and complex OCaml codebase using fairly dumb, regular expressions to struggle to find your way around? Well, if you answered yes to any of those questions, then OCaml is the plugin for you. The structural editing capabilities provided by OCaml will literally allow you to edit at the speed of thought itself. But fair warning before we proceed, the structural editing capabilities provided by OCaml may change the way you write code forever, and it is addicting. So be prepared for the consequences. Okay, with the elevator pitch aside, let's get down to business and see how exactly this thing works. Okay, so let's say that you're writing a function in OCaml, as one is oft to do. Now, over the course of the implementation, for any one of a number of reasons, you may find yourself in a situation where you need to change the definition of the function that you're writing. For example, maybe you want to add another argument, maybe the name of the function is no longer accurate, maybe you want to explicitly annotate the types of the arguments, or as the case here, maybe you want to make the function recursive. The key point that I'm trying to make here is that this is a fairly common operation that is somewhat non-trivial, so it would be nice to have some kind of editor support for this operation. But how exactly should we provide editor support for this operation? Well, we can take some inspiration from Emacs. It turns out that Emacs actually already has a binding for this operation. In particular, pressing Ctrl-Meta-A runs the function beginning of define. And so when you're editing Emacs Lisp code, this will move your cursor from its current position to the start of the nearest enclosing function definition. So, turns out the editor is already configured. The only problem is that this is only defined for Emacs Lisp. So we need to provide a definition for OCaml. But how exactly should we implement this? Well, as a first attempt, we might say that every let binding begins with a let. So can't we just search backwards for the first preceding let? Well, this kind of works, but what about let expressions? That kind of throws a wrench in things. But wait, it gets even worse. What about local modules? Because these modules could have let bindings within them. The key point that I'm trying to make here is that it's not quite as simple as it might seem. And this is fundamentally because OCaml doesn't really have any kind of required lexical tokens needed to denote the start and end of expressions. And so it makes it very hard to determine these kind of structural operations using the kinds of lexical operations that an editor framework might provide. And actually, if we zoom out a bit, it turns out that we're actually brushing up against a sort of fundamental dichotomy in the design space of programming languages. So now, if I were to plot out the programming languages on this little graph here, where on the x-axis, as we move to the right, we reduce the level of syntactic redundancy in our language. Then we can plot languages like Lisp on the far left, because they have very high amounts of syntactic redundancy. In particular, every expression is denoted by an opening and closing parentheses. Conversely, we can plot ML family languages on the far right, because they have very little syntactic redundancy, as we thought about earlier. And in the middle, we can place languages that are C or C-like or like Rescript. Now, it turns out that this notion of syntactic redundancy is a sort of double-edged sword, because by having a lot of syntactic redundancy, languages like Lisp can easily provide robust editor support, because it's very easy to work out where expressions should be. But the problem with this is that it makes programs written in the language very noisy. It's very hard to parse Lisp program as a human, unless you're used to dealing with these kind of parentheses. Conversely, with ML family languages, by their virtue of very little syntactic redundancy, they have a very clean and concise syntax that makes them a pleasure to read and write. But this comes at the cost of having very ad hoc editor support. So this is kind of the fundamental dichotomy that we're brushing up here. But is it possible to do better? Is it possible to get the best of both worlds? Well, what if we were to track the syntax tree from the editor? This way we could bypass this dichotomy and get a very syntactically clean language while also getting very high quality editor support. And this is exactly the insight that inspired OCaml mode. So, to summarize, OCaml is an editor-agnostic generic framework for structural editing of OCaml code. Now, to do this, it leverages the OCaml compiler pipeline for faithful parsing of OCaml code. And then on top of this, it provides functionalities to track and maintain the concrete syntax tree for an edited file. And on top of this, defines common editing operations as AST transformations, thereby allowing for a fundamentally different way of editing OCaml code. Now, OCaml mode is a particular Emacs plugin that uses the OCaml framework to provide robust and consistent editing support for OCaml code in Emacs. And the beauty of this implementation is that it seamlessly integrates with existing Emacs workflows. When you need the structural editing capabilities of OCaml mode, the functionalities are merely a keybind away. And when you don't, the plugin simply fades into the background, and you wouldn't even know that you had it installed. So hopefully that's piqued your interest, and in the rest of this talk, I'll give you an overview of this work. So we're going to start off by going through a little tour of the various features of OCaml, and then we'll do a little bit of live coding to see how it all fits together. And then we'll talk about how exactly it works and the implementation of the framework itself. And finally, I'll talk a little bit about the future work and where I hope to take it from here onwards. So, without further ado, let's get started. Perfect. So let's begin with a quick whistle-stop tour of the key functionalities provided by OCaml. In particular, the 5 functionalities that you can see on screen. Move to definition, structural navigation, structural transposition, structural deletion, and extract expression. Now, there are a couple of other quality of life functionalities that OCaml mode also provides, but for the purposes of this video, we won't be covering them. So the first functionality we'll be looking at, as hinted by the introduction, will be the move to definition operation. So the idea here is that when the user presses the key binding control meta A, the editor moves the cursor from its current position to the start of the nearest enclosing function definition, as you can see on screen. Now, because this functionality is so robust, it works perfectly fine, even when you're dealing with really large expressions with several let bindings in between them, and even when you're dealing with local modules that may have bindings within them themselves. Now, while we're starting off with a fairly simple functionality, this turns out to be particularly useful, especially when you're dealing with really large function definitions that don't even fit on screen. In this case, trying to do a manual approach would likely be very disorientating, so this is actually pretty nice. Now, the next functionality is structural navigation, which allows a user to navigate through code in terms of the syntax tree. And this is where it starts getting interesting. So as I mentioned before, OCaml has very little syntactic redundancy. So there aren't clear lexical markers to denote syntactic constructs. So how do we convey to the user their position in the syntax tree? Well, to do this, we introduce an entirely new modality. When the user presses a key binding for structural navigation, as shown on screen, the user enters the zipper mode. We'll look into the reason why it's called that in a bit. And in this mode, the editor tracks the structural position of the user and highlights it as a small overlay, as you can see on screen. So with these key bindings, the user can freely navigate through the AST. And it turns out to be very useful, especially when you're dealing with very large match statements where one branch may span several pages. So very nice again. And now that we have this zipper-based interaction scheme, it turns out that we can actually tack on several other useful functionalities on top. And structural transposition, the next functionality, is one such addition. So the idea here is that whenever you run one of the structural navigation key bindings and add a shift to it, it becomes a structural transposition or structural movement operation. And rather than just moving the cursor, the editor moves the entire selected syntactic construct through the syntax tree, as you can see on screen. So as it turns out, one useful place where this is particularly nice is when editing module signatures, where it's actually very useful to be able to just freely move around various declarations without having to worry about very syntactic issues. And a nicety is that it also carries around the comments as well, so pretty good. The next extension that branches off zipper mode is structural deletion. So the idea here is that when the user presses the key binding to delete either Control Meta D or Control Meta W, the editor removes the selected syntactic construct from the syntax tree. And this makes it very easy to refactor codebases. Again, another place where this turns out to be useful is in editing module signatures, where you can freely remove various declarations by just pressing one key binding. And the final functionality that we're going to be looking at is extract expression. Now, this isn't strictly based on zipper mode per se, but more to highlight the kind of additional functionalities that you can support if your editor has a deeper understanding of the syntax. So when the user presses the key binding Control-C, Control-E, the editor attempts to extract every instance of the selected expression into the nearest enclosing let binding. So unlike tools like Rotor, this isn't guaranteed to be sound and may entirely change the semantics of the program, especially if you're dealing with references, etc. Now, it is partially aware of scope and will try and extract the expression to the nearest enclosing scope that contains all the variables in the selected expression, but it can't really make any guarantees. And this is perfectly fine because it's not intended to be a large-scale refactoring tool, but rather a lightweight, quick operation that a user can use in anger while editing. So that kind of covers the main kinds of functionalities that I want to cover in this video. But so far, I've only shown you these different features in isolation. To get the full experience of OCaml, we'll need to see how these functionalities all happen to interact during actual coding. So talk is cheap, let's do some live coding. So, as they say, the proof is in the pudding. So today we're going to do a little bit of live coding for you. We're going to be writing a simple evaluator for a small term-based language. And this language is adapted from types and programming languages. So as you can see, it's fairly standard. We have constructors for true, false, if statements, zero, suck, and is zero. Pretty basic. Let's write an evaluation function for this thing. So we'll start with let eval t equals t. Now I'd like to destruct on this t term, but unfortunately because it's an abstract type, Merlin doesn't allow me to do that. So we can press Control-C, Control-P to take us to the nearest parameter, and then we can explicitly annotate the type as being term. And then if we move back, Merlin will allow us to do the destruct again. Now once we've destructed, we can have a look at the cases here. And we can see that actually when we're implementing an evaluator, there are only two particular cases that we care about. That is tm if and tm is 0. Now moving these all to the top, we can then delete the rest. and just replace them with a raise no rule applies exception. Okay, now moving back to the remaining cases, what we can do is we want to duplicate a couple of these. So the if statement should be duplicated at least 3 times, and the 0 statement should be duplicated twice. So let's implement the TMF. The reason for the duplication is that if we're dealing with a TMIF of a TM true term, then we can simply evaluate this by returning the if branch. And if we're dealing with a TM false, and the conditional is false, then we can just simply return the else branch. So that's pretty simple. Now let's move on to implement the full case, where we need to evaluate the condition. So we can name each one of the parameters, and let's start evaluating the conditional first. But wait a minute. In order to evaluate this, we need to make the function recursive, but we haven't made it recursive. Now we can use moveToDefinition to quickly jump to the definition, add a recursive annotation, and jump straight back. And now we can call eval without any problems. Let's eval the remaining terms, so eval t2 and eval t3. And once we've done this, we just need to return the exact term that we started off with. Just to simplify things, I'm going to just copy the thing that we matched on and paste that exactly as the return statement. Now let's handle the 0 is 0 cases. So where tm is 0 of it is 0, then we just return tm true. And if we're dealing with a tm is 0 of an unevaluated term, then we just need to eval it as we did before, and then return tm is 0 of this newly evaluated term. So pretty simple, pretty straightforward, pretty cool. Alright, so now that we've had a chance to see OCaml mode in action, now let's take a look under the hood to find out how exactly it's implemented. So, how exactly is it implemented? Well, I told you earlier that it's implemented by tracking the concrete syntax tree for the currently edited file. But it turns out it's not quite that simple. And this is because of one small problem. And to understand what that problem is, let's take a look at the OCaml syntax tree. So I've thrown on screen a snippet from the definition of the OCaml syntax tree, the part that defines an expression. And as we can see, it's fairly standard. One can easily imagine how you can instantiate this data type to construct various trees to represent the types of programs that users might throw at you. But there's one small problem with this definition, and that is that this definition is inherently static. It's not suited for an interactive traversal, the kind of traversal that we would have to do if we're trying to implement structural transformations. So how do we solve this problem? Well, it turns out that this problem, that of performing an interactive traversal of a data structure like a tree, is a fairly standard operation. And it turns out it has a fairly standard solution. That is, a zipper. So the zipper data type, originally conceived by Hewitt, is a functional data type that represents an iterator over a data structure like a tree. Now, in our case, we've made a few small modifications to make a zipper that's tailored for editing. Now, to understand what this definition means, you have to understand that a zipper represents a path through a tree. And so at every instance, the zipper will be focused on one particular element of the tree. Now, with this context in mind, we can understand each one of the fields as follows. The parent field represents the immediate parent of the currently focused element. The sibling fields, the above and below, represent these siblings that are immediately preceding the current element, or the ones that precede. In this case, there are none. Now, the main modification that we've made is to add this additional field, bounds, that represents the text region that encompasses the entirety of the currently selected element and all of its children. And this turns out to be really useful for editing because it means that we don't need to understand the contents of a node in order to perform transformations on it. We can simply tell the editor to move or remove the text region that corresponds to the entirety of the selected syntactic construct. Now, the zipper also has this constructor top that represents a path to the root of the entire syntax tree. And we also represent the currently selected item using this item field. Now, this item field has a type of T, but this T is not just an alias for the OCaml syntax tree. It's actually a fancy wrapper. And this allows us to implement this kind of lazy zipper for editing. The idea here is that rather than converting the entire OCaml syntax tree into our zipper format, we gradually convert the syntax tree by wrapping it initially in this data type. And then as the user moves through the tree, we convert these instances into this generic data type that loses all the additional extraneous information and only tracks the bare minimum structural information needed to perform these kinds of operations. So hopefully that gives you an idea of how this is implemented. But how exactly do we use this zipper to implement structural transformations? Well, to get an understanding of the intuition behind how this works, let's take a look at a few of the structural transformations that we've seen previously. Let's start with structural navigation. Now, as it just so happens, this concept of a focus node in the zipper maps one-to-one with this notion of a focused syntactic construct in our so-called zipper mode. And so in order to implement transformations, in order to implement movements, we can simply update the zipper. So for example, in order to move up, we would select the parent using the parent field and then update the zipper accordingly. In order to descend into a node, we would need to break into it and convert it into a generic format, select the first child, and then update the zipper to point to the first child. Similarly, if we wanted to move to any of the siblings, we could select the above or below fields and update the zipper accordingly. So fairly concise and an elegant implementation of this operation. Now, the second operation is structural transposition, and this is slightly more complex, although still fairly simple. In order to implement transposition, we first have the zipper that's focused on one particular element. Then we work out the element that we're going to be swapping it with by looking at either the sibling above or below fields. And once we've found this other element, we can then implement the transposition by extracting the text regions that correspond to both of these selected elements, and then asking the editor to implement this swap of these two text regions. And once that's done, we can update the zipper and update the corresponding text regions, and the zipper is now up to date. So once again, fairly concise. The final operation that we're going to look at is structural deletion. Now, deletion is slightly more complex, although still fairly nice. Now, the way we implement deletion is the zipper will be focused on a particular element. Now, when we want to delete it, we need to work out where the zipper should move to. So we select either the parent or the sibling. In this case, there's a sibling, and update the zipper accordingly. Next, we just simply remove the deleted element from the syntax tree and ask the editor to remove the text region corresponding to that deleted element. But we're not quite done yet, and that is because the text region has been removed. This means that all text regions for the ancestors of the current node are now invalidated. So we need to ask all ancestors to update their text regions to account for this removal. And then we also need to ask every sibling of the ancestor to adjust their text regions to be shifted backwards according to this deleted region. And once we've done that, the deletion has now been implemented. So hopefully that should give you an intuition as to how we implement structural operations using a zipper. But there's one part of this implementation that I've been particularly vague about. And that is, how do we integrate this with an editor? Well, to understand this, let's take a look at the system architecture for the overall tool. Now, currently we've only had support for Emacs, but it turns out, as we'll see, this is not a large limitation. So our architecture begins with this instance of the Emacs editor, which has a buffer that contains the code that the user is editing. Now, on top of this, we provide a package, OCaml mode, that is actually written in OCaml using JaneSpeed's eCaml library to allow us to dynamically bind to the Emacs instance. Now, with this package set up, in order to build the AST, we then, because we're writing in OCaml, we can just reuse the OCaml parser to get 100% faithful parsing of the user's code. And once we've done this, we can then convert the AST into the zipper using the operations that we've seen previously. And with this, the package is set up. Now, whenever the user submits any kind of transformation or structural operation, we work out how to implement that operation in terms of the zipper. And once we work that out, we then tell the editor to enact that change in terms of fairly simple text operations. And this means that the editor is actually 100% unaware of the complexity of dealing with OCaml syntax. And a nice consequence of this is that it means actually the architecture is fairly generic over the choice of editor. And so in theory, in the future, we could actually modify it to support other architectures. So that kind of wraps up everything that I wanted to speak about today. Just to summarize the main points, OCaml is an editor-agnostic generic framework for structural editing, and to implement this, we leverage the OCaml compiler pipeline for faithful parsing and use a mix of zippers and ASTs to implement these kinds of structural transformations. OCaml mode happens to be a particular Emacs plugin that uses the OCaml framework to provide robust and consistent OCaml support for Emacs. Now, in the remaining few minutes of this presentation, I just want to take a second to talk about potential directions that I hope to extend this project in the near future. Now, the first such direction is, as I mentioned, support for other editors. Another direction that would be nice is to have robustness to invalid syntax. Currently, the buffer has to be syntactically valid in order for the structural operations to work. but it would be nice to have support for invalid syntax, a la Merlin. Ideally, I'd like to reuse the Merlin compiler, but unfortunately, it's not really exposed in a way that is easy to reuse. Another direction would be to have additional semantic-aware transformations. Currently, we only do very basic structural syntactic analysis for our extract expression, but seeing as we're tracking the entire AST, it seems like there's lots of potential for doing some more semantically aware transformations. For example, maybe an extract expression that is in fact sound and guaranteed not to change the behavior, a la rotor. And a final direction that would be nice is support for meta-OCaml programs. Currently, the syntax of meta-OCaml isn't supported by the current parsers that we support, and so we can't really do structural editing of meta-OCaml programs. So that's about everything that I had to say. Hopefully I've managed to pique your interest, and if you are interested, I'm pleased to tell you that OCaml mode is actually currently available, and it's a breeze to install. Just simply download it from OPAM, and then load it in your Emacs.d. As a warning, you will need an Emacs instance that supports dynamic modules. Now, if you're interested in contributing or looking at the code, feel free to check out the QR code in the corner or the link above it. And I guess that's about it. So thank you for your attention, and I look forward to your questions.
Thank you, Kieran.
Thanks for the hosting the talk and all the emoticons floating on screen.
Mm-hmm. So we have a lot of questions. So let me start with the one from Francois. So Fred, can you display the question? Yes. So do we have to choose between OCaml or Merlin? Or can we use both at once? Could they be integrated in the future?
So you can use both at the same time. In the live demo that I showed, actually, I was using Merlin's destruct throughout the process. It works seamlessly with Merlin as well. So it sort of works in collaboration with Merlin in some sense, because you can, Merlin, the constructs that Merlin outputs often leave type holes, and OCaml has an operation to sort of jump to the nearest hole in the current expression. So that actually works quite well with Merlin.
Cool. Okay, then the next question is from Tim. So what other refactorings can you build on top of this work?
Right. So currently we track the syntax tree in the editor, but we don't track any type information. So that's currently the main limitation. But I guess the next step would be to also load up the type information. The problem with that is that makes the plugin more dependent on your project structure. So I'm still looking into a way of sort of reusing the OCaml build artifacts output by Dune, for example, to perform some more advanced analysis. But that's still sort of a way out at the moment. But hopefully more sort of semantic-aware transformations, yeah.
Then we have two questions from Gabriel. The first one is, other projects would have use for a common OCaml concrete syntax tree definitions. Are there any plans for collaboration or reuse?
Right. Well, currently OCaml just reuses the syntax tree definition by whichever parser version it's using. So currently there are two versions. The talk was slightly out of date because there is a version of OCaml that uses the Merlin parser, and in that case we just reuse the definition that's exported by Merlin, and then normally we use the latest OCaml syntax tree. Yeah, so I guess it doesn't define its own concrete syntax tree definition. It just reuses the current OCaml one.
Great. And the next one is, how do you deal with partial or incomplete buffers with syntactically incorrect or missing bits in the middle?
Right. Thank you for the question. So currently, so there are two versions, as I mentioned, of OCaml. One of them just uses the normal OCaml parser, so it has very little tolerance for invalid buffers. And so you just have to make sure that your code is in the correct state. We have another version that actually uses the Merlin parser, And this gives us some robustness to invalid parse trees. But then the consequence of that is sometimes the sort of syntactic constructs may be slightly different than what you're expecting because the parser can't make a sort of complete syntax tree. Yeah.
Okay. I think we can have one more question. The eLisp snippet in your last slide enables OCaml in OCaml YAC MLY files. How does it work there?
Right. Okay, I guess that's so. OCaml OCaml doesn't work for OCaml YAC, but it turns itself off, so you won't have any. Yeah, I think that's an old set of setup files. But if you load it in one of the sort of either OCaml YAC or Menhir files, they'll just turn itself off, so you won't sort of be disturbed. But yeah, we can't really parse that at the moment.
Okay. So I think it's time to switch to the next talk. So thank you again, Kiran.
Thanks.
And so Fred, could you please bring the next speaker onto the stage?
My name is Laurent.
Okay. Our next speaker is Laurent. The talk is about how to use OCaml libraries in Python programs. Please start.
I work as a researcher at Jane Street in the London office. Today I'm going to talk to you about our experience using OCaml and Python together at Jane Street, hopefully getting the best out of each language. You probably already know it, but Jane Street is an OCaml shop. We are using OCaml for mostly everything, and there are lots of things that we enjoy about it. For example, we rely a lot on the OCaml type system to guarantee some invariance. It's pretty amazing to be able to refactor some critical systems and rely on the compiler to stop you at all the places in the code that you have to fix. The OCaml performance is also pretty good when using native binaries. And even better than that, the performance profiles are reasonably easy to understand. Python is at the other end of the spectrum. The default version is interpreted, and it's an order of magnitude slower than OCaml. There is also no type checking, and it's quite difficult to reason about large libraries in Python and guarantee that they will behave correctly. So why would we use Python? There are actually quite a few advantages to it. Python has become, over the last few years, the de facto standard for data analysis. Its lightweight syntax makes it very easy to use, and it has a thriving ecosystem of libraries for numerical computations, plotting, machine learning, etc. A common way to perform data analysis in Python is to use some notebooks. The experience there is very interactive. You just try to adjust the code by looking at the current output until it produces what you would expect. When it comes to, for example, reading a CSV file, extracting a time series of data, and quickly plot the data, and then compute some statistical indicator on it, it's very hard to do better than this notebook experience. Overall, it's quite different from when using OCaml. Python is mostly used as some glue code between different libraries. And in your case, it's mostly to write code that will be discarded soon after being used. Doing so in OCaml would be quite annoying because you would have to handle all the edge cases until the compiler gets to generate the binary. In Python, you can get away by focusing only on the bits that you care about. Though obviously it's easier to shoot yourself in the foot in this setting. So our goal is to leverage Python for this fast interactive development experience, but back this with OCaml services and libraries that are robust and will scale well and perform quite faster. So the standard Python interpreter is called CPython. It actually has a pretty nice C API that can be wrapped in OCaml. For this, we've relied on PyML, which is an open source library. We've built several libraries on top of it to optimize for our main use case, which is calling OCaml code from Python. This actually works in the following way. We compile the OCaml code at the shared library, and then Python loads this shared library and calls the endpoint that will start the OCaml runtime. The OCaml code then starts executing, and it registers various modules and functions using this Python C API. Once this is done, the control goes back to Python, and the Python code can just use this function without even knowing that they actually rely on OCaml code. An important point when devising this Python OCaml interaction is that we wanted to be able to write most of the code in OCaml. Because we have more experience with this language, and also because we have overall better practices. Like we have proper unit testing, continuous integration testing, continuous deployment, etc. And using OCaml for all our bindings makes this interact pretty well with our existing systems, and also in general is good for favoring robustness of the code. That said, we obviously have also put some significant effort in making the exposed function Python idiomatic. For example, we automatically generate some documentation. We try to integrate well with existing Python libraries such as NumPy or Pandas that are very commonly used. The main library that we use to write these bindings is called pythonlib. It extends PyML and provides some easy way to define Python functions from OCaml. You can see an example on this slide doing so. First, at the top of the slide, you have the Python side of the things, where we import a module that is called OCaml, that has been defined on the OCaml side, and we call the approxpy function on this module with an integer argument. You can see then the OCaml code that has been used to generate these bindings. Via pythonlib, we expose an applicative functor that makes it easy to define the argument used by the function. In this case, we have a single positional argument called n of integer type. This applicative functor would also support keyword arguments, arguments with default values, and will help checking exhaustiveness, that all the necessary arguments are passed, and also that no extra arguments are passed, and will return nice error messages if there are any mistakes. We then compute some value on the OCaml side based on this n argument, and finally you can see a Python of float call which converts the resulting OCaml floats into a Python value. Then at the bottom you have some top-level code that creates the OCaml module and then attach the approxpy function to it. One tricky bit is converting back and forth between Python and OCaml values. In this example, we've only seen very straightforward values to convert, but it's more finicky to do when converting complex values. For example, OCaml records will naturally map to Python dictionaries using string as keys, but doing such a conversion manually would be quite cumbersome. So instead, we wrote a ppx extension to help automating this process. So this ppx extension can be used to annotate any type, and it will generate two functions. Of Python, that is used to take as input a Python object and convert it to the target type, and to Python, that goes the other way around, converting the target type to a Python object. All the basic type will be automatically mapped to the equivalent type on the other side, and we also have an annotation at python.default so that some fields can be optional and get some default value. This is quite useful because it avoids Python user needing to populate all the expected fields. One tricky bit is the encoding of OCaml variants, as there is no clear equivalent on the Python side. Currently, what the PPX will do is use a pair, where the first element of the pair is the constructor name, taken as a string, and the second argument of the pair will be the arguments of the constructor. We tend not to use it a lot, so most of the time we just avoid exposing types that involve variant and try to rely more on records. So we mentioned that we've used pythonlib to expose a wide variety of libraries and services in Python. Actually, we've exposed a bit more than 35 of them at this point, and one of these libraries is quite special. It's the Toploop API. So this library that is provided by the OCaml compiler lets you build easily some read eval print loop environment. By wrapping it in Python, you can pass it a Python string that contains some OCaml code, and then evaluate it. So we've put together such bindings, and we also used some Jupyter magic. So on the right-hand side of the slide, you see some Jupyter cells. And for example, this %% OCaml magic, what it will do is take the content of the cell as a string and pass it to some Python function. This Python function will then pass it to the OCaml side and to the Toploop library there, so that it actually gets executed on the OCaml side. So you can just have cells that contain OCaml code. You can see on the next cell another magic that is %OCaml. On the line RPN equals %OCaml RPN, the %OCaml will convert the OCaml values to Python values, and it even works for closure. So the right-hand side RPN is actually the OCaml function, and the left-hand side is the resulting Python function. And then you can see over the next two lines that this Python function can be used as any other Python function. So we mentioned at the beginning of this talk that we enjoy the performance of OCaml. Now that we have this integration of the OCaml Toploop in the notebook, it's quite easy to check that. So here you can see in the top cell an implementation of the n-queens algorithm in OCaml. This algorithm just counts the number of ways to put n-queens on a n by n checkerboard. It's a pretty backtracking approach, and it serves us as a CPU-intensive benchmark. So we define the function in the first cell, and in the second cell, we make a Python function out of it, and we compute the output on some values. Then we of course do the same on the Python side, writing a function to compute the equivalent output, but using Python code, and we try to stick to the same algorithm. You can see here a comparison of performance. The left column is the OCaml timing, and the right column is the Python timing. And OCaml turns out to be a bit more than 5 times faster than the equivalent Python algorithm. It's actually even better than that, because we use here the bytecode version of OCaml. Switching to native code would likely make the difference even larger. So writing such bindings has proven to be quite an easy thing once we had the proper idioms in place in pythonlib and once we had this PPX extension. But not everything is actually easy. So a pretty tricky part is managing memory. We want there the two memory models of Python and OCaml to line up. As most of you probably know, OCaml has some form of garbage collector to manage the memory. Python, on the other hand, uses ref counting. It still has a garbage collector to handle cycles. So when values are exchanged between the two runtimes, we would have to inform the runtimes about what just happened. For example, if you take a Python values and pass it to the OCaml side of things, you will have to increase your reference count. And then when the value disappears on the OCaml side, you can decrease the reference count. And you can use a GC finalizer for that. Conversely, if you pass an OCaml value to the Python side, you want to inform the OCaml garbage collector that it's not safe to compute this value for now. And once the Python side has released the value, you can tell the garbage collector that it's okay to collect it. So that tends to work fairly well in practice. However, there is a tricky part when it comes to cycles that cross the Python OCaml boundaries. Such cycles will be a Python value that has a reference to an OCaml value, and this OCaml value has a reference back to the same Python value. In that case, the Python runtime cannot decide to collect the thing on its own, because the OCaml value, it knows that it has some reference count that is one, and it's the end of the pointer that it can see. So the Python GC cannot do anything. And it's the same for the OCaml GC. The OCaml GC sees the OCaml side pointing at some Python value. It knows that these Python values are live, but it doesn't know that these Python values are pointing back at OCaml. So none of the two runtimes can decide on its own to garbage collect the thing. We actually don't have a very good solution for that at the moment. We rely mostly on automated tests to monitor for memory consumption and check that such cycles don't appear, and on reports from users. So we already had the case of such a cycle occurring in practice, and hopefully that will not happen too often, because it starts to be a bit of a convoluted setting when you have pointers that cross the boundaries both ways. But still, it's something that can happen. So there are multiple things that we would like to work on next to make these bindings even better. The first thing is improving the cooperation between the OCaml and the Python runtimes. So we use async on the OCaml side for async computations. And currently, when the OCaml code is running, the Python code is blocked. And when the Python code is running, the OCaml code is blocked. This makes it quite easy to reason about the code, but is far from being optimal. And we would like to improve that by letting both the OCaml and Python side run simultaneously in different threads. Ideally, we would even be able to map the deferred values from OCaml async to the equivalent Python values, which is the async await syntax. That would be fairly neat, because this way a Python user could decide in its notebook to trigger an OCaml computation. He would immediately get the control back, be able to work on other stuff, and at some point to check back the results of the computation, or to tunnel the computation to another function and get a deferred for the next stage of these computations. We would also like to improve the user experience. So for example, our users tend to rely a lot on pandas data frames, and using a library like Arrow would make it nicer to exchange data between the two different sides in this format. It would even be possible not to have to copy the data around each time. We would also like to make the bindings more Python idiomatics and more transparent, like have nothing that lets the Python runtime know that they're actually not real Python functions. Finally, we would like to make it easier for people to write Python bindings. An idea that we already looked at in the past is automatically generate these bindings from the OCaml compilation artifacts. So what we did is, using the CMI compilation artifacts, automatically generate some OCaml code that will wrap the code that produces the CMI in a way that can be used in Python. The prototype that we had worked well, but it has a drawback that the generated code doesn't look very Python idiomatic most of the way. So there are probably two ways to improve on that. One of them will be to accept that the code that you generate is not very Python idiomatic, and then have a Python layer that would, on top of it, do the conversion to make it nicer on the Python side. The benefit of this approach would be that it will be easier for users to hack around, and if they don't like the conversion glue that we added on top of the OCaml function, they would just be able to copy and paste the code and tweak it. Another way to get around that would be to annotate OCaml functions with some form of PPX, so as to decide that they're exposed to the Python runtime and give some hints about how the parameters should be handled. That's what something like the PyO3 crate does in the Rust world. So yeah, you can find all our code on our GitHub repository. You would want to search for pythonlib and ppx python. And that's pretty much all that I wanted to talk about today. So please, if you look at your code and have any feedback or questions about it, just reach out. Thank you for your time.
Thank you, Laurent.
Thank you.
Okay, we have two questions. The first one is from Dmitry. Do you have any numbers about comparing performance of bytecode and native OCaml top level versus interpreted and compiled Python repo?
Yeah, thanks for the question. So I don't have any hard numbers at hand. I guess when it comes to comparing bytecode versus native OCaml, there will be far better experts than me in the chat that could give details about that. When it comes to comparing interpreted and just-in-time compiled Python, it can be the case that the just-in-time compiled Python is an order of magnitude faster. But one thing to keep in mind is that it's not the typical Python use case. So the just-in-time works super well on loops, but because of the slowness of the CPython interpreter, people tend not to write loop in Python and rather rely on C libraries to actually do the heavy lifting and all the numerical operations. And obviously, these C libraries are pretty efficient. That said, they're also a bit painful to use because it means that when you want to do a loop in Python, you have to find the equivalent operation in NumPy or whatever is your library that will do the loop on the C side for you.
Thank you. The next question is from Haochen. Do you have a pip package? If not, do you have a plan to make one?
So we do indeed have a small pip package that just includes this top loop thingy, and so that allows mixing Python and OCaml in the same notebook. That said, it's a problem with pip package that embeds binaries is that it's hard for them to work on any platform. So the current version actually works on Colab, like the Jupyter-like platform from Google, but I haven't tested it much on other platforms.
Okay. The next question is from Gabriel. I suppose your work is not usable from PyPy itself as it relies on the CPython API. any plans for implementation portable bindings in the spirit of HPy?
Yes, so the first point is definitely spot on. Indeed, we rely a lot on the CPython API, and so we are not portable with other Python interpreters. I didn't know about HPy, so I cannot really comment on that. That said, what we are doing right now is trying to minimize a lot the Python side of things, like the interface with the interpreter, making it as minimal as possible, and putting all the logic on the OCaml side. So we hope for that, like thanks to that, to be able to easily switch the Python layer.
Okay. And a question from Anu. Do you have any plans to write high-level interfaces to the machine learning ecosystem, like PyTorch? Or would Python lib be a good base for the community to work from to do so?
Yeah, so when it comes to PyTorch, I'll do a bit of a self-plug for something called OCaml Torch, which is a library that I wrote, who actually lets you use PyTorch from OCaml, but it doesn't go through Python. PyTorch has a very nice C++ API, and OCaml Torch will just talk directly to that API without putting any Python in the picture. Things for which it's nice to use Python lib, like the other way around, exposing Python libraries to OCaml, are typically plotting libraries, such as matplotlib. That's something for which we've written some small bindings. We don't have definitely plans on pushing on them, but that could be a nice use case.
All right. There's a question on YouTube. Do you have any issues with regard to differences in integer representations?
Yeah, that's again a very interesting question. So we actually don't do anything smart about it, but obviously it's not correct because integer in Python are arbitrary precision, whereas integers in OCaml are like 63 bits or whatnot. So it can definitely be the case that the integer won't fit. And right now it's just undefined behavior. And that's something that we should try to fix and go to Zarit or whatnot, rather than just going to like arbitrary behavior.
Thank you. We still have 2 more minutes. If you have any further questions, we might be able to handle one more question. And actually, I was wondering, so you mentioned conversion between OCaml and Python, and I was wondering if you have proved any formal properties like semantics preservation.
No, we didn't do that much on that front. I don't know if there is any kind of a formal model for what the Python behavior should be like, but it's kind of a tricky bit. People tend to work around idiosyncrasy on the Python interpreter, and that explains why using the main Python interpreter can have different behavior compared to other Python implementation. It would be nice if it was a bit more standardized, but it's not the case right now, and so we haven't done anything to kind of analyze how we would react to that.
I see. Thank you.
Thank you.
Okay, so let's thank the speaker again. And now let me introduce the last speaker of this session, Sudha. Please come onto the stage.
Greetings, everyone. Welcome to the presentation on adapting the OCaml ecosystem for multi-pore OCaml. This is Sudha, and you will probably meet Ankurant, Sadik, Tom, and Casey in the Q&A session following this presentation. Just to give a quick overview on what this talk is going to cover, we will go over what is multi-core OCaml, the motivation for this talk, the distinction between multiprocess and multi-core OCaml programs, building packages with the multi-core compiler, global state and how that affects the thread safety of multi-core OCaml programs, semantics of systhreads, breaking changes that were introduced in the runtime during the process of the multi-core OCaml GC development, and an example of a library that was parallelized with multi-core OCaml, that is LWT. So what is multi-core OCaml? Multi-core OCaml is an extension of OCaml with support for shared memory parallelism via domains and concurrency via algebraic effects. What do we mean by parallelism and concurrency in this context? So parallelism is the ability to run computations simultaneously. When these simultaneous computations are run on multiple CPUs, we will observe speedups in the running time of programs. Concurrency, on the other hand, is the ability to partition computations so that they can be executed in overlapping fashion. So OCaml 5.0 will have support for domain-only parallelism. Concurrency primitives such as fibers and algebraic effects are expected to land in the subsequent releases of OCaml after the 5.0 release. What is the motivation for this talk? So as I already told you, OCaml 5.0 with multi-core support is just around the corner. The upstreaming process has already started, and some large patches such as the safe points have been merged to trunk. There's increasing interest amongst the library authors to port their existing libraries to multi-core OCaml. So the aim of this talk is to make people aware of changes that come with the multi-core runtime so that they are equipped to deal with multi-core compatibility for the libraries. We do hope that this talk will be useful to all users of multi-core OCaml on maintaining compatibility on various different areas that we are going to cover. So at this point, we should make the distinction between multi-process programs and multi-core programs clear. Admittedly, due to the lack of multi-core support, people use Unix fork syscall to speed up the execution of their OCaml programs. To convey the status of Unix fork on multi-core OCaml, Unix fork syscall is not supported in multi-core programs that have more than one domain. They do function as they are expected to be when there are no more than one domain in a multi-core program. That is, when the program is still sequential, but they are expected to fail as soon as any domain is created at any point in time. So we recommend that in multi-core OCaml programs, Unix create process can be used as a replacement for Unix fork primitive. The distinction between a multi-process and a multi-core program in this context is that in multi-process programs, the parent process and child process have their own copy of global data, including the heap, but that is not the case in multi-core programs where the global data is shared amongst all the domains that are present. This affects the thread safety, as we shall see in a subsequent section. Before that, how do you build your package with multi-core OCaml? So the good news is that multi-core compiler is available in OPAM repository, and all you have to do is to create a new switch, as you see the command here. There are two different variants of the multi-core compiler available in the OPAM repository. So the first one is 412 plus domains. This has support for domains-only parallelism, and this is the branch that is close to what is expected to be OCaml 5.0 soon. There's another branch, 412 plus domains plus effects, that contains support for both parallelism and concurrency through algebraic effects. We recommend that you use 412 plus domains unless you're using algebraic effects in your programs. So we have deployed some infrastructure to keep a tab on the status of the ecosystem, one of which is OPAM health check. OPAM health check builds and runs the test suite of all the packages that are available in 412 on the 412 plus domains-only parallelism branch once every week. And it reports any new build failures as such. You can check out the OPAM health check on the link that is visible in this slide. So this has been helpful to us to discover any incompatibility on the existing libraries, as well as it has been helpful to discover bugs in the compiler and to fix them. So the other part of this is the OCaml multicore CI. OCaml multicore CI is deployed on the OCurrent pipeline. It monitors a select set of widely used OCaml packages such as Ermin, Coq, etc. They are monitored for every commit that we make to the 412 O plus domains branch, so that we keep a tab on the compatibility with the ecosystem as closely as possible. We do hope that this will be useful in catching any bugs early on and fixing them. So moving on, global state and threat safety. As we know that OCaml allows mutable variables, and mutable variables are widely used in many OCaml programs for both efficiency and correctness in some places. So they are fine in sequential programs, but what happens in concurrent programs that have mutable variables is that concurrent modifications of mutable variables can lead to non-deterministic results and race conditions. We are developing fuzzing tools to detect data races, and they will be available for use soon. Do check out the Parafuzz talk happening in this same workshop for more details on the fuzzing tools. So the takeaway here is that care needs to be taken to ensure that mutable variable modifications are thread safe and they do produce deterministic results. In order to ensure that, what does multicore OCaml have to offer? Multicore OCaml offers these primitives for synchronization. So the first one is atomic values. Atomic values are similar to mutable references, except that it guarantees atomicity. Internally, it uses the compare and swap operation to ensure that all the mutable references can be converted to atomic variables in multicore OCaml programs. We have support for synchronization primitives such as mutex, condition variables, and semaphores. They are expected to work with both domains and systhreads. Next is the domain local storage. Domain local storage provides APIs to have particular values that are local to a domain. They are stored as key value pairs, and a value that is attached to a key is local to that particular domain, and it cannot be accessed from any other domain of that program. It is GC'd as soon as the domain is terminated. We will also have a bunch of concurrent data structures such as concurrent list, concurrent queue, concurrent hash table, etc. They will be available in the parallel programming library domain slip. The concurrent data structures can be used in multicore OCaml programs in place of the sequential data structures that exist currently. To give an example of how atomic module can be used to ensure thread safety, as we can see, this is a simple counter that increments reference by a value n. If you see this part, we have a reference variable that is starting at 0 for the counter, and it increments the counter. But what happens when we increment, when we call the increment from multiple different domains is that we cannot reason about the order in which the operations are executed. So inevitably, this will lead to some unexpected operation happening and to unexpected results. So to counter that, all we have to do here is to make this variable atomic and increment the value atomically. This will ensure that the operations are happening deterministically, and we do get the result that is expected, which is, in this case, the value is incremented by 100 and the result will be 100 in the case where we use an atomic variable, but we cannot predict what the result would be in the case when we use a reference variable. Sorry, a mutable reference. When we talk about thread safety, we know that the standard library has a lot of data structures which allow mutable values. So natural question arises on what the status of them would be. So standard library is not going to be thread safe by default. There are some mutable interfaces present in the standard library, such as queue, stack, hash table, etc. And they are not, and they will not be thread safe by default. Why is that the case? This is the case because making them thread safe will incur overheads on sequential programs that are not necessary for sequential programs at all. So the option is given to an user where they can wrap these mutable data structures with a mutex so that they are thread safe in a multi-threaded environment. Or these data structures can be replaced with their concurrent counterpart, such as the lock-free queue or the lock-free stack. Also, the memory model of multi-core OCaml guarantees memory safety even for programs that have databases. For more details on the multi-core OCaml memory model, it is recommended that you go through Bounding Data Races in Space and Time that was published in PLDI 2018. So there are some interfaces in standard library which appear to be pure, but they do use some global state internally, such as the random module or the format module or the hash table module. So what is the status of these modules in multi-core OCaml? They are still thread safe to be used in multi-core OCaml, and they can be used safely from multiple domains. The global state present in these modules internally have been converted to thread local state so that they still operate as though they are operating sequentially at the same time that they can be called from multiple domains and used without any non-determinism. So systhreads in multi-core OCaml. Good news is that the systhreads implementation in multi-core OCaml is compatible with the stock OCaml's thread API. So we expect that any program using threads is still expected to be run in the same fashion in multi-core OCaml as well. There are two categories in which we have to distinguish how systhreads are going to work, namely in sequential programs and in parallel programs. So it's quite simple in sequential programs. They are expected to behave as they behave in stock OCaml, and there is no upper bound on the number of threads that can be created at any point in time. On parallel programs, there are some changes that you need to be aware of, which is that when a systhread is created from a domain, it is attached to that same domain until the systhread is terminated. So what it means is that there's going to be no load balancing on executing the systhreads. Imagine this scenario. Let's say we have two domains, domain 1 and domain 2. Domain 1 creates 100 systhreads and domain 2 doesn't create any new thread at all. So domain 1 is going to execute all the 100 systhreads until they are done, while domain 2 is going to remain idle unless it has something else to do. So there is no load balancing on the domains. If there's a need for load balancing, that has to be done manually. Threads that are registered from the C API are always bound to domain 0 so that they don't terminate unexpectedly, as termination of domain 0 means that the program has already ended. So we are slowly venturing into defense against the dark arts. There is changes in the runtime. Good news first is that there's no changes in the C API due to the stop the world parallel minor collector. So the existing C API is expected to work as such. The development of the multi-core garbage collector has led to breaking changes in code that explicitly access GC internals. This is because the multi-core GC no longer needs some of the GC internals, as well as it adds a few GC internals that do not exist in the stock OCaml GC. So programs that access the GC internals directly might need to be checked against the multi-core GC and modified according to the multi-core GC's API. The major changes in the runtime are these. Multi-core OCaml has a new lazy implementation that works in a multi-domain environment. Next thing is that naked pointers, that is out-of-heap pointers, are not supported in multi-core OCaml. There is a distinction in how GC colors are operated in multi-core OCaml and stock OCaml. Some of the runtime global variables are stored in a dedicated structure called domain state. We will look at the details of these one by one. First, lazy values. So lazy values, as we know, will be forced once it is called, lazy force is called. So in multi-core OCaml, lazy values cannot be forced concurrently from multiple domains. When that happens, it leads to an exception called lazy. So we see here that the program tries to force the same lazy value from 4 different domains. When that happens, it raises an exception called lazy. How do we tackle this? One way to do that is to use the try force operation. Try force operation checks if the lazy value is being forced by some other domain. If that is the case, it returns a none. If that is not the case, it forces the lazy value and returns the result that is some v. In case the lazy value was already forced by some other domain, in that case too, it returns the result value that is v. We can use this primitive to force lazy safely from multiple domains. As we see here, using try force from multiple domains gives us the result that we expected in this case. Next runtime change is naked pointers. Pointers outside heap, or also known as naked pointers, are deprecated since OCaml 4.11. They will not be supported from OCaml 5.0, and they are not supported in multi-core OCaml. To detect any naked pointers present in your package, there is an useful compiler option, enable naked pointers checker, that can be enabled with the OCaml option NNP checker package that is available in the OPAM repository. Once this package is installed, whenever we run a program, it keeps checking for any out-of-heap pointers present in the program and reports it as soon as it is found. Once we find the address, a breakpoint can be set on this address in GDB or RR, and the exact location of the naked pointer can be found. Once we find that, in order to fix this naked pointers that are present in our programs, we can wrap them up with an abstract tag or a custom tag, and they are good to go. There are some alternative methods of dealing with naked pointers, such as they can be treated as native integers or they can be treated as boxed integers. The next change is the domain state. So this was introduced in OCaml 4.10, and domain state stores a bunch of global variables present in the runtime in a dedicated structure called caml state. So the variables that are present in caml state are domain local. So this includes variables such as the minor GC pointers, including the young pointers, and GC stats that are tracked with the caml state values. In stock OCaml, they are currently present in the compatibility macros. It is highly likely that the support for compatibility macros will be deprecated in OCaml 5.0. So the variables that are present in caml state needs to be called from caml state itself. And it is also useful to check whether them being domain local is going to cause any changes in the semantics in their existing usages. The next runtime change is GC colors. The historical GC colors present in OCaml are black, white, blue, and gray. Since OCaml 4.12, there's no gray color in the OCaml GC, and that has been replaced with multi-core OCaml's mark stack. The GC colors used in multi-core OCaml are marked, unmarked, and garbage. Yes, they're very simple. So we can see that the terminology is different in stock OCaml and multi-core OCaml. So this means that directly referring GC colors while creating the headers or in any other place is not going to work in multi-core OCaml programs. So in order to fix this, the recommendation is that this can be replaced with a more stable API, since the GC colors API is local to the runtime and it is not expected to be stable. In case that it is inevitable to use the GC colors, we recommend that the multi-core equivalent of the stock OCaml's GC colors can be used. So moving on to an example of parallelizing a library with multi-core OCaml, we look at the case of LWT. LWT is a monadic concurrency library that is widely used in the OCaml ecosystem for concurrency. It provides mechanism for effective IO parallelism, but there is no support for CPU parallelism till now. It has support for preemptive threads via the systhreads module. So in order to support CPU parallelism, we do something similar to preemptive threads, and we use multi-core domains to offload the CPU-intensive computations to all the cores that are available to us. This is how we introduce parallelism in LWT. So the domain, LWT domain, is the interface that lets us use parallelism in LWT. This is an example of how that is done. This is implemented via the parallel programming library of multi-core OCaml domains lib. Some of our primitive experiments showed good speedups up to 20 on 24 cores, as you can see in the graph here. So that was a lot of details for one talk. Let's try to summarize what we covered till now. The takeaways from this talk are that multi-core OCaml compiler is available in the OCaml repository and you can use it right now. Global data in your program needs to be handled safely in a multi-domain program. When porting your program, your existing libraries and programs to multi-core OCaml, even from multi-process programs. The standard library is not thread safe by default. People are recommended to use synchronization primitives in order to ensure thread safety. Observationally pure interfaces such as random format and hash table remain safe to be used from multiple domains. Breaking changes introduced in the runtime might affect explicit GC accesses, lazy values, and out-of-heap pointers. We hope that this information is useful for everyone with respect to compatibility with multi-core OCaml. We do hope to get support from the community for the multi-core effort. Please do try to run your library with multi-core OCaml. If there arises any specific cases of incompatibility with multi-core, please do not hesitate to contact us via the multi-core issue tracker that is linked in the slides. You can find the slides and the abstract of this talk in the link that is given in the ICFP website. We are eager to take any questions from you. Thanks. Thank you.
Thank you, Sudha. Are you there? I don't see. Oh, okay, you're not on stage. Hi, Sudha.
Hello.
Hi, hello. Let's look at the questions. Okay, we have two questions from Edwin. The first question is, would it be possible in the future to encode thread safety in the type system or some borrow checker like in Rust? So there is a paper on separating permissions from data presented at this year's ICFP. And as Anil points out in the chat, there's also a paper on safe mutation with algebraic effects presented at the Haskell Symposium.
Right. So yeah, I think Anil's answer answers it. And even if we can borrow some ideas from the algebraic effects paper, I think that's going to be future work. So we should see how that goes in the future. Right now, it's on the programmer to ensure thread safety in multicore.
Thank you. Any other questions from the audience?
I see a question on lazy triforce. So the
yes.
question, yeah.
Yeah. Let me read this out because I don't think people will see this on YouTube. So lazy.triforce returning none. Can we insert a CPU relax pause call in the spin loop there?
Yes, we can very well insert a CPU relax. Domain module exposes the CPU relax instruction directly, so it can be used from there. So we also use that in some places in our code bases. So yes, we can definitely use it there.
Okay. Any other questions? I sort of see Gabriel was asking something in the chat. Oh, there is a question. Okay, if I want to write code in ownership passing step, mutable value owned by a domain, but I can transfer it to another domain with an explicit move call, is there a library I can use to get runtime checking of the ownership discipline?
Yeah, we haven't really experimented with moving ownership from one domain to another domain. What we have done is to use shared variables between domains. So this is something we have to experiment in the future. There isn't such a library currently to check the runtime of values for moving a variable from one domain to another.
Okay, thank you. Any other questions from the audience? If there's no more questions, then let's thank Sudha again.
Thank you.
Yeah, thank you. So this is the end of this session. And I think there will be a table marked OCaml in the lounge. So you're all welcome to visit there and chat with other participants. And I think we will resume in 30 minutes. And Fred, do you have any other remarks, announcements?
No, I think it's all fine. Thank you very much for sharing this session, and see you all in 30 minutes.
Yes, thank you.
Bye.
Bye.
Fantastic.
I think we are live.
Hopefully we're alive. So welcome everyone to the second session of the OCaml workshop for 2021. My name's Tim McGilchrist. I'm a software engineer at Terides. For this session, we've got 4 presentations, a 30-minute talk and 3 20-minute talks. So we've got a lot to get through for this session. Like previous session, we'll have Q&A after the video is played. So our first talk will be on deductive verification of realistic OCaml code. It's a presentation by Mario Piera on the deductive verification of OCaml code using their new tool, Camelier. Both Mario and Carlos will be joining us for the Q&A after the video. So let's start the video.
This presentation has as a basis the work done by myself, Mário Pereira, and Simão Melo Souza. So, we'd like to start the presentation with a sentence we found to be particularly well fitted to it, which is that programming is easy, but programming well is hard. And to fully understand why programming well is hard, we must first define what programming well means. Programming well means creating an efficient program and creating a program that does what it is intended. It will be mainly on the second point that we will focus our attention today. That is because having an efficient program is useless if it has execution errors or if it gives the wrong value as output. So, given that, we can define 3 things we need to program well, and those things are a specification, which is a logic description of the computation to be done, here represented by whats. We also need a program, of course, that describes how to calculate a supposed answer to an instance of the problem, represented by how, and, as a final ingredient, to verify the proposed program and that it does what it is supposed to do, we have to confront the program with its specification, here represented by why. We can see in this image that the specification and the program struggle between each other, and this is where the why part enters as a mediator, effectively confirming if the program and the specification are in agreement with each other. So, for the deductive verification of code, we use the tool called Camelier, which has, as its main assets, the verification of programs written directly in OCaml, being that those programs are provided with a specification using comments in the specification language Gospel. The program is then translated to the verification framework Y3, being that it makes use of the Y3 IDE, presenting a more user-friendly experience by means of a GUI. This is a research prototype under active development. We will now present a small example of a program written in OCaml with Gospel comments. Take this function, mem, which searches through an array of ints A for an integer m, returning a boolean representing the presence of the element in the array. A simple for loop through the array, and if we find the element we are looking for, an exception is raised. This exception is raised to ensure that the program is efficient, acting as a break statement in the loop. But, to verify the correctness of the program, we must provide it with a specification. We can see here that the specification is introduced using comments with the special character at, following the usual parenthesis and asterisk. We introduce, in this function, a loop invariant to guarantee that we are getting closer to the solution during each loop iteration, and a post condition, that if the function returns true, then there must be an I between 0 and the length of the array, where the element at index I is precisely the element we are looking for. Otherwise, none of the elements in the array can be equal to the element we are looking for. Calling Camelier on the program shown before, we enter this Y3 session, where 6 verification conditions are generated, all of them being easily discharged using an SMT solver, such as Altergo, CVC4, or Z3. As for the workflow of the tool, we have seen that it takes as input an OCaml program commented with Gospel specification. If the program is compilable, that is, if it has no errors on the pure OCaml side of things, then it is translated to an YML file, and a Y3 session is started for that file, where we have the verification conditions of the function that can be discharged using the SMT solvers of choice, for example, Z3, Altergo, or CVC4. We decided to focus on answering 2 main questions, that were, can Camelier be used in realistic examples, and do the design choices made in Camelier work? To answer both of these questions, we decided to tackle the proof of the set module, which is present in the OCaml standard library, therefore being widely used. So, it should come as no surprise that the set module is a container data type and that it provides the usual set operation such as add, remove, union, subset, etc. This module is built on top of an AVL tree data structure, being the AVL tree a self-balancing binary search tree. The AVL trees in this module, however, have an interesting feature, that the balance factor used is of no more than 2, which is quite more permissive than the traditional balance factor used in AVL trees, which is of no more than 1. So, that being said, you might ask why 2? Well, using a balance factor of 2 proves to be more efficient in real use cases, effectively making a trade-off between the overall balancing of the tree and the excessive use of the rebalancing function. As for the signature of the set module, the module type order type represents the input signature of the functor make. As for the output signature of the functor make, it is here represented by the module type s. The make functor constructs implementations for any type, given a total ordering function compare, which should behave as the usual compare function in OCaml. So, for the data structure verification, we decided that a good example of it would be the ball function, because even though it is an internal function, it is of the utmost importance for the AVL trees. Assuming we have a call to ball of LVR, this function will create a new node with left on L, value V, and right on R, performing one step of rebalancing if needed. However, it is expected that L and R are AVL trees and that their heights differ at most by 3. All the elements of L must be strictly smaller than V, and all the elements of R must be strictly greater than V. Given that, the function returns a new AVL tree, where the element V has been inserted. We'll now show the specification of this function, written in a gospel comment. And, as you can see, it is not much different than the affirmations made in the slide before. Here, we introduce 4 preconditions using the requires keyword, where we say that L and R must be AVL trees, where their height must differ by no more than 3, that all the elements of L must be strictly smaller than V, and all the elements of R must be strictly greater than V. Given that, we introduce 5 postconditions using the ensures keyword, where we ensure that the resulting tree is an AVL tree, that all the elements present in L and R are also present in the resulting tree, and that V is also present in the same tree. We also ensure that if the resulting tree differs in height from the maximum height of L and R by at most 1, we also ensure that if L and R do not differ in height by more than 2, then the resulting tree will be the same as a call to the create function, which performs no step of rebalancing, effectively ensuring that the rebalancing step is really only done when needed. And because we believe a demo is worth 1,000 words, we'll now showcase the verification of a function that uses ball.
Alright, so for this live demo, I've picked only a part of our proof of the set module from the OCaml standard library. Okay, and as expected, it features the functor make declaration, together with the set data type declaration as well, and some gospel elements, like for instance, logical functions, okay, to be used in specification, lemma functions written in the form of OCaml functions, a predicate, in this case what it means for an element to belong to a tree, all right, the logical representation or the logical definition of the height of a tree, another lemma, and now the predicate that states what it means for a tree to be an AVL tree. It has to respect all of these conditions, right? Or just to be simply a binary search tree. I'll not go into many details about the gospel specification at this point. I'll focus mainly on the proof of the OCaml functions from the module set. Okay, another lemma function, and finally we get to the first actual function from the set module, right? A very simple one, the one that computes the height of a tree. So in this case, what you do is that in our gospel contract, we name the result of the function res, okay, and we state as a precondition that t, which is the name that we give to the argument of the function, t must be an AVL tree for this function to work well. And so we say that as a result, as a post condition, the value that the function returns is the same value as the one represented logically as the height of a tree. Okay, so this call here is to the logical function height and not to the programming function height. To not be confused. Next function is a create function. Okay, and together with this contract. The bal function, which performs one balancing step if needed. Okay, this one is much more interesting when compared to create. Okay, there's a bunch of cases and subcases. Right, it's gospel contract. And finally, the last one is the add function, which adds an element to the set. Add is actually contrary to bal and create is a function that is exported to a client of the set module, which means that you can call the add function, but you cannot call neither create or val. These are internal functions. All right. So since we have the code, which is exactly the code that you can find in the OCaml standard library, annotated with gospel elements, right? We can now start our proof using Camel. And so this is as easy as typing Camel followed by the name of the module, in this case demo.ml. And we are immediately presented with the Y3 IDE, Integrated Development Environment. Okay, so on the left hand side you have your proof tree, and on the right hand side you have your code, the OCaml implementation and gospel specification. As you can see, I have already performed the proof of some of the auxiliary lemmas that I've introduced. Okay, so let's just jump ahead into the proof of the height function. Okay, this is a very simple one, as I stated. So now I can choose the task tab in order to inspect the verification condition that Y3 generated for the program that Camel translated from the OCaml input program. Okay, and so the goal represents the verification condition that I'm trying to prove. All right, and above this line, I have all the hypotheses that are in my proof context. This is called a task in Y3 terminology, and this is exactly what is sent to SMT solvers. Right, so the goal for the create function is actually a very simple one. So for instance, if I choose directly the height node and I type here, let's pick CVC4 as our first attempt for an SMT solver, and you can see the green button appear, which means that SMT solver is able to discharge the verification condition for a height function, which means that the specification, or better said, the height implementation adheres to the its specification. Now, moving into the create function. All right, so this is a more interesting one when compared to height. I can take a look into the generated task, which I see that the goal is now a larger formula, but let's try to prove it directly as well using CVC4. Okay, and CVC4 is also able to discharge it in almost no time. So it is still doable directly. This formula here on the right hand side is still doable, still amenable to an SMT solver to directly discharge it. And now I can be brave and jump ahead into the val function. All right, so now if I look into his task, now I see a huge formula as the goal. And so it comes with no surprise that the proof of this function is much more difficult, so it does not fit into this live demo. Let's just go take a look into very particular details of this proof. So the first thing that I do is to use the split transformation from Y3, which is going to generate simpler verification conditions from this huge formula. Okay, right, so you can see that now your task is easier, and in particular goal is much easier. Okay, so let's take a look, for instance, into this precondition 17. Okay, going back to the code. So in this case, the yellow part represents what I need to prove here. It's a call to create. All right, and so I see that I'm trying to prove the precondition of create that states that the element, or all the elements of the right-hand side tree, or the R tree that I pass to the create, this one here, all of those elements must be greater than the element v being the second argument of the function. So in this case, it is LV, right? So which means that I need to prove that LV is strictly less than any element returned by this nested call to create. Okay, so if I take a look at this particular task for this particular verification condition, okay, let's go a little bit up in my hypothesis context, right? And I can see two hypotheses, H12 and H13, all right, that are still pattern matchings, and this means that I can still help a little bit SMT solvers doing some case analysis. For instance, a subcase of this proof would be when the R tree is empty, okay, and the other one when it's not. And also another subcase would be when L is the empty tree and when it's not. Okay, so if I do another split here, I call the split transformation, I can now go into the one of the two generated new verification conditions. All right, and for instance, if I go up, now I see that H12 is no longer a pattern matching, and now I see that I'm in the case, H13 is no longer a pattern matching, and now I see that I'm in the case where R is the empty tree, and the second one, with no surprise, states that, all right, it is not. So it's not the empty tree. So, okay, so I'm doing I'm helping SMT solvers doing some case analysis here. Okay, but still, I still have another pattern matching, which I can split in order to make even simpler verification conditions. And when I get to that point, no more pattern matching in my hypothesis context, right? So at this point, it is very easy for SMT solvers to discharge these verification conditions. So for instance, I call CVC4 on the first one and Z3 on the second one, and they are able to automatically prove them. Okay, so remember that now we are in the case where L is not the, when R is not the empty list, right? So if we do now another split, we'll destruct the H13 hypothesis. Okay, so it's easy when L is the empty tree, but it's trickier when L is also not the empty tree. So in this case, I need to help my proof a little bit by doing an assert. All right, and this is a logical cut. Okay, so what I'm trying to prove once again is that LV is strictly less than every element resulting from the tree after calling create. Right. So in particular, I must say that X3, which is a renaming done by Y3, but X3, after some inspection of the proof context, you can guess that X3 is LV, right? So in particular, X3 or LV is strictly less than V. That's what I'm writing here as this logical cut. And so apparently this helps my SMT solvers to finish the proof. Okay? So now let's go to the proof of the head function. Quite big formula, so let me do a split by pressing my S key of my keyboard. Okay, so now let me try to finish my proof using another SMT solver, AlterGo. Okay, so after some splitting, I see that there are a couple of preconditions, right, and some post conditions that are not discharged. Before trying to call a different SMT solver, let's take a look into what AlterGo was not able to prove by itself. So it says here that I'm trying to prove a precondition of a call to the BALF function using LL, V, and R. And so what is interesting here is that LL is now the result of a recursive call to head. This is important. Okay, and so what is the precondition of BAL that I'm trying to prove? I'm trying to say, okay, I'm trying to prove that the difference between LL and R is at most, the difference between the heights of these two trees is at most 3. Okay, and so this is not provable at this point, given this specification, this hotspot specification. Why? Because I also, since LL is the result of a recursive call to add, now I need to add a post condition that actually states something about the height of the resulting tree after calling add and the tree that is its second argument. Okay, so what I'm missing here is a post condition to this function. So I return to my to my file. So let me do a nicer alignment. Okay, so the post condition that I'm missing is actually this one. So I need to say that the height of a new tree differs at most by 1 of the height of the tree T that is passed as an argument. Okay, so I increase the height of a tree by at most 1 when compared to the height of T. Okay, so now if I can get back to the Y3 integrated development environment, and if I press Ctrl R, so it reloads my proof, so it calls OCaml here once again on the background and asks Y3 to generate a new verification condition for the new specification. Okay, so now let's try to select once again this node, the split VC, call AlterGo, and check if I'm able to prove the remaining preconditions. Okay, so it seems that he's pretty happy with me at this point. Okay, so the preconditions that I was having a hard time proving, now AlterGo is able to discharge them. Okay, so but the post conditions, that's not actually the case. Okay, so let me just inspect the task. Okay, so I think I found the guilty one. This is a huge hypothesis in the form of a pattern matching. So if I select this node here, I press S. Okay, I see that the other ones I was expecting these. The other post conditions are also huge, or have also huge hypotheses as pattern matching. So now let me call AlterGo on everything that is left. Okay, as you can see, now some of these post conditions are proved, only the last one remains. Let's take a look. Okay, you see the huge pattern matching here. So what happens after a split VC? Some of the cases still remain. So with no surprise, let me apply another level of split, and now I'll call AlterGo, and let's see what happens. So now everything is green, which means that the new specification of the head function, let me show you it, with this headed post condition is now proved by SMT solvers. So this means that the implementation adheres to the given specification. What is interesting here, and let me finish by stressing this out, is that in order to be able to prove this post condition, okay, we needed to add an extra post condition also to the val function, one that says that when there is no need for a balancing step, this function behaves as a create function. Okay, so it actually corresponds to this case here. Okay, and in order to do that, or in order to be able to talk about create inside the specification, since create is also a programming function, what we did is that we attached the logic attribute to the create function, which allows OCaml here, or which allows one to use the create name inside specification as well. Or in other words, it also says that this is a pure function, side effect free function that you can use inside other function specification.
For the verification of the use of the data structure, we will approach the proof of the subset function. The subset function takes two sets and returns true if and only if the first one is a subset of the second. To define the correctness criteria of the function, we introduce the predicate subset. This predicate is only satisfied if, for all the elements present in the first set, then those same elements are also present in the second set. As you can see, this function goes through the two sets recursively, trying to find a match in the second set of the element we are seeing in the first one. Eventually, we reach the case where we have gone through all the elements in the first set, and therefore we return true, because we found a correspondence for every one of them on the second set. However, if we go through all the elements of the second set and not all of the first, then we know that there are elements for which we found no correspondence and must return false. As for the specification of this function, we introduce a precondition, where both the sets must be represented by binary search trees, and not necessarily AVL trees, because during the recursive calls to the function subset, we do not guarantee the balance factor between the trees. We also introduce a variant to guarantee that the function ends, here represented by the two sets, because the function effectively ends when one of them is empty. As for the post condition, we guarantee that the output is true if and only if the subset predicate is satisfied. Calling OCaml here on this function generates 13 verification conditions that, through some lightweight interactive proof, can all be discharged using the SMT solvers AlterGo, CVC4, and Z3. For conclusions, we'll first present the proof statistics, being that this consists of 122 lines of code and 117 lines of gospel specification. Calling OCaml here on the file, there are 21 functions to prove, from which 1,141 verification conditions are generated. All of these verification conditions can be discharged using the SMT solvers AlterGo 2.4.0, CVC4 1.0, and Z3 4.0.6. This proof can be replied on an average time of 53 seconds. As for the conclusion on the work, the road so far has been the successful verification of a module from the OCaml standard library. The proof is mostly automated, with very few lightweight interactive steps. Therefore, OCaml seems well fitted for the proof of realistic OCaml code, and it is doable by regular OCaml programmers. The road ahead is proving other modules from widely used libraries, such as OCaml Graph, Base, Core, and Batteries. We also want to prove higher-order iterators, starting with effect-free iteration, such as fold, and then moving on to effectful iteration, such as iter. Thank you for your attention. We'll be available to answer any questions you may.
Thank you, Mario and Carlos. Great presentation. We've got time for a couple of the questions that are in the chat. Can we bring up Gabrielle's question? Gabrielle asks, it looks like SMT solvers struggle with the Y3 encoding of pattern matching, and split helps them a lot. Could split be integrated in the SMT solvers directly?
So just to rephrase very quickly what I have already answered to Gabriel on the chat, yeah, that's most likely a good direction for SMT solvers to provide better case analysis reasoning of some sort. The other thing is the encoding of algebraic data types and pattern matching itself inside SMT solvers, because it has been quite an issue for us in the Y3 team for a while now. But we are aware that recently some SMT solvers, including AlterGo and CVC4, are doing some efforts to better support algebraic data types, and so that could help a lot on case analysis.
Okay, thank you. Another question from Edwin. What happens when the proof fails and you ask for a counterexample from the solver? Does the counterexample refer only to things defined in gospel, or does it have temporary intermediate values due to the translation?
So yeah, that's a very good question, because for now we are only supporting counterexample generation inside Y3. So it's not a thing that we have available on gospel directly. I think the last talk on this session will give some hints about runtime assertion checking, but for a moment, counterexample generation is only available inside Y3. So if you ask counterexample, you need to deal with the temporary YML encoding, so you need to be able to read a little bit of YML.
Okay. One more question from Thomas. It would be great to verify the OCaml C-struct library with this. We've had various bugs in the past due to failing to consider integer overflows. Can Camelier handle that? It looks like it doesn't consider overflow by default.
By default, that is the case, because even if we know about very famous bugs on the overflow side, we decided to shut it down by default, but you can still tune it to be able to prove overflow absence. So, but the thing is that most of the times you really tend to not care about integer overflow, so we shut it down by default.
Okay, maybe one more quick one. Could this be used to prove time complexity of operations, particularly interesting other join, split, merge, etc. operations which are logarithmic, but it's not easy to prove?
So on time complexity in general, I think we could somehow imagine to integrate, and I think we had some projects in the past to integrate the approach by François Potier, Arthur Chaguero, and Armael Guignot on using separation logic to reason about time complexities. So it could be that. So I hope that we can do that inside Gospel. But to prove logarithmic results automatically, that might be a struggle. So in general, reasoning about time complexities for linear operations, something like that, it could be feasible. For logarithmic, I think it would be quite a hard time for automated solvers.
Okay, thank you. We might stop the Q&A there and thank the speakers. And our next talk will be on parafuzz. So the presentation is by KC. It's talking about applying parafuzz which is an input and concurrency fuzzing tool to multi-core OCaml programs.
Right.
Parafuzz builds on top of the Crowbar library and extends it to handle the multi-core parallelism.
Today, I'm going to talk about a testing technique for multi-core OCaml programs using a tool that we developed called Parafuzz. This is joint work with my students Sumit and Adarsh. So multi-core OCaml is an extension of the OCaml programming language that adds native support for concurrency and parallelism to OCaml. By concurrency, I define overlap execution of tasks in time, and parallelism is defined as simultaneous execution of multiple tasks in time. And in keeping with the separation, multi-core OCaml provides distinct mechanisms for expressing concurrency and parallelism. For concurrency, multi-core OCaml provides what are known as effect handlers, and for parallelism, it provides a mechanism called domains. The focus of this talk is going to be testing parallel programs written using domains using the concurrent programming mechanism in multi-core OCaml. So let's take this parallel program written using multi-core OCaml as an example. So in this program, we have a function test that takes an input I, which is an integer, and it creates two atomic variables x and y, where y is initialized to 0 and x is initialized to the input value I, and it spawns a new domain. And the new domain reads the atomic variable, and if the value is 10, then sets the atomic variable y to 2. In parallel, the parent domain sets x to 0 and y to 1, and then waits for the newly spawned domain to terminate. And after that, it asserts that the value of y is not equal to 2. Now the question is, can this assertion fail? Yes, it can. It fails for a particular combination of input and thread scheduling. In particular, if the input value to this function is 10, and the newly spawned domain happens to read the value of x before it is written by the parent domain, but the write to y in the parent domain happens before the write to y in the newly spawned domain, then the final value of y will be 2, and this will falsify this assertion, right? And the point to notice here is that these sort of bugs are what I call logic bugs. These are much more than just detecting data races, right? And in particular, there are no data races in this program, right? So even if you were to use a language like Rust, which avoids data races by construction, these sort of bugs may still manifest. So our goal with this work is to build a tool that is an effective and pragmatic tool for testing these sort of programs applicable for the working OCaml programmer, right, who has a limited time budget and they want to sort of catch these sort of bugs. Okay? So that's the goal for this work. So what are some of the existing solutions? You can stress test your program by running the program over and over again in the hope that the assertion is triggered. Or you can be a little bit more intelligent, where you generate random inputs for the program, but also perturb the OS scheduler somehow in order to trigger the bugs. Unfortunately, these sort of testing techniques are not very effective because of the large input and the schedule space of typical programs. You can do model checking using model checkers such as Spin and TLC. These have very strong guarantees, but are not practical if one has a limited time budget. And there is often the case that there is air gap between the models that you actually model check and the actual source code that you want to execute. Finally, you can try formal verification, but this requires expert knowledge and lots of time and effort. And formally verifying concurrent programs is also hard even for experts. So our goal is to look for pragmatic testing techniques and to build on top. Right? So let's ignore concurrency for the moment and only focus on input non-determinism. In this case, there are a few techniques that we can build upon. The first is property-based testing, where the idea is that you sort of give a property that you need to test, and then you also write a generator in order to generate random inputs to test a function. This technique was first introduced by QuickCheck for Haskell, which has been very effective and has been cloned in many, many languages. The other technique is fuzzing. And the idea here is to generate random inputs in order to crash a program. And the prototypical example here is American Fuzzy Lock, AFL, which is an extremely effective fuzzer. And it is also a gray box fuzzer. What does that mean? A gray box fuzzing compiles the program under test with instrumentation that sort of emits some information about the paths that are taken by the program back to AFL. This coverage information is very useful because AFL can see what paths the program has taken and try to mutate the inputs in order to see whether the program goes into a different path, and thereby maximizing coverage and detecting bugs. Right? And there is this tool called Crowbar for OCaml, which combines fuzzing with QuickCheck to do what is known as coverage-guided property fuzzing. This has been very successful and has been applied to many OPAM packages and has found a number of bugs. Right. So building upon these techniques, what is Parafuzz? Parafuzz is a combination of a Crowbar, which itself is a combination of gray box fuzzing plus property-based testing, applied to parallel programs. Right. And what is our particular challenge here? Our challenge is to control parallel thread scheduling. So when you run a typical parallel program, the operating system controls the thread scheduling. But in order to trigger these hard to find the concurrency bugs, you need to force a particular buggy schedule. So you need somehow to control the parallel thread scheduling, right? How do we do that? The way we do that is through effect handlers. So we mock the parallelism API using effect handlers. So what are effect handlers? Effect handlers are this modular and composable basis of non-local control flow mechanisms, including exceptions, async await, lightweight threads, coroutines, etc. From an operational point of view, effect handlers provide a structured programming mechanism over delimited continuations. So we use effect handlers in order to simulate a parallel thread scheduler over the domain API. And what we end up getting in return is that we don't use the OS thread scheduler anymore. Operating system threads are mapped onto user level threads, and the operating system threads scheduler is actually now translated to a user level thread scheduler, where we retain control over the scheduling decisions, right? And now what we do is we actually fuzz the scheduler. And how do we do it? At every synchronization point, a synchronization point is a point where if you context switch, you lead to some non-determinism. So at every such synchronization point, we actually force a thread yield. And what do we yield to? Here is where AFL comes in. So we actually leave the decision of the next thread to run from the ready queue for AFL. So AFL gets to sort of pick the next thread to run, and the path information sort of is fed back into AFL, and AFL can see whether it has the program has sort of gone into an interesting path which it has not seen before. So what are synchronization points? These are what you would expect, right? The points where you spawn and join domains, where you read and write and compare and swap atomic variables, lock and unlock mutexes, wait, notify, and broadcast on condition variables. So the whole system looks like this. So you would take the program that you want to test, you will compile it with a special compiler that adds instrumentation, and it is run as a daemon with AFL. And AFL sort of supplies the input to this program, but also the thread execution order. And the instrumented program emits the execution path information back to AFL so that it can generate more interesting inputs in order to force the program to go towards the buggy path. So there are several advantages to using Parafuss. Parafuss is a drop-in replacement for multicore OCaml. If you want to test the programs using Parafuss, you just need to install a separate compiler switch, add your assertion, write a generator, and off you go, right? And there are no false positives in the system. If a bug is found, it is a true bug. And when a bug is found, we also get a trace. That is a deterministic trace, which allows us to replay the executions and debug the program. So how effective is this technique? So we take the same example as that we've seen earlier. We are comparing 3 testing techniques here: Parafuss, random testing, and stress testing. And the main takeaway is that Parafuss is the only one that was able to find the bug. Random and stress testing were not able to find the bug in an hour, right? We terminated the program in an hour. And Parafuss was able to find the bug within 10 minutes. Random and stress testing were able to do many more executions, but still were not able to find the bug because it was not heading towards interesting schedule and input combination. Right? That's the reason why Parafuss was able to find the bug in this case. We also evaluated the technique on a number of known bugs that were taken from other papers. These included bugs that were due to racy conditions as well as deadlocks. We were interested in 2 metrics. The first is effectiveness. So what fraction of the runs does the tool actually find the bug? And the second is efficiency. What is the mean time to failure? Right. So we ran the program. We ran each of these test cases for 30 executions for each tool, and we report here the fraction of executions that found the bug. And what you see in this table is that Parafuss was able to find the bug in every execution except one in the CL circular list example. Stress testing was not able to find any of the bugs. Right? Random testing was able to find the bugs in every execution in this one case, which is domain slip. And one other execution in this BI example. So Parafuss turns out to be much more effective than stress and random testing. And in terms of efficiency, you can see that these numbers reported here are in minutes. So Parafuss was able to find, seconds. Parafuss was able to find bugs within a reasonable amount of time, right? So less than around 15 minutes to half an hour, right? And even in the case where the random testing found a bug, Parafuss was able to get to the bug 5 times faster, right? So Parafuss is both efficient and effective. So one particular future extension that we are considering is encompassing programs that have data races as well. So currently Parafuss assumes that programs are data race free, and data race free programs in multicore OCaml have sequentially consistent semantics. This is what allows us to only insert yield points at the synchronization points, right? And still have coverage because our program has SC semantics. But what happens to programs that have data races? So our PLDI 2018 paper shows that for OCaml, we have a very simple operational model that describes the behavior of racy programs compared to, say, the complex operational models that you have in, say, C++ or Java. In particular, in multicore OCaml, a racy read may return one of a subset of writes that have been performed to a particular atomic location. Right? So using this simple model, we can actually extend Parafuss to test the racy programs as well. And the idea here is to use AFL to pick the value that a read should return, and also force a yield at every non-atomic read and write, right? And the challenge here is the latter, right? Can we actually make it fast enough for pragmatic use is the question. This is yet to be seen. In order to summarize, Parafuzz is a property-based fuzzing tool for parallel OCaml programs. It is easy to use. There is a drop-in replacement for multi-core OCaml programs with a separate switch. And the results show that the technique is effective and efficient at detecting concurrency bugs. Thank you. I'll stop here.
Thank you, KC. Any questions put into the Q&A? I think there was one from Francois that might have got answered in the chat. It might be good to do this for the YouTube stream. So question was, as far as I understand, it cannot be used to debug programs that involve races on non-atomic locations. Is this correct?
Yeah, that was covered in the penultimate slide. So we don't cover it yet, but we have a very good idea of how to do that.
Okay, fantastic. Is there any more questions? Nothing in QA. Can I ask a somewhat different question? With the domains, how heavyweight are the domains? Like how many of these domains could you create? Like, for example, could you create an actor system where you have a domain per actor?
So domains directly map to operating system threads, right? So they have additional things on top. So they participate in the GC. So you can possibly create hundreds if you have a large enough machine, but I wouldn't go to thousands, right? And the idea would be that if you wanted to build an actor system, you would want to do that as part of using algebraic effect handlers, right? So you would write that as a library using effect handlers, and then build your own like a scheduler that load balances these actors over a fixed number of cores, right? Where you create one domain per core and then multiplexes them on top. Domain slip gives you an idea of how to do this. We don't build actors, but they are very very close. You have channel-based communication. You have lightweight threads, but that should give you a very good idea of how to build one of these things that don't kill all of the performance.
Okay, thank you. We've got time for one more question. Does Parafuzz provide a way to replay a particular scheduling trace from a failed run?
Yes.
That sounds interesting.
Yes, it does. This comes directly from AFL. So whenever AFL finds a bug, it sort of says, okay, here are crashes that I found, and it produces a input file that deterministically captures the failure. And because we control the scheduler, you can just replay each file. You can just say this executable, this file, oh, here's a bug. And then you can step through and debug it. So you get separate deterministic logs for each one.
Okay, thank you. That's probably about all the Q&A we've got time for the next talk. So thank you, KC.
Thanks.
Okay, our next talk is titled Wibbly Wobbly Timey Camely, and I'm assuming this is going to have some sort of doctor in it. So the presentation is going to cover a favorite topic of mine, which is fraught with danger and bugs, which is time handling. So D. Long and Gabriel have written the new OCaml library for tackling this hard problem. So let's see the presentation.
Wibbly Wobbly Timey Camely. My name is Dilong, or Darren. This is a project done in collaboration with Gabriel Redan. Time processing is messy. Sometimes we get intervals which cross the day boundary, in which case we do not have the same date for the starting time and ending time. Sometimes the interval does not have a fixed duration due to things like daylight saving time. And for recurring intervals, we may not be able to compute them easily depending on the time zone, again due to a varying time zone offset. And perhaps more critically, who remembers the time zone offset of a particular day anyway? Introducing Timere and Friends. It's a scheduling toolbox written in OCaml. It resembles a domain-specific language, or DSL. It provides accurate datetime handling with time zone via the time description component. It provides some natural language processing support via the parsing component. Overall, it is highly expressive and flexible. Here we provide a small example to figure out the common time Gabriel and I have for the conference question time. So we can specify a time constraint as free time, relying on Timere parse to parse our natural language string in English. We specify the conference time. We specify our own time zones, and we finally combine the time constraint, and we finally and then at the last line we attach the individual time zones to the time constraint, and we get our final scheduling object or constraint. And the result is a lazy sequence of pairs of timestamps. We start off by introducing the individual API components. So the first one, as we've seen in the example, is the Timere parse component. So it translates a string into a Timere object, which is the scheduling object. So here we have two examples, and we use the as expression serialization to represent the Timere object itself. And we can see it's equivalent to the direct construction, but it's often quicker to just ask Timere parse to construct simple things like these for you. So now we move on to direct construction of simple terms or atoms. So they ingest concrete information. So in here they would ingest a particular timestamp, for instance, and we can express simple things like the time from now, or the time before a particular timestamp. Next, we move on to something more powerful, and these are very close to how we specify time naturally. Namely, we tend to specify a set of date and time with a certain pattern. So you would say something like the year 2021, month of June, some weekday to some other weekday, and so on. The nicety of this is that we don't have to care about the actual timestamps or the actual or the particular time zone specific information, and we leave that to Timere to resolve. In terms of intervals, we can specify explicit intervals, which are just pairs of start and ending timestamps. We can also specify intervals that follow some pattern for the starting and ending time, but they don't fall on the hour boundary or some other boundary that allows a efficient specification via a single pattern. So for instance, 5:33 p.m. to 6:15 p.m. We can't specify it by picking just a single hour. So in this case, we could use a pattern matching interval. So we can either do a direct construction, or we can do the equivalent via asking for Timere parse help. Next, we begin to talk about combinators. So we start off with intersection. So this is the same idea as a set intersection. So we pick out the common intervals between two expressions. So in our first example, we specify the time from now till the end of the domain, so end of year 9999. And we also and then we intersect that with the time before a particular daytime in Paris. And combining the two, we have specified a range. And the next example we have, we pick out all the Thursdays, and we also pick out all the Septembers. And by intersecting, we are asking Timray to pick out all Thursdays in all the Septembers. Then we have union, so it just merged the intervals derivable from the two expressions. So here it's like all Fridays or the 29th of any month. We also have not, which is complement, so it flips a particular expression. So in this case, we have not Friday. So this is equivalent to picking out all the weekdays which are not Friday. And combined with intersection, this overall reads all 20th, which are not Fridays. Next, we have an important one. So this is with time zone. This allows us to attach a time zone to a term. So the nicety of this is that this allows us to reuse the same term across multiple time zones. And we can also mix and match terms with different time zones together using other combinators. And finally, we have chunking. So this is very similar to the lazy sequence selectors you would see in other libraries. So we specify a chunking method, in this case, disjoint intervals. So it just means that the selector will receive a lazy sequence of disjoint intervals. And then we specify our selector. So it takes every other, so take nth means take every nth. So we take every other item or interval and then pass it on to taking the first 20. And we specify a pattern, picking out all the Mondays from now. So overall, this reads, take every other Monday starting from now, and then pick out the first 20 only. So having a powerful API is nice, but it's not very useful if it ends up being very slow to use in practice. So to tackle this, we address the efficiency concern in three main ways. So the first one is about the memory usage. Internally, everything is a lazy sequence. This gives a better memory footprint compared to other data structures that demand the intervals to be provided up front. So this would include, or at least a naive use of interval trees. The second way is to speed up a commonly used primitive. So in this case, pattern matching primitive is very commonly used by the other constructors and other logical components. And speeding it up would help a lot because essentially it is a hotspot. So we begin by explaining how pattern matching works. So pattern matching is essentially finding out what what date times inhabit a particular pattern. So it's somewhat like a regular expression in some sense. So to achieve this, we use a depth-first search. So in this case, the root of our search tree is a year, and followed by the month, and followed by the day, and so on. The short-circuiting refers to the observation that if after a level, so in this case after the day, all the remaining levels are wildcard. So in other words, no constraints. So it could be any hour, any minute, any second, any nanosecond. Then we can actually stop at the last concrete level. So we can actually stop after processing day. So in this particular case, we can actually pick out the first interval, namely the start of 20th and the end of 20th. So the benefit of short-circuiting is that we no longer have to spend unneeded computational time to go through all the hours, minutes, seconds, nanoseconds, just to combine back into a contiguous interval. Next, we have search space optimization. So this comes from the intuition that when we have a chain of intersection, the term with the smallest search range gives us the biggest clue as to where to begin and where to end. In this case, since one of the we notice that one of the term has a search range of 2021, and so we can naturally conclude it's pointless to go through any other year, and so we can propagate this search range or bound to the neighbors across the chain. And next, we have dynamic search space optimization. So this works for union. So this comes from the observation that if we have a very large interval, then it's not useful to go through all the small intervals that would be within the large interval anyway. So as a concrete example, we have here one that matches the year 2021. The one matches all the 5 to 6 p.m. of year 21 to 2023. So intuitively, it's pointless to actually go through all the 5 p.m.s in 2021 because we are including the entirety of 2021 in our result anyway. So there's not much point in going through the list of all the 5 to 6 p.m.s in 2021, only to add it into the larger set and not introducing any effect essentially. So to mimic that intuition, what we have is that if we can visualize this as a message sequence chart. So if the union operator spots a large interval, so an interval that's greater than 30 days, let's say, then it will propagate the search space, or more precisely, it will slice the search space, equivalent to asking the other terms to skip to a particular time point. And so this avoids the needless search that does not introduce a observable effect. So in this case, we just ask the other term to skip to 2022 instead and start returning the results from then. Finally, some remarks on testing. So we use some unit tests for very basic checks. We use property-based testing for a lot of the logic components. And then we use fuzzing when we still want property-based testing, but randomized input is too slow. So we want something that can time out and something that can make a educated guess during the search. And so a crowbar and AFL is a good fit for this. We use this to test the more time-consuming logic components. And we also use this to test the overall implementation by comparing it to a simple one. So a simple one has a much lower code complexity as it relies on interval trees as implementation. To conclude, we presented 3 components: time desk, tim array pass. They together form a toolbox that is expressive and flexible. Namely, they provide first-class support of time zones, and the combinators constructors work robustly across time zones and boundaries, as they are based on pattern matching. They are efficient, namely they resolve quickly in the usual cases, and they have a low memory footprint. And lastly, the toolbox is quite smart, namely one can construct common terms quite easily via tim array pass. Thank you.
Thank you. Do we have any questions in the Q&A? I think we've got a couple of minutes. Yep, we've got one in the Q&A. What is the database source for the time zones?
So it follows the IANA TZDB. Yeah, so it basically extracts it from the Linux, the copy of the time zone database stored on the Linux distro.
Does that mean that the library requires a Unix environment?
Oh no, so it's compiled statically into a library. So you can opt to. So we don't have a way to have the library access the Linux local file copy directly, because we need the we need access to the transition table to do the pattern matching correctly, and it's that requires extra effort. And simply compiling it into the library itself is easier. So we essentially have a serialized form of the database inside the library.
Okay. We've got one more question from Gabrielle. What's your use case for investing such effort into an impressive library?
So originally this was for a constraint solving to-do list thing, which did not end up happening. So after some discussion with Gabriel Redan, he suggested taking it to like a language approach, so and turning it into something that's much nicer. So users don't have to think about time zone, don't have to think about the search space or how to optimize them and so on.
Okay, thank you. One more question. Anil asks, is the library pure OCaml or does it contain any C? I ask since we have a CalDAV implementation in Mirage OS, and it would be very cool to use this to handle human time inputs in the UI.
So it is in pure OCaml, and it would work for web UI as well. So we have made a small demo called Doodleinator. So it basically uses Timarray to fill in a doodle.com timesheet for you based on your constraint.
Fantastic. One more question. Edwin, it would be great to use Timarray to generate Outlook recurring invites or translate to Slack's limited reminders language. I assume it is possible.
So assuming there is a efficient generation from a list of so the Timarray term is strictly more expressive than simple recurrence, I think. So it boils down to what type of constraint you're trying to translate. So if you can, but one can always translate a list of time ranges into individual separate calendar items. So in that sense, yeah, you can probably generate invites that way.
Okay, fantastic. If there's no other questions, we'll please thank the speaker.
Yep, thank you.
Good. So we've got one more talk for this session. So the next talk will be Nicholas Osborne. Will be presenting his joint work with Clement Pascuito on the use of fuzzing again. This time automatically generating fuzz testing suites based on OCaml interfaces. Let's cue the video.
Hello, my name is Nicolas Osborne. I'm currently an intern at Tarides in the process of completing my master's degree in computer science at Université de Lille. At Tarides, I work under the supervision of the second author, Clément Pascuto, who is in the process of completing a PhD at Tarides and Université Paris-Saclay with Jean-Christophe Filiat. The goal of the work I'm presenting today is to provide OCaml developers a tool that allows to automatically generate fuzzing suits based on formal specifications. This work is based on 3 other pieces of software. I will briefly present them in the following slides. Gospel is a formal specification language for OCaml interfaces. It lets you write formal properties that you expect from your program. The project was initiated by Jean-Christophe Filiat and Mario Pereira. ORTAC is a runtime assertion checking tool. It uses Gospel specification to generate OCaml code that checks them at runtime. It is mostly maintained by Clément Pascouteau. And finally, Monolith is a model-based fuzzing framework developed by François Potier. Specifically, today's work is a front-end for ORTAC. Let's have a quick overview of the workflow with the front-end to advertise how easy to use our tool is. To begin with, the developer writes down the properties they want to check in the form of Gospel specifications alongside the functions and types declaration in their .mli file. Then they can call ORTAC specifying a front-end, here the monolith one. We will print on the standard output the generated code, so the developer can redirect it to a file of his choosing. At this point, main.ml contains the further code that you would usually write by hand. Finally, after compiling this file, they can run the generated batch of tests using AFL fuzz. You can see that it is really simple to use. The remaining important part of your job is to write the specifications. This is going to be a 4-part presentation. First, I'm going to briefly present the Gospel specification language and ORTAC. Then I will talk a bit about the work of introducing a modular architecture into ORTAC to allow different verifications front ends. I will then dive into the details of the monolith front end and how it can help automate the writing of fuzzing suits. And finally, I will present some experimental applications of our technique to existing code bases of the MirageOS ecosystem. I will conclude with discussing some of the limitations of the tool in its current state and the work perspectives that are planned for the future. Let's take a quick look at an example of Gospel specification and what ORTAC does with them. Gospel is a contract-based behavioral specification language. Here you can see a very simple example of such a specification for arraymax function. They are written in a special command starting with the @ character. The first line, called the header, gives names to the arguments on the return value so that we can talk about them later. The next line states a precondition. The array shouldn't be empty here. And the two last one states postconditions, that the return value should be in the given array and that there is no other integer in the given array that is bigger than the return value. This is only a very quick glance at the spirit of Gospel specifications. The language is quite rich, and we are not going to detail all its features now. But here is a reference if you are interested. Based on this specification, ORTAC will generate a wrapped version of this function, checking the specifications at runtime. At its core, ORTAC translates a subset of Gospel into OCaml Boolean expressions. This allows to generate a code that is in the idea similar to the one on the slide. The generated code has 3 main parts. First, it will check that the precondition hold on the given argument. If the test fails, we act accordingly with the behavior defined by ORTAC. Here, the ORTAC error. Then it will call the original function for the computation with a given argument and store the return value in a variable. And finally, it will check that the post condition holds given the return value before returning it. Here again, if the contract is violated, the program will have the behavior defined by ORTAC. At the end, we have 2 versions of the same function, the original implementation and a wrapped version with runtime assertion checking. Again, I omitted a lot of the details and checks that ORTAC performs. It also checks type invariants, unexpected exceptions, and so on. More details are available in this upcoming publication at RV21 this fall. Because ORTAC can be used in various settings, I first had to come up with an architecture that allows to easily add frontend to ORTACs. No, defining a front end mostly consists in two parts. The first part is defining what to do in case of contract violation. The default behavior is that an exception is raised, but one can, for example, build a front end that will only report preconditions violations in order to inform the clients of the library that they are not using it correctly, or just log violations for future inspection. The idea is to be very flexible. The second part lets you embed custom code alongside the wrap version of the library. So the front-end developer can use this wrap version in any way he wants. Once I had this modular architecture, I built a monolith front-end for ORTAC. The idea is to automatically generate a standalone monolith fuzzer ready to run out of the box. So, first, what is monolith? Monolith is a model-based test framework that allows to fuzz library. In a nutshell, the user provides two implementations of the same library, a trusted one called the reference and the candidate. Monolith will then test whether, given the same input, the candidate will return the same value as the reference. As ORTAC lets us with two versions of the same library, we can easily use monolith. But which one of these two versions will be the reference? As the wrap version checks all the contracts of the specifications, it makes sense to choose it as the reference. This is the versions that behave accordingly to the contracts. This is the version we trust. That was for monolith and how we use it. Let's now turn to the specifics of the monolith front end. Recall that defining a front end lets us define violation handling and adding custom code. Let's start with the custom code. Like every test framework, monolith involves a lot of boilerplate code. In the case of monolith, it mainly consists in the test declarations and data in the generators and serializer for user-defined types. Our front end leverages the typing information from the specifications to automatically generate them. Finally, we need a reference and a candidate module. We use the wrap code as a reference and the original code as a candidate. Now that we have seen how to handle the boilerplate via custom code embedding, let's turn to the more interesting question of the contract violation. The case of post conditions is pretty straightforward. In general, monolith checks that the candidate returns the same value as the one returned by the reference. So we just need the reference to not return the computed value in case of contract violation. This is easily done by raising an exception defined by ORTAC when a contract is violated. For example, if the implementation of our function arrayMax returns an integer that is not in the array, the original version will return that integer, while the wrapped one will raise an exception. Monolith will spot the difference in return of the return values and act accordingly. On the other hand, if the original implementation indeed returns the maximum of the array, then, as no contract has been violated, both functions will return the return value, and monolith will consider the run correct. The case of the precondition is a bit different. So, indeed, precondition violations are only interesting for the client of the library. Since the function itself is not even run, there is no information about its behavior. And since monolith will feed the function under the test some random inputs, these inputs won't necessarily respect the function's preconditions. So, in order to avoid a lot of noise, we do not report preconditions violations as errors. Instead, a special monolith exception called please back off will be raised, and monolith will gently ignore the test case. With these steps, we are able to automatically and completely generate the fuzzer. At Tarides, we are starting to use this technique in real-world libraries. So let's take a look at these experimentations. Of course, as ORTAC and its front end are in early stage of development, the story is still short. We used this tool to test modules of the library opt-int on the traversal of graph in Irmin, which both are part of the MirageOS project and maintained at Tarides. I was able to write some specifications for both of them. It showed that our technique can handle decently large specifications, but also highlight some of the limitations of both Gospel and ORTAC. Let's take a look at one of these specifications. Here is a sample of the specification for the graph traversal. The function iter executes a traversal of the graph in topological order and puts the verticals in the resulting array in the order it encountered them. I won't go into the details here, but you can see, for example, that the first clause expresses the fact that the verticals present in the argument skip are really skipped in the traversal. Now, about the limitations and perspectives. Some of these limitations come from the core of ORTAC itself. Most of them will disappear when ORTAC will support a larger part of Gospel. And other limitations are related to the front-end itself. I'm going to focus on one of them, which is data generation. In the current state of the front end, the arguments for the functions are generated according to the structure of their types, but no considerations is taken with respect to specifications that would restrict the possible values of these arguments. For example, in our function arrayMax, the generated argument can be an empty array. Thanks to the special monolith exception, the test won't be taken into consideration, but it is still generated. And even with the fuzzing, a lot of bad inputs are still generated, especially if the preconditions describes a small input space compared to the type of the arguments. To overcome this limitation, we have presently two beginning of leads. The first one is to allow the user to plug specific generators written by hand. This can be easily done, but goes a bit against the idea of ORTAC being a completely automatic tool. The second one still requires a bit of investigations to determine if it is viable. The idea is to find a mean to generate a generator given a type and Gospel terms. This would allow to always generate inputs that respect preconditions. It's not clear at the moment that it is even possible, but if it is, it would allow to always have valid inputs for the functions we test. In conclusion, I have presented the monolith front-end for ORTAC that allows to leverage formal specifications written in Gospel to generate a standalone monolith program ready to be fuzzed. There is still some exciting work to do in order to ORTAC and its front ends to be production ready, but this already seems to be a promising way to get more guarantees about OCaml programs with limited effort from developers. Thank you for your attention. Just know that all the software I've talked about is open source and that ORTAC and Gospel are available on GitHub under the OCaml Gospel organization.
Fantastic. Thank you for the presentation. Please post your questions in the Q&A tab. Looks like we've got one from Gabrielle. Is Nicholas around to answer questions? I'll read it out. Is the differential testing comparison aspect of Monolith important here? It sounds like you are looking for assertion failures, but then Monolith will also compare output values that will always be the same with your approach. Is this it, right?
Sorry, I was struggling with the interface. Can you repeat the question quickly, please?
Sure. Is the differential testing / comparison aspect of Monolith important here?
No, not really. We could have done that with Crowbar, for example. We just have to have a mean to know that a contract is violated.
Okay. One more question from Mario. Can you comment on the time it takes to run ORTAC and Monolith to test big libraries and or difficult specifications?
Not yet. It's what one thing that we will have to do once we can specify and further bigger libraries is to check the time it takes. It's still an early project. It's not really up to a big library for now.
Okay. Any other questions in the Q&A? Yeah, we've got one from Edwin. I used structured guided fuzzing in QC STM style, generate only valid commands and check whether the combination of commands function call on a data structure leads to a failing assertion. What would be the best way to combine that with gospel ORTAC?
Not sure. We have some information about the valid values with the specifications in form of preconditions or invariants for types. If we find a way to use that information to guide the generation, and that would be the answer. That would be what get it done, I think.
Okay, thank you. One more question from Thomas. Can you tell us what the current ORTrace limitations are? Modules, abstract types, etc.
Okay, so for now, ORTAC doesn't really open module in modules, but that's just a little problem of engineering, or perhaps just a little bug. It should do it. Abstract type, yeah. Well, Clément is working on this, on how to handle abstract types. The problem is that we have to find a way to talk about that, even if we don't know how to construct them or deconstruct them. So in Gospel there is something. There are some model you can tell the ORTAC or Gospel that a type have a model, and but that's on the logical perspective, and Clément should have to find a way to compute that, to put it in the computable perspective. And he is also working on checking invariants, so information specification for types that are checked before a function and after, and here too he has some work and some problem to decide.
Okay, thank you. I think that's all the questions that we've got in the Q&A tab. So please thank the speaker again.
Thank you. And just, I'm not Clément, I'm Nicolas. I just had to struggle with the registration and all that. So Clément give me his link. But thank you very much.
Thank you. And that concludes this second session of the OCaml workshop. I think we're back in 30 minutes. I'd encourage people to go and visit the OCaml workshop tables in AirMeet and try and recreate the hallway track for 30 minutes. So see you back in 30 minutes time. Thank you.
Hello everyone. Session 3 for the OCaml workshop is starting now. Hope everything is back from lunch or like or breakfast or dinner, whatever time zone you are. And so the first session will be about, the first talk, sorry, about that session number 3 will be about probabilistic resource limits or programming with interrupts in OCaml. And Guillaume Maccagnoni will do the talk and will answer the question after that.
Hello everyone, my name is Guillaume Maccagnoni from the Galinet team at Inoria, and I am here to present the state of programming with asynchronous exceptions in OCaml, also called interrupts in the terminology of standard ML. They are exceptions that are raised to preemptively cancel a computation under various circumstances, and so they are challenging to reason about because they can arise almost anywhere in the program. In this talk, I will first present you memprof limits, which is a library that implements global memory limits, allocation limits, and thread cancellation for OCaml 4.12. These are new features thanks to the new StatMemProf memory profiler. Then I will talk about reasoning about programs that use asynchronous exceptions. How can we recover from an exception arising at a random place? The thesis of this talk is that ML exceptions are an unstructured facility from which we can carve two distinct reasonable programming structures. This is inspired by the story of Ross error handling. If you do not care or do not use asynchronous exceptions, you can replace it with truly unexpected condition or even bug, which will give you a non-defensive exception handling model. In other words, how confident are you that all the exceptions in your program are properly handled? First, what is memprof limits? Consider two facts. The first one is that in OCaml, you can interrupt a computation by raising an exception directly from an asynchronous callback. This is what happens when you press Ctrl-C in the top level. An exception is raised directly from the signal handler for Ctrl-C. Consider also that the new StatMemProf memory profiler comes with new asynchronous callbacks, and they have very interesting properties about when they are called. For each allocated word, it runs a callback with a certain probability. In our case, we will take 10 to the minus 4. Memprof limits represent new things we can do by combining the two ideas. I had several motivations for writing memprof limits and for giving this talk. The first one is that memprof limits implements features that are not standard in proof assistant. My colleagues in the Galinet team implement the Coq proof assistant. But the Coq proof assistant behaves badly in out-of-memory situations. But we know that it is possible to interrupt a computation and fail gracefully when a user-defined memory limit has been reached. This feature is now compatible with threads and with safe resource management. The Coq proof assistant also provides a timeout for computation based on wall clock time, and it has to warn users that it is non-portable. But we know that it is possible to have a portable and reliable timeout by simply counting how many words are allocated. Memprof limits gives you probabilistic allocation limits for this purpose. So it is now possible to port these two standard features to the Coq proof assistant. The second motivation is that the out-of-memory exception is not reliable in OCaml. The garbage collector can decide to stop the program if it fails to allocate memory. In addition, many places in the OCaml runtime are not resource safe when out-of-memory arises. Both issues would be very complicated to fix. So OCaml needs a better model for out-of-memory situations based on the assumption that small allocations do not fail. Instead, we can propose to use a proper asynchronous exception for small allocation. For instance, a global memory limit as proposed by memprof limit. Then, out-of-memory becomes predictable. It becomes a synchronous exception that only arises for large allocations that are either explicit or implicit. The first motivation is understanding exception safety and resource safety and their interaction. Multicore OCaml will introduce a new primitive resource, fibers. Multicore OCaml has a resource safety model based on cleaning up resources when an exception arises, and triggering the cleanup of resources contained in a fiber by resuming it with an exception. The multicore OCaml designer pointed the well-known difficulties this poses with asynchronous exceptions arising at random places. So it is important to understand how one can program with asynchronous exceptions, including in the presence of first-class resources, in order to make informed decisions in the language evolution. More generally, we would like to promote a non-defensive exception safety model. I will now show you a quick tour of memprof limits. Memprof limits is available on OPAM for OCaml 4.12. I will set up an OCaml top level by running memprof limits, which will in turn run the memprof engine. The first example is global memory limit. They interrupt tasks when the major heap reaches a certain size. You can then attempt to recover by freeing some memory, or you can simply cleanly terminate your program. We first define a task, which will be a memory-heavy function that allocates 2.2 gigabytes with 100 million cells in a list. We then define a monitor, which is the function responsible for running the task. We call limit global memory, and this returns either OK if no limit was encountered, or error if the limit was reached. In that case, we attempt to free memory by calling gc.compact. The whole function runs under a global memory limit of 1 gigabyte. It returns out of memory. The second example is with allocation limits. They interrupt tasks after it has allocated more than some limit. This counts allocations, but not the allocation. So it is sometimes considered a better measure of fuel than counting the whole clock time, because you want sometimes that it is reproducible and portable. The unit we count is 1 kiloword. That means roughly 7.8 kilobytes on 64 bits computers. The task will now allocate roughly 100 million cells, but it will do it piecewise by throwing away 1,000 cells every time it has allocated 1,000. The monitor will set a limit of 500 megawords, or function allocated 300 megawords. It will call the function limit allocation, and it will return the estimated allocation on success, or it will say that the program was interrupted with out of fuel in case of error. We have a success. It has estimated that 298 million words were allocated. We can run it again and obtain a different estimation. Memprof limits is provided with a statistical analysis that tells you that the estimation of allocated words is pretty accurate. The main difficulty with interrupts is not so much managing to raise an exception in order to stop a computation, as it is to being able to reason about the state of the program once this exception has been caught. This can already be seen in the implementation of memprof limits itself. Memprof limits manages an arbitrary number of limits for an arbitrary number of threads, and it uses a shared global state to do so. If an interrupt occurs while this state is being updated, it would get corrupted. Memproof limits comes with tools to reason about the consistency of state. The idea is that we can skip a check for limits if it happens in the wrong place. Indeed, another memproof callback will happen soon enough. This capability, which is necessary for the implementation of memproof limits, is provided to all users of memproof limits in order to reason about the consistency of state. This comes notably in the form of a resource management combinator called withResource. withResource lets you pair the acquisition of a resource with its release. It works as follows. Acquire is called, and if it is successful, then scope is called. In turn, whether scope succeeds or whether it fails, then release is called. It is guaranteed that release is called if and only if acquisition succeeded. In addition, it is guaranteed that during the acquisition and during the release, no interrupt can arise from memproof limits. I want you to think of resource management not simply as something to manage the opening and the closing of files coming from the OS, but as a general technique to mutate and reason about the global state in transaction style. I must mention the known limitations of withResource in terms of expressiveness. This is due to its well-scoped nature. It is not the ultimate solution. Nevertheless, this is the first time that something like this is made possible in OCaml. I now want to recap why all this is new in OCaml and why StatMemproof is important in the implementation. The first reason is efficiency. We want to perform a check both often enough and rarely enough so that performance is not affected. The second reason is the compatibility with threads. The probability of performing a check is proportional to a thread's allocation rate. The threads that allocate the most are also the ones you are more likely to want to interrupt. In fact, we can reason that there is less than 10 to the minus 50 chance of not being interrupted after allocating 8.8 megabytes in excess. The third reason is masking. We want to be able to skip some of the events in case they happen while we are updating the global state. This is possible because we perform the check often enough. In fact, we are more precise. We know that thanks to the independence of the event, this does not affect the statistical reasoning. The fourth reason is that it lets us approximate the number of allocation for any thread. This reminds the similarity between resource limits and memory profiling noticed by Young and Maziar. In fact, this might let us in the future implement local memory limits, that is, interrupting a task according to an estimation of the memory it currently retains. I now want to talk in more details of the reasoning about interrupts. The documentation of memproof limits provide a detailed guide to reason about recovering from interrupts. I believe this will interest you because I think this is the first time this story is told to the OCaml community. There are 3 principles to follow. The first one, do not pattern match on the interrupts. In OCaml, you cannot rely on the fact that the interrupt you raise is the exception that is going to be caught at the place you want to handle the interrupt. The exception could have been caught in the meanwhile and transformed or dropped and replaced by another exception. Memproof limits handles this for you because it will remember whether a task has been interrupted due to a limit. The second principle, re-raise interrupts promptly. Both the Isabelle and Coq proof assistants have found necessary to issue guidelines to treat interrupts specially and re-raise them promptly. Similarly, treat bases option.toy with, which converts an arbitrary exception into data, as an anti-pattern. Memproof limits will help once again because it will enforce the discipline by re-raising the interrupt soon after if you drop it by accident. The third principle, ensure isolation of state at handling boundary. The task to be interrupted must not share state with the outside world unless this state is protected by an interrupt-safe abstraction. Next, I will give examples. My first example of an interrupt-safe abstraction is inspired by poisoning in Rust. Whenever you share state and protect it with a mutex, you record alongside the mutex in which condition the mutex has been released. If the mutex has been released due to an interrupt being raised, then you remember that the state might be corrupted. memproflimits lets you implement this. It provides you with a predicate to test whether the task is currently being interrupted. Then, you can define acquisition and release function that perform the check and that record the condition. This pattern is used to communicate the interruption, and a similar pattern has been used in the Coq proof assistant. Next, instead of invalidating the state, we could simply remember the old value and in case of an interruption, replace the new value by the old value, which is guaranteed to be valid. To summarize, the reasoning about interrupts involves a task to be interrupted and a monitor, which will isolate the task. In order to program the task, there is no need to reason about where the asynchronous exceptions occur. One must only strive to clean up and to fail fast in the event of a failure. The monitor must make sure not to share state with the task unless write access to the state is protected under an interrupt-safe resource abstraction. Now, while researching this subject, I realized that finding a meaningful design for interrupts is an open question since SML. The situation with memproflimits is improved, but it is far from perfect. I propose to go back to the principles of structured programming. As you already know, correctness should follow from the structure of the program. In turn, the structures provided by the programming language should facilitate the patterns of reasoning about the program. OCaml violated this principle. The reasoning about resource safety is currently incompatible with the presence of interrupts. There is a large body of programs and libraries that rely on resource safety and that is currently incompatible with interrupts. When you want to use a library with OCaml, you have to pay attention in which incompatible dialect it is currently written in. Also, ML exceptions try to do two things at once and do it badly. In OCaml, you have catchable exceptions, which include recoverable error codes, jumps for control flow, sometimes exceptions that are a mix between the two. They essentially behave like a result, but more efficient and less typed. Then you have serious exceptions. They include interrupts and bugs. You cannot cache them in the same way. A priori, you do not necessarily want to recover, but you want to clean up and fail gracefully. This is the original meaning of the word exception. This is a story told many times over. The terminology recoverable and serious implies a value judgment. I prefer to distinguish them by how they differ in reasoning. The immediate caller is responsible for recovering or deciding to propagate the exception in the first case. Whereas in the second case, the immediate caller is not involved in the reasoning. Whoever wants to handle the exception ultimately is responsible for making sure that the consequences of the failure remains contained. According to structured programming, they should be offered via two different programming structures, tailored to each reasoning pattern. In the first case, checked exception should give you the best of both worlds between the result type and catchable exception. In the second case, we have to devise what would be a design for panics in ML. So what could be a solution? Remember that two of the issues we had to do with misuses of the catch-all exception handler. The proposal is to ban the catch-all exception handler. For backwards compatibility in OCaml, This probably means introducing a class of exceptions which is not caught by catch-all handler. Just like the goto was replaced by more sensible control structures, we will have to replace the catch-all handler by well-behaved and suitable substitutes. There are various valid uses of the catch-all handler. One is promoting a checked exception into a panic, which is better done explicitly. The second is to clean up before raising. So the whole proposal hinges on the possibility of an expressive enough resource management facility. I believe that once we have identified what programming structures and informal reasoning patterns we need to support, this will inspire interesting directions for more formal type theoretic exploration. For instance, Rust shows that it is possible to offer compile time checks for the third principle of isolation, even though it is not necessary for memory safety. This talk is near its end, so I would like to thank you for following it. I would also like to thank Leo White and Steven Dolan for freely sharing their thoughts and debating on this topic in the past years. Since I've got some time left, I would like to mention a couple of related works. The first one is the work by Aman and Bauer, who explain having recovered the distinction between checked and unchecked exceptions using algebraic considerations in denotational semantics, which constitutes a novel insight. In general, interpreting how semantic considerations relate to programming considerations as we developed here is hard work. For instance, a crucial question is whether the proposed finalization mechanisms are sufficiently expressive for programming at scale once the escape hatches have been taken away from the programmer. This is the main challenge in both of our approaches. Lastly, the debates about evolving exception handling models in programming languages is all the rage. For instance, with two recent proposals to evolve the error handling models of the C++ and C programming languages. I believe that being aware of the distinction and complementarity between the two methods of reasoning about exceptions can be helpful in the debates and controversies surrounding this topic beyond the OCaml and ML community. Thank you.
Thank you, Guillaume. So is there any question? I guess there's a few of them in the Q&A. So first of all, is Guillaume around and can go on stage? Otherwise, we can ask the questions, but nobody will be able to answer them. Yes, Guillaume is there. Cool. So the first...
No, you can see me.
Yeah, we can see you and we can hear you. Great, thanks. So the first question is from Edwin, which is he would like to use this memprof. I mean, your tool in a security sensitive application.
You might have a button to show the question on screen. Perfect.
Yes, do you see it?
So in a security sensitive application, so you want to avoid denial of service. Okay, that's one of the applications of resource limits to avoid DOS. Yes, you're asking for the estimation. Can it be made accurate enough? In the case of out-of-memory limits, it is accurate enough because it uses the actual size of the major heap. So there is no approximation in the estimation. In the case of out-of-memory, the probabilistic nature comes in the fact that you know that you're almost sure in the mathematical sense. So in practice you are sure that there is some check that is done at the worst case, like 8 megabytes in excess. You're really sure that a callback has been triggered. Like the probability of 10 to the minus 50 is something used by physicists for saying something that never happens. So in the graph that I showed you for allocation limits, which count time. I also provide a line corresponding to 10 to the minus 50, which would be thought of something that never happens.
Thanks. I think there's a second question from Edwin as well, which is now on the screen. So
catch-all handlers are useful in logging libraries. Yes, so this use case would need to be, it's like printing the uncut exception on the prompt. I mean, this is a use case that has to be taken into account, but it does not look very complicated to, like, you could have a function that says that just converts the exception into data without risking dropping it on the floor.
Thanks. I think I don't know if there is more question, but I have one more question that I don't know if I have to write it, which is like, is more about like the with resources function that you have. So do you have like some example of how it is used in Rust, for instance, for doing like, which kind of resources basically can you track, and like, I guess file descriptor is a good example, but is there like over like good example to that we can use in that framework?
An example of application of a read resource?
Yes.
So I gave the example of the mutex with poisoning. So the mutex is a natural resource where you want to acquire and release, but then you can create custom resources that allows you to have better invariants in your program, like recording the fact that the data is probably invalid. This is another example of a resource, and this is actually used in Coq, I think, for the hierarchy of universes to invalidate in case of Control C to, I don't know exactly how it works, but I know that this is already used. Then you have the things coming from the OS and all that.
Okay, thanks. Is there any more question? If yes, please write it on the Q&A tab. And if not, I guess we can switch to the next talk. So let's thanks again, Guillaume. Thank you for the presentation and for answering the questions. And so now I think the next talk is about continuous benchmarking.
Oh, I'm Rizzo.
Oh, and I don't know if Rizzo or Gargi are present, but they should come on stage soon, I guess. Oh, Gargi is there. Great.
Hi.
Hello, Gargi. So yeah, I will let you present the work that you're doing on continuous benchmarking for OCaml project. The stage is on you.
Today we're going to be presenting Current Bench, which is an infrastructure for continuous benchmarking of OCaml projects that we have been working on for quite some time now. So the goal of the project is to provide a scalable, predictable, and continuous infrastructure for benchmarking OCaml projects. The aim that we have is really to support benchmarking as part of the CI process of any GitHub repository that is part of the OPAM ecosystem. And we want to make it as easy as possible. So any project right now can just enable the benchmarks without any additional configuration or any setup and start benefiting from running benchmarks and kind of analyzing the historical trends in their performance over time. We started with a fairly small selection of projects and users to kind of develop the system and figure out what are some of the important features that we want to build. Specifically, we designed the system around benchmarking for the Irmin family of projects. So we have 3 projects right now from the Mirage and Irmin ecosystem, using the continuous benchmarking infrastructure. More recently, we also added support for Dune benchmarks, where people are measuring the build performance of the build system that we use in OCaml. And we're also currently integrating the project with the multi-core backend for the OCaml compiler, and we have some work in progress tooling to support running the Tezos benchmarks. But again, as I mentioned, the goal is really to get to supporting as many OCaml packages in the ecosystem as possible in the future. We have 3 different operational modes in which we can run the benchmarking infrastructure. The main one and the most interesting one for most of our users is probably number 1, which is the GitHub application. So we have actually created a GitHub application that you can go to and enable for one or multiple projects in your account. And that will essentially allow us to monitor every single pull request and commit that happens in your repository, so we can schedule and run benchmarks and collect results from those benchmarks and present them in a UI that you can explore. But in addition to that, we also created 2 supplementary operational modes that essentially allow people to focus on monitoring a single GitHub repository or even a local file system-based Git folder. So those 2 are mostly used for testing purposes or for some specialized deployments. If you want to hack on current bench, you can probably use it on your local machine with the local repository operational mode. So this is how the project looks like. We have a fairly comprehensible user interface that allows people to explore the benchmark results over time. You can see here that we're looking at the Mirage Irmin repository and specifically at one of the pull requests that was submitted. So in this picture, you can see all of the different metrics that were recorded as part of the execution of the benchmarks. You see the latest value from the specific pull request, the equivalent value on the master branch, and also the deviation from master. The graphs also include computation for standard deviation and include error bars so that it's much easier to track outliers throughout the history of the benchmarks execution. The project is actually live and deployed at autumn.ocamllabs.io. We'll change that at some point, but for now you can go there and explore the UI, see how it looks like, and just get a feel for it. At the back end of this platform is actually powered by OCurrent, which is a super handy and useful library that allows us to essentially keep things up to date and monitor all of the sources for changes. Specifically, we, as I mentioned in the beginning, connect to the GitHub API, and we monitor that API for changes. And whenever there's a new pull request or a new commit, our current backend, which we also call a pipeline, will detect those changes and trigger an execution of a bunch of computations that are required to get the information about the pull request, understand how to execute it, build Docker images and execute those Docker images to actually record the results and store them in the database. To tell you how the project actually works on the inside, I'm going to hand it over to Gargi, who's going to tell you all about it.
Hi, everyone. So as Reza mentioned, I'm going to talk about the internals of current bench. So this is what the infrastructure looks like. We have an OCurrent pipeline. We store the results in a database that the front end queries over the GraphQL interface and then puts it on a website for the user to see. When you open a new PR, the first thing that happens is a webhook event is triggered that the pipeline receives. The pipeline then goes and looks for a make bench target in your project and runs the benchmarks inside a Docker container. We've done a bunch of optimizations to ensure that there's no noise when we run the benchmarks that I'll talk about later. once the benchmarks finish running, the pipeline puts it in a database and updates the status on the GitHub PR. So once the benchmarks finish running, the PR status on the GitHub pull request is updated, and you can go click on it and look at the results in the dashboard. The benchmark results is just a simple time series result, which we store in the Postgres database. So it has a bunch of information about when it's run and the commit and branch and pull request information. And you can have multiple benchmarks in the same repository. And we support having multiple benchmarks in your repository, and those benchmarks can have the same test name. That's okay. And all the metrics we store inside a JSON that the front end then uses. So the hardware optimizations that we do is that we pin the benchmark to a single CPU. So at any point of time, we're only using a single core, and the benchmarks are scheduled. So we run one benchmark at one time, so there's no noise that can fudge the numbers. For I/O performance, we have a TempFS partition, and we pin the TempFS volume to a specific NUMA node, and we disable the address-based randomization so that it doesn't introduce any noise. This is the work that Tom Kelly and Sadiq did for OCaml multi-core benchmarks, but they run the benchmarks natively, and we run them inside a Docker. If you want to enroll your project, it's super simple. You go to OCaml benchmarks GitHub app on the GitHub Marketplace. You need to have a make bench target in your repository, and you need to produce a JSON that is compatible with current bench. So you just have the name of the benchmark and the results. And you can have multiples of these JSONs for like different kinds of benchmarks you have in your project. And yeah, that's it. In the future, we want to have a bunch of improvements. So we want to allow users to query data using GraphQL, so that if they want to play around with the data, know something more, or have graphs that we don't support, they can do that. And allow custom Docker files. So if your benchmarks need pinning of a certain OPAM package, or want to get some data from somewhere and other things, we want to allow the users to do that also. And allow the capability for fast and slow benchmarks. So maybe on your pull request, you need faster feedback. So you want to run benchmarks that can finish fast. But you also want to run other benchmarks that you care about, just not for the pull request. So maybe you want to run them nightly or weekly. So we want to be able to support that, and we want to provide detailed stats. And basically, our grand vision for the future is to have continuous benchmarks for all OPAM projects, which is a challenging and a very interesting problem to solve, given that we only run benchmarks on one core at the moment. So scaling is something that we're looking to do, and very excited to face the challenge and look into how we can do that. And that's it. And we'd like to acknowledge all of these people who contributed to Current Bench and got us here. And that's it. Thank you so much.
Thank you.
Bye.
Thank you, Gargi. Thank you, Rizzo. I think Gargi just disappeared, so if someone can put her on stage again, that would be nice. Gary, can you hear us?
Yes, I'm back. Sorry.
No worries. So I think the first question is from Peter. Do you have a way of calibrating for different runner architectures?
What do you mean by runner architectures?
I guess so I'm not Peter, so I cannot exactly say. But is there a way to maybe have to limit the CPU, to know which kind of CPU you want to run on, or like the RAM that you can use? It's also
Yeah.
the benchmarks. Okay.
Yeah, I think eventually that's what we want to do. Yeah, that we can have different non-homogeneous architectures and run benchmarks across all the different architectures and compare them as well. But we don't have a way to do that right now. But this is something that we want to do also.
Okay. Then the next question is from Armel, who is asking for how to declare code to run Anton benchmark. I think.
So basically, you will define your own benchmarks. The only thing that we do is run them for you. So as long as you have a make target in your repository that specifies the benchmarks that you run, that's all we need. So like what actually gets measured is what you want to measure for your code. Like we can't know what benchmarks to run for project because we haven't worked on the project, so we wouldn't know what to measure. So that's something you would have to do. But what we'll measure is whatever you want to measure. So for example, if you want to measure how much time a specific function is taking, that you can have in the benchmarks, and then we'll measure that.
Thanks. The next question is from Edwin. So so what kind of thing do you disable for the benchmark, basically?
Sorry, I'm just reading the question. Do you disable CPU turbo boosting or monitor actual CPU frequency based on a perf and perf? I think we just disable the CPU turbo boosting, but don't monitor the CPU frequency. Yeah.
Thanks. And then the next question is from Xavier, who wants to apply that to the OCaml compiler. I'm not sure that's a question, but
yeah, as long as we have benchmarks in the OCaml compiler, we can do this for the compiler also. Yeah, that would be very cool.
And Florian has another question as well related to the OCaml compiler. So I think there are some interest here, which asks how well the current architecture works with IT multidimensional data.
Sorry, I'm just, again, looking at the question.
Yeah, no worries.
I am not sure what is meant by multi-dimensional data.
I think Gabriel said that it's like a lot of numbers, like if a very large JSON file, for instance.
I see. Yeah, I think the current architecture won't scale. So one of the things that we do want to do is provide run the benchmarks for you, but then provide it as data for in like a Jupyter notebook, or provide a data endpoint that you can use to have whatever graphs you'd like to have, in case we can't support the graphs that you would want. Because that would be, I think, more straightforward. But we also eventually plan on supporting more different kinds of graphs.
And probably you can as well aggregate the data before generating the file. I think you have some typed field where you can precise values and errors, and so you can show them on the graph, but you have to pre-process them before.
Yeah, we could also do that, yes.
So I got one more question for me, which is like I'm just curious about what is the experience with the feedback loop when you develop that stuff? Is it like do you have like feedback from developers saying that it's useful for them, or like integrating that as on a pull request? Does it make a difference in your experience?
Sorry, can you say that again?
Sorry. So what is your experience from the developers and of point of view of using that kind of system? Do you, like, in practice, do you see that people are relying on that, or is it something that seems to be useful?
Yeah, I think you can also answer for that, Thomas, since Erwin family of projects is using it. But when you're building something that's performance critical, I think you care more about the numbers versus not. So I think in those times it could be useful to look at those numbers and have a handy way of doing it rather than having to do it yourself every time.
And yeah, so in my experience, it's like it's clearly like it's very useful to see like regression when they appear. Like sometimes you don't really expect like a simple change to completely change the performance metrics of your application, and then just having this kind of early feedback is very helpful for that. Any other question on the Q&A? I see there's a lot of activity about how to do that for the compiler, so probably we'll something to work on is to add the compiler to the suite very soon. Great, thank you again, Gargi.
Thank you.
Let's thank you again by sending your emoticon. I think the next talk is about the two next talk are about documentation. So I don't know if John or Lucas are around to answer the first question, but they will both present their like a system to build documentation for OCaml packages on a very large scale, and that should be the next. Oh, John is around, but there is no slides. I think they will be arriving soon. And no, there's the slides. Perfect.
My name's John Ludlam, and I'll be giving our talk entitled A Multiverse of Glorious Documentation, written by Lucas Pluvinage and myself. Those of you that were here last year may remember I gave a talk about ODoc entitled The Final Piece of the Documentation Puzzle. Now you might notice that I'm back with more documentation work, so you might reasonably think that perhaps last year's title was maybe a little premature. The difference this year, however, is that I want to expand our scope. We were less ambitious last year. We only looked at documenting a single library. This year, I want to document every single library I've ever seen, and all the libraries I've never seen too, and even every version of all of those libraries. And I'm going to tell you how to combine all of those library documents into not just a glorious universe of documents, but an entire multiverse. Let's go. As usual, we start with the goals. We're looking at the OPAM repository, and we want to produce documentation for each of the versions of the packages in there. This amounts to just short of 20,000 versions as of today. A lot of packages, to be sure, but not insurmountable. In fact, we actually end up documenting a few more than that, and I'll discuss the reasons why this is the case in a bit. Additionally, we'd like this to be an automated process, so we can just let it get on with things and not worry about it. I don't particularly want to have to schedule a weekly update the docs slot into my Monday mornings. Even better, let's have it such that any time a new package or version is merged into opamrepository.git, we'll build docs for it. And while we're at it, let's have it quickly. Let's aim for about 10 minutes and see how we do. And if the server we're running on it dies a horrible death, we need to be able to start it all up again without too many tears. And finally, let's make it a useful basis for future work. Okay, so now we know what we want. How are we going to do it? Well, no surprises here given my talk last year. We're going to use ODoc. It's the only tool in the game, really. The trouble is that the way ODoc works is that it requires a consistent set of packages that are all co-installable, or more accurately, co-typable. To understand why, see my talk from last year. So that rules out having more than one version of a package. What we're going to do then is build the documents separately into some carefully defined file tree, and then union the trees together into one set of docs. Happily, ODoc 2.0 supports rendering HTML into an arbitrary file structure, so we're good to go. Our next decision is therefore exactly what file layout will we use. Well, the most obvious answer is just to stick the HTML docs into a file structure based on the package name and version. Is this sufficient? Sadly, no, it's not. The fact is that the interface exposed by a package is dependent not only on the package itself, but on the exact versions of its dependencies. Consider, for example, a package that exposes a set created from the functor in the standard library, specialized in this case so that the type t is equal to myType. In this signature, the function filterMap has only been included since OCaml 4.11, so if you build this exact package against 4.10, it would not contain that value. Obviously, the standard library is not unique in this, so it's entirely possible for the interface of a package to change if you change the version of any of its dependencies. Consequently, in order for the cross-referencing to be exact and correct, we need to identify a particular set of docs for a package not just by the package name and version, but by the triple of package name, package version, and universe ID, the last of which we define as a hash dependent on the package's version's dependencies. The next question, can we get away with only ever compiling each version of each package against one set of dependencies? It would be convenient, but this turns out not to be possible. Take the example of findlib. Virtually all packages depend upon findlib, and with no constraint, meaning OPAM will pick the latest compatible version. However, many packages have constraints on the version of OCaml, so we end up compiling the latest version of findlib against many different versions of the compiler. Consequently, for some packages, we necessarily need to produce documentation for the same version for each different universe in which it's needed. Since these may be different, we need to ensure that these are put in different paths. So the most obvious way to do this is to use the universe ID as part of the path. So something like /packages /universe ID /package name /package version. While this scheme is correct, it doesn't lead to particularly discoverable, pleasant, or easy to remember URLs. To fix this, what we do is pick one particular universe to be the representative for each version of each package. I'll describe later the exact mechanism we use for this at the moment, but the important thing is that this gives us a way to have a nice discoverable and easy to use URL for each package version, while retaining the correctness that every link can be guaranteed to go to the destination that the package was actually compiled against. We call the chosen representative universe the blessed universe. We use OCurrent to build an incremental pipeline to build the docs. So this is the same system that's being used for CI systems such as OCaml CI. It's designed to watch Git repositories for updates and respond by submitting jobs to a cluster for execution. It's got some really nice caching built in that works really well, though it's not quite capable enough today to match our needs, so we've built a bit more of a stateful pipeline. Not only that, but since the artifacts we work with are quite large, we store them on an external file system, and that in itself is a stateful part, so we really have two states to keep in sync. OCurrent encourages incremental builds, so that even when the build graph changes, for example, when a new package or version is committed into OPAM repository, it only rebuilds the new artifacts required. It does this by defining a key value pair for each step in the build process. It then memorizes the results, so if it's already calculated the value associated with the key or keys, it just returns the previous calculated result. Let's take a look in more detail at some of these individual parts. The solver's job is, for each package and version we're tracking, to run an OPAM solver to find the precise set of packages required to install it. The inputs, the key, is the commit hash of OPAM repository, and the list of the packages we're interested in, and the resulting value is the list of solutions. We do keep some additional state, the list of previously solved packages, so that when the input changes, which is most often a new commit on OCaml repository, we can decide whether our previous solutions are still valid. Right now, if we have a cached version, we'll always reuse it, but we'll likely adjust this in the future. There are a variety of circumstances under which we'll want to resolve. For example, we'll almost certainly want to resolve for everything when a new compiler is released, as in many cases the solutions will change to use this newly released compiler. Possibly we'll also want to resolve just on a regular cadence to ensure our solutions are reasonably up to date. We do not insist on installing the optional dependencies where they exist, as it's perfectly possible for optional dependencies to be mutually exclusive, or for some broken packages for the optional dependencies to cause the build to fail. To some extent, we do make up for this in the blessing step. Once we've got a solution, the next step is to install it. The pipeline takes care of choosing a base Docker image to use with an appropriate compiler version, then invokes OPAM to install the packages. It runs the tool voodoo prep to find the files within the OPAM folder that are necessary to produce the docs. Mostly this is the CMTI, CMT and CMI files that ODoc requires, but we also pull out a few more files. Any package docs installed, Dune package files for a bit of metadata, and some info from some of the CMA files if Dune package doesn't exist. These files are then tarred up and pushed to the external file system and the hash calculated. The hash is the value of this part of the pipeline. When we've got the complete builds, we can choose which universes to be blessed. We do this by picking a universe with the most dependencies. Doing this means that when we've got a successful build with some of a package's optional dependencies, which occurs when a dependent package has a non-optional dependency, then the blessed universe will have the docs for the package's optional libraries. When a tiebreaker is needed, we simply count the number of dependent universes and choose the universe that's included in more of our other universes. Once we have the artifacts extracted from the OPAM directory, the next step is to perform the ODoc compile and link steps. These are roughly analogous to the usual compile and link steps. To compile the docs, we require the results of compiling all of the dependencies, hence this forms part of the key of this step. Furthermore, this is the first step in which ODoc is actually required, and since we're using an unreleased version of ODoc right now, we track the commit ID here too. For more details on this step, see last year's talk again. The result of this is the linked version of the docs that can then be converted to a variety of output formats. Here's a section of the compilation pipeline showing the pipeline stages in this compilation step following the dependency ordering of the packages. So you can see LWT depending on OCaml syntax shims and Dune configurator and mmap and so forth, and then subsequently cstruct LWT depending on that, and also cstruct and so on. The separation of the HTML generation step is done largely to ensure that we can rerun this quickly as the desired output changes. To rerun this step over all universes only takes about 90 minutes at the moment. We have a slightly altered HTML generation step than ODoc usually has, which has allowed the integration of the docs into other sites easily, in particular, of course, v3.ocaml.org. This HTML generation tool is currently being prototyped in the Voodoo suite of tools, but it's likely we'll fold it back into ODoc once we decide on the most useful output format. As with all live systems, we need to have a policy on how updates are handled. In general, the updates are either breaking changes or non-breaking changes. As an example of a non-breaking change, we might have a new package put into OPAM repository. This could be done simply by inserting the new set of HTML files into the appropriate place in the unioned file system. A breaking change is anything that might cause links to break or the downstream consumers to break. For example, if we change the layout of the metadata consumed by the v3.ocaml.org server, we might wish to do that atomically across all packages rather than just incrementally. For these sorts of changes, we have what we call an epoch symlink on the server. When the build is completely finished, we simply flip the symlink and atomically switch from one set of metadata to the new set. Some stats on where we currently are. We produce about 50 gigs of HTML files in total. This is across about 3,300 packages and about 17,400 versions. And about 2K are actual installation failures, so where the build has failed at the time we try and do the OPAM install. We have 18,600 versions living in parallel universes and producing 3.3 million documentation pages. The package that has the largest number of parallel universes is actually logs, which occurs when logs 0.7.0, which occurs in 209 different universes. The total build time across the OCaml Labs cluster, when the cluster is not being particularly used, is about 6 hours. So it doesn't take a huge amount of time, but we have quite a lot of machines there. We have plenty of work left to do. As I mentioned before, we've set up the pipeline to store its artifacts externally, and this is done in a fairly naive way, and there are plenty of opportunities to improve this. Additionally, or alternatively, we might invest in embedding the idea of a data pipeline more directly in OCurrent. We've already got a public API of sorts in place where the documentation generated by the pipeline can be consumed by the v3.caml.org server and rendered nicely as part of the new OCaml website. But it would be interesting to think about more other uses of this. For example, we might want to embed the output in the Visual Studio Code plugin in some form, or we might be able to use the data we're generating in alternative ways. For example, some sort of search. We've not done a lot yet on comparing the documentation in different universes. While it's certainly theoretically different, it would be really useful and informative to understand how different it actually can be in practice. And while we're considering comparing the output, it would also be really useful to be able to show the diffs between different versions of a package. Although since they may be compiled against different dependencies, we'd again need to carefully consider what the source of the differences is. In short, there remains much work to be done. So, thank you very much to our colleagues at OCaml Labs and at Terides, in particular Jules Aguillon, Lubega Simon, Patrick Ferris and Thibaut Mathieu, to the rest of the ODOC team and to Jane Street for their financial support. And thank you all for your attention.
Thank you, John. I think Lucas on stage as well. So is there any, and I think there's some question in the attendee as well. So first question is Edwin, who is saying that it would be cool if we could auto-diff libraries APIs and show AdSense annotation. Do you see any challenges to do that?
So I think the main challenge there is to figure out where, as I said, where the changes come from, because it's quite possible that the changes, because we're compiling each different version against a different set of dependencies, the diffs in the libraries could come from different sources. But other than that, I think that's probably fairly unlikely. I think there's no particular challenges in this. I think we could do quite a nice display of showing like new values that have appeared, types that have changed, and all that sort of stuff.
Thanks. Any other question? Oh, Xavier has a question as well. So, yeah. So, what kind of file do you need to make that work? Do you want CMTI? Do you need more file?
So mainly it's the CMTIs if they exist. If the CMTIs don't exist, we go for the CMTs, and if they don't exist, we look at the CMIs. And then there are of course the other more metadata-y type things. So that there's the Dune package, which that's how we figure out which modules appear in which different library. And MLD files, if they exist, we'll use them. I think that's most of it, I think. Yep.
Thanks. Next, we have Kenichi has a question about different languages. So is it possible to support like a document with, well, or do you plan to support multiple languages in the documentation basically? And do you think about that?
I think this is a really good question, and I'm not sure we've got a good solution for this yet. MLD, we could produce different MLD files for those documentation pages in each different language. That would be fairly straightforward. But for what appears in the actual the module interface documentation, that's going to be a bit more tricky. So I think we need to think quite carefully about that, because that's definitely clearly something that we should try and address.
Thanks. So I have one question, but feel free to ask more questions in the Q&A, please. So my question is more about I heard that there are some secret JavaScript top level embedding stuff the plan, and so can you tell us about that a bit more? Are you muted?
Yeah. Yes, that would be brilliant to have JavaScript top levels for each of these libraries. So we've had a bit of a play with this sort of thing, yes, that would be really neat. It's on the list of things to do. I don't think it'd be that hard to do, hopefully, and I hope that many packages it will just work for. But we'll need to actually try it at scale to see how well it actually does work.
So what are the challenges exactly for that? Like...
C bindings mainly. So of course we're just using JS over OCaml. So anything with C bindings for which we haven't got equivalent JavaScript implementations, that's always going to be a problem there. But many packages should work fine, hopefully.
Cool, thanks. More questions in the chat? Let me check. And so maybe you mentioned like v3.ocaml.org, and I think Anil added the link to the chat. So it's v3.ocaml.org/packages, and so is like, do you want people to start using it, or is it something which is still a work in progress? What is the status of that link right now?
Yes, I think we can. People can start looking at this. Certainly, we're very keen for contributions and feedback. So our portion of the v3.ocaml.org is just in the /packages hierarchy. But yeah, it's all live now. You can go and have a look and see how it seems. We've already got a bunch of issues that we know we need to fix. It's certainly a work in progress. So there's the repositories are on the OCaml GitHub organization. So that's the best place to have for the feedback to be there.
Thanks. And I think we have a last question from Edwin, who is asking if you have any recommendation for package authors to make their docs better fit together, or do you have any particular doc features that you recommend to use?
So I think we need to write up some recommendations for this. We don't have anything really in place at the moment beyond the usual OCaml doc recommendations, but because of this, the existence of this now, I am hopeful that people will work on the documentation of their packages more, as you sort of see the live updates. And so obviously as people work on it, that's when we'll get more interesting features to feature suggestions to implement to make things work better. But right now we don't have really any specific recommendations beyond the usual OCaml doc section in the compiler manual.
Okay, thank you. I think we are just on time for the next talk. So thank you again for the presentation, and I hope people will write more documentation now. And especially since we have a second talk on documentation, so I'm sure like people are very interested by documentation. So that's a good proof of that. And so the next talk will be about Digodoc and docs by Mohamed, Fabrice, and Thomas and Louis.
Welcome to this talk.
And I guess so. We can do the talk, and then at the end, I don't know if Mohamed is around or who is going on stage, but just let me know, or let us know in the chat at the end. So let's learn to Mohamed now.
On Digodoc and docs. My name is Mohamed Ernov, and I will present you our work done by OCaml Pro team and explain how we built our OCaml documentation hub using Digodoc. As you all know, OCaml programming language is surrounded by a very rich ecosystem, which consists of many thousands of packages, which in turn include a lot of modules and libraries, starting from modelized algebraic data structure, ending with web server skeletons. In such ecosystem, developers could find every kind of package that helps to build a solid, efficient, and large-scale projects. Package developers usually provide documentation for their package in order to use correctly its functionalities. Such documentation almost always consists of a set of static HTML pages. Each page lists types and functions inside the module for a given package. The set of HTML pages is generated automatically by existing tools called documentation tools like ODoc and OCamlDoc. Those tools read modules binary files and generate page that exposes commented interface for a given module. Despite all this, today's ecosystem is facing some problems. Firstly, documentation tools are quite limited by single binary file. For example, ODoc cannot find by itself locations of binary files referenced inside a specific module, which means that we should manually call ODoc for each module and for each dependency specify paths to its documentation that should be already generated. All that is almost impossible for a large number of packages. The second issue is the fact that there are multiple notions of projects in OCaml ecosystem. That implies that there are different ways to choose which notion will the documentation be based on. It's either the notion of libraries as a set of modules used by OCaml compiler, either the notion of project with metadata used by Dune, either the notion of packages used by OPAM. Nowadays, there are tools in ecosystem considering just one notion, but not the others. And third, the biggest issue that is implied by two issues mentioned before is that there isn't a single place where a developer could find the documentation of all the packages, libraries, modules he might want to use. Instead, he should search it on multiple sites and platforms. Usually documentation of a package resides on an official website of a maintainer company or, at the very least, on GitHub homepage. Sometimes, as you know, it could be really complicated to find what you want through all the decentralized system, especially for OCaml newcomers. That often makes them difficult to explore OCaml's ecosystem, and even sometimes that demotivates them. And finally, they give preference to other languages more suitable for ecosystem exploration, to other languages that unite every kind of information they may need in one single place. Afterwards, today we have a pleasure to introduce you Digodoc, powerful tool that scans an OPAM switch and creates a graph associating modules to libraries and projects to packages, and then computes dependencies between all of them. Later, this graph is used for full and incremental generation of packages, modules, libraries, and projects documentation with ODoc. That helps to solve first two issues, in addition to the fact that it provides GitHub-like source explorer with syntax highlighting for OCaml files. Applying Digodoc's functionalities on an OPAM switch with more than 2,100 packages gives us OCaml documentation hub, which for its part solves nicely third issue, and in the long term could be improved by covering all the packages in OPAM repository. The given site was entirely generated by Digodoc, with all its indexation pages, allowing to find and to access easily the entry we want, only by its name. Site is actually active under the mentioned link. A large part of work done and of work that will be done for the site was inspired by counterparts from other languages such as Hackage for Haskell and Crates for Rust. And now let's move to the details. The first step we had to make was creation of switch, which is large enough to contain most of existing packages. OPAM is a package manager that uses dependency solvers for its package. Besides built-in solver, OPAM also might communicate with external solvers through CUDF format. In our case, we used external solver named SPQt. OPAM's user could customize solver with what we call preferences or criteria. In our case, we needed to install as much as possible new packages while trying to install the most recent versions. And this is done by criteria specified in the slide. Additionally, we should specify some entry points for solver, and finally we obtain our switch with more than 2000 packages. All work done by Digodoc could be divided to 3 large stages. Each of them will be considered later. It should be noted that each stage depends on previous and couldn't be executed out of context. For example, docs generation needs computed data about every package and full graph of dependency, as well as indexation needs fully generated set of documentations. Throughout the execution, Digodoc deals with 4 main data structures. For each of them, he extracts all types of information we need during the first stage. For each, he generates documentation during the second stage, and for each, he creates a standalone index page. Switch exploring starts with scanning all the .changes files located in the same place. Every package has his own .changes, where we can find paths to all associated to him files, starting from compiled modules and libraries and ending with license and README files. Then, for every package, we handle all its associated files in order to extract all required information and in order to create corresponding data structure. OCaml binary files are firstly handled by OCaml objinfo that helps to get output that could subsequently be parsed. Parsing has a goal to initialize corresponding data structures and especially to get its hash code and hash of its dependencies. Later that will help to build graph of dependencies between the modules. Digodoc provides a library that parses meta files and extracts all type of information like description, version, meta dependencies, included metas, but also existing archives that represent either a library, either a module with the same name. All that information initializes meta entry at meta entry's data structure. The .mld and .md are separately saved and used afterwards during the doc generation. And the last stage of switch exploring consists to read information from OPAM file that helps to fill OPAM entry, which was initialized during the first stage. Subsequently, same file is used to compute dependencies between packages. Upon switch exploration, Digodoc has computed state of data structure and has information about belonging of those structures to the various packages. But despite all of that, this is still not enough to generate full documentation. So he proceeds to compute all type of dependencies, inclusions and associations between those data structures. Firstly, he computes dependencies between OPAM entries, basing on information extracted from OPAM files. Since packages' names are unique, we could easily find the OPAM entry we want, knowing his name. For this purpose, Digodok holds in his state global map of package, grouped by their name. Then he computes dependencies between meta entries by extracting desired information from meta files. Here he acts in the same way as with packages. Meta name is unique, and the corresponding meta entry could be get from a global map. Later he determines which module entries are included inside a library entry. At the moment of reading of library's binary file, OCaml Objinfo exposes all exported units. We could get module entry we want by comparing his name with units1 in the same package. Then he associates meta entry to all its library entries by looking up archive fields inside meta file. Archive name corresponds to library name inside the same package, or inside the package of its meta dependency. And finally, he computes dependencies between all module entries. A module specify hash of all used external modules inside binary file read by OCaml Objinfo. Then corresponding entry could be found in global hash table, filled progressively during switch exploration. Like that, Digodok moves to the next documentation stage. At the very beginning, we generate documentation for module entry, because later they are referenced by other entries. So this is how it looks like. Since the algorithm strictly follows an order imposed by graph, all dependencies should be already generated. For other entries, documentation is generated by a quite different way. At first, all available information is transmitted to MLD page constructor, which builds a skeleton of future page, separates info by sections, and creates .mld file. That file is then compiled and transformed to HTML page. Also, Digodok generates separated pages for all .md and .mld files attached to entry. Additionally, Digodok generates Explorer for sources of OPAM packages that helps to navigate easily inside source arborescence. To do that, firstly he gets package directory with OPAM source. Then he iterates over the directory and reads the file's content. During generation of HTML pages, OCaml source files are parsed in order to generate highlighted page. Actually, we are working on expansion of the list of supported files. After documentation stage, Digodok passes to the last indexation stage that helps to create full cartography of the site and adds search functionalities. At the end of docs generation, Digodok sends requests to specific API server that iterate over the set of documentation pages and fills database of entries. Then he generates an index page for each type of entry, which uses JS of OCaml frontend. This frontend part is in turn communicate with another API server that deals with entry search in database. So that was a short overview to Digodok. Since this project has inexhaustible perspectives, we are still working on it. Right now we are working on improvement of Sources Explorer that will allow us to find out a type of a variable inside ML files and also to navigate between definitions. Also, we are working on extensions of search functionalities that grants possibility to customize the search and to find functions with specific name or specific type. And finally, in the long term, we want to document not only a precise version of a package imposed by switch, but also another versions. And on that note, I want to thank you for your attention.
Thank you, Mohamed. So is there any question? If not, I have a few of them. So first of all, are you around, Mohamed? Can you hear me? Yes. We can't hear you. Mohamed, are you here? Let me try to ping you. Right, is someone else can answer the question maybe in the audience who's around? Fabrice or Thomas or Luis? Right, well. Am I the only one not hearing Mohamed or? Oh, okay. Stephen, do you want to answer questions? Adam. I can see you, but I cannot hear you. Maybe you want to answer by chat. So the first question is from Gabriel, who is saying that he used docs.ocaml Pro a couple of times, and he found it quite useful, and he say thanks. And I think it's useful to post URLs to point other people to docs too as well. So I think it's more like it's not a question, it's more like a comment. And yeah, clearly, like it's a very useful website to have for the community. So then a question from Anil, we're saying that the source browser is very nice, and he's wondering how reusable components as a component is it? Can we integrate it with IDs? Can we add it to the VS Code plugin? I think Louis, you joined, but it's you're on mute. So.
Yes, well, I'll let the others answer because I didn't actually work on this. If they can.
Maybe you can reply by on the chat. I don't know. And I think the question in general to reuse components as a library, I think could make sense. So and I think I'm wondering as well how is it split into libraries? Is it easy to reuse some of them? And as you can all speak, my answer would be unanswered, I guess. Do you want to? Oh. Okay, so Mohamed said that the library is done for the HTML part, but the digidoc base info are easy to repurpose. Okay, thanks. Yeah, it's like a bit unfortunate that the mic is not working. So probably we can just stop here. And thanks you again for the presentation. And we can continue.
Can you hear me?
Yes.
You can.
Well, you can answer your question now if you want, but I think it's we are like.
I don't know how to configure our sound. Sorry about the delay.
No worries.
So are there still questions to reply to?
Well, I think it's I think two questions about the reusability of libraries, because I think that's part which could be very useful for our project, like the browsing of like using the HTML browsing for source code, for instance, or converting the meta or like all the metadata into Markdown as well could be like interesting.
Okay.
It will be very cool future. Like we will have a plan to link VS Code with docs generation. It will be possible when we will like have a link between sources and modules documentation, because now we have two two separated parts, like docs and sources. And the moment when when we will link them, it will be in the next step. It will be to integrate HTML pages in VS Code.
Okay, thanks. And maybe like a last question, as you can answer them now. So it's more for I have a question about the incrementality of the process. So I'm just like wondering how long it takes, for instance, to build a full switch from scratch, like the 2,000 packages that you describe. Or how long does it take to generate the documentation for them?
If I understood well your question, it was how much does it take this time?
Yes, and if something a little bit, and if you have a new package coming in the system, do you have to rebuild everything as well? Like,
for sources, we can rebuild just using DigoDoc special option. Like we can build Explorer for one packages, one source package. But for docs, like we need to have a graph, so it means that we need to rebuild documentation. And with the server, it takes like 2-3 hours without sources part.
Okay, thanks.
On a single server, right?
On a single server, on a switch that's bigger than you can ever use.
In open bin that would share binary packages.
But we have plans to make it more incremental too, but right now we are focused mostly on features.
Okay, thanks. Any more questions in the chat? I think in that case we are a bit late on the schedule, so thanks again for the presentation. And I hope everyone is writing documentation now because we start to have like nice website to show them. So let's write more documentation.
Thank you.
Thanks.
Thanks.
So greetings, everyone. Welcome to the keynote session for the OCaml workshop. My name is Anil Madhavapeti. I'm from the University of Cambridge. And I have the easiest job for this workshop because I have to introduce the one person that needs no introduction, Xavier Leroy. So Xavier Leroy, I'm going to introduce him anyway. Xavier Leroy is the chair of software sciences at the Collège de France since 2018. And before that was a researcher at INRIA, where he wrote the OCaml compiler in 1996. Since then, Professor Leroy has been leading the OCaml project for the past 25 years. And because it was OCaml's 25th birthday earlier this year, has kindly accepted our invitation to give a keynote on reflecting on the entire history of OCaml since then. So it is my pleasure to welcome Xavier to present this, and I encourage people to leave questions in the Q&A tab so that we can have plenty of discussion afterwards as well about what the next 25 years of OCaml brings. So Xavier, please go ahead and begin the talk.
Hello, and welcome to this talk on 25 years of OCaml, including a short history of camel logos. The reason for this talk is this announcement that I sent 25 years ago in May 96, announcing the availability of Objective-Camel version 1.00, which was the latest version of the OCaml language, the camel language at that time. And to celebrate this and to reflect on what happened since, the OCaml workshop organizers invited me to give this prospective talk, and it's my great pleasure to do so. Actually, the story starts well before 1996. Let me move back 25 more years back and to the early 1970s and talk about the work of Robin Milner, perhaps the most inventive computer scientist I have ever met. So in 1971, 1972, Milner was working on an interactive prover for a logic, LCF, the logic of computable functions. And the prover would work this way. Users would write proofs as terms, little programs of type THM, meaning theorem or proposition that is valid. And THMs would be built using functions that reflect inference rules of the logic. For instance, this is the inference rules for transitivity of equality. Trans T1, T2 checks that T1 proves A equals B, and T2 proves B equals C, and then it returns a theorem saying that A equals C has been proved, otherwise it would fail. And to write these terms, Milner wanted a meta-language that was applicative, functional, interactive with a real print loop, and strongly typed to enforce type abstraction on type THM. It is crucial that the only THMs that can be manipulated are those built from the axioms and the inference rules of the logic. The user must not be able to claim 0 equals 1 is a theorem, for instance. So, of course, Milner was using Lisp, like everyone in artificial intelligence and theorem proving at that time, but Lisp would not do because it doesn't let you define abstract types. Hence, Milner invented ML, a functional and imperative language with strong static typing and type abstraction. And Milner also wanted the types to not get in the way, and that users should write programs pretty much like they would write them in Lisp without type annotations. So he studied type inference and noticed that type of function parameters can be inferred from their uses. Here, for instance, in this function, it's obvious that x and y are booleans because that's how they are used. But what if types of function parameters cannot be inferred, as in funx or x, where the use of x doesn't tell us anything about the type of x? Earlier work by Hindley, a logician, for the simply type lambda calculus would lead to giving type alpha or alpha for some fixed unknown type alpha. And Milner noticed that this function identity could be given a type schema for all alpha, alpha or alpha, that denotes a polymorphic function that can be used at several different types. So that was really the beginning of ML. But one thing was still missing, which is support for user-defined data structures. So in LCFML, there are built-in product types and some types, but all other data types are defined as abstract types plus constructor functions plus accessor functions. For instance, here we have binary trees with values of type star that leaves. So a tree is either a star or a pair of two star trees. And it has constructor functions, leaf and node, the predicate is leaf, and projection functions, leaf val, left child, right child, that can all fail at runtime. And it's only at the in the very early 80s that inductive types and pattern matching were added to LCFML. Various work by Burstall, McQueen, Milner in Edinburgh, and Guy Cousineau in Paris, with some inspiration from Hope, an experimental language of Burstall, and perhaps also from Prolog. And so we went, at that time, they went from typed Lisp, that you can see on the left, to OCaml with a data type definition and a function defined by pattern matching over the tree. And so that gave OCaml as we know it today. So this very nice combination of a call by value functional language, inductive types with pattern matching, and Hindley-Milner polymorphic types and type inference. And from that initial design emerged an incredible number of languages. It was kind of the primordial soup, okay, from which emerged at least 3 lines of functional type functional languages. The one was standard ML, so led by Milner at Edinburgh, and moving towards standardization and formal definition, but also adding modules. We will talk about that later. Another one was a pure functional programming line of work with early languages like Miranda and LazyML, and a convergence around Haskell in around 1992. And the third one is the OCaml branch, the French branch, if you want, which we are going to talk more about today. So what about this OCaml language? So that was the result of the work by Guy Cousineau and Gérard Huet at INRIA and University Paris 7 and later at INS in the early 80s, later joined by Michel Moni, Skander Suarez, Pierre Weiss. Basically, it was OCaml plus facilities for embedded languages like parsers, quotations, and type quotations, kind of thing we do with CamelP4 or CamelP5 these days. You can see at the bottom of the slide a bit of OCaml code. Well, it should look pretty familiar to you. Well, there's a where-rec construct that we no longer have. Constructors have quotes, and at the bottom you see the use of quotations and anti-quotations to use a concrete syntax for plus and for addition and multiplication, your little language of expressions, as patterns. So it was developed along the Coq proof assistant, basically at Coq's implementation language. So in the early 80s, Gérard Huet decided that the calculus of constructions would be implemented not in Lisp, as his previous project, but in a language with more types. And so he chose ML for that. But what gives OCaml its name is actually its implementation technology. So it's ML running on the CAM. And so it was implemented on top of a Lisp runtime system, the LeLisp system, and its LLM3 virtual machine. But it would not, unlike earlier ML implementations, it would not translate to Lisp and then compile the generated Lisp. It would compile through an intermediate language based on the CAM, the Categorical Abstract Machine, which was worked by Guy Cousineau, Pierre-Louis Curien, Michel Moni. A simple evaluation model for call by value inspired by Cartesian closed categories. Categories where products and function spaces are dual. And so, well, I've written the basic compilation scheme below, which is how code that takes the environment at the top of the stack and leaves the value of the expression at the top of the stack. And what is notable about the CAM is that it was one of the first formalizations and formal discourse about function closures. Before, function closures were well known, but just as an implementation device for functions as first-class values. Here they were kind of connected with a bit of a theory, and that was very interesting. What was disappointing with OCaml is a lack of performance. Each binding, each let binding, each function parameter being passed to a function would result in a const, in a heap allocated const cell, and the environment would have the structure of a list, so no constant time access. And it's about at that time that I hear about CAML for the first time. So I was a student at ENS, and Guy Cousineau was one of my professors. And one day I went to see him to discuss internship possibilities, and told him I would be interested in an internship in systems or maybe compilers. And he told me, je connais un langage où il y a un gros travail de compilation à faire. Let me tell you about a programming language where there is much compilation work to do. And then he proceeded to demonstrate CAML on the big screen of his Sun workstation. And I was completely blown away. I mean, this didn't look like any of the languages I knew at that time. And it looked so much more sophisticated and advanced and pleasant to use and so on and so forth. So I did a short internship on CAML, learning about the language, but also about its implementation, which actually was written in CAML, so it was bootstrapped, so I could see that it was a very good language for writing compilers and language processors, basically. And in 1989, two things happened. So first, Damien Deligé, who was a classmate of mine at ENS, started a master's thesis on garbage collection and memory management. And I was still thinking about the CAM and why it is inefficient and how we could do better, have more efficient abstract machines for call-by-value functional languages. And so we decided to do an experiment. It was called Zinc. It was a GNU-style recursive acronym for Zinc is not CAML. And the idea was to implement CoreML, a really simplified CAML language, using Damien's efficient generational garbage collectors, and using an abstract machine that I was designing, the Zinc abstract machine, the ZAM, where bindings use a stack, like in every other virtual machine for every other language, but are heap allocated only when closures are required. And there was actually a bit of theory too behind the ZAM, because it could be explained in terms of the calculus of explicit substitutions, the lambda sigma calculus that Pierre-Louis Curien and others were working on at that time. And since time was short and we didn't know how to write native code compilers, we decided to do a bytecode interpreter written in C. And the results were pretty interesting performance-wise. We were competitive with CAML despite the overhead of the bytecode interpreter. And then, then the project was kind of put on the back burner for a while when I was starting my PhD on a different topic, and came back to life in 1991. There was really a strong desire to use ML languages for teaching, and the implementations like CAML were not appropriate. They were expensive, that was commercial software, and required big, expensive machines to run on. And really the current state of the art was pretty poor otherwise. I remember playing with a SML interpreter written in C, running in MS-DOS, that would basically crash after a few sentences. And I thought I could do better based on Zinc. And so, with help from Damien Deligé and also Pierre Weiss and Michel Moni, we basically completed the Zinc experiment to get a practically usable ML implementation that could be used for teaching. So that meant adding type checking and type inference, which were omitted in the Zinc experiment, implementing separate compilation and linking, and that's when I decided to use modula2 style modules with an implementation file, .ml, and an interface file, .mli, that can hide some of the aspects of the implementation. There was also a top-level interactive report. It was bootstrapped and was quite portable. So we made it available for Unix workstations, but also there was a port for the original macOS and even a port for MS-DOS running in painfully in 640K of RAM. And it was quite successful in higher education, especially so for undergraduate CS courses, sometimes first programming class, especially in France. So these are some of the books that were written, textbooks that were written in the 90s, corresponding to lectures being given in OCaml Lite. And then perhaps the next step, a few years later, was trying to understand the standard ML module language. So standard ML had this very nice language features for programming in the large, including modules, structures that could be given multiple interfaces, signatures, could be parameterized by other modules. These are called functors, with sharing constraints between the arguments, etc., etc. But that module language was also mysterious, as presented in papers and in the definition of standard ML. Basically, it was given complex type-checking rules based on algorithmic type-checking rules, let's say, based on an internal DAG-like representations with unique names representing types, at least, basically type identity, but also substructures had names, unique identity. And I and several other people in the type programming language community were wanting to explain standard ML modules in more type theoretic terms. Okay, like for all and exist quantification that give a good account of polymorphism and type abstraction, maybe dependent types, maybe something else. And the solution came in 93. Called it manifest types, but maybe I was only the second one to find it because Robert Harper and Mark Lillibridge at CMU were working in parallel on very similar ideas. So we had two papers back to back at Purple 94. But really the crucial idea was this ability to put in signatures equations between types, like type U is actually equal to x dot t. And that accounts for type propagation through functors, but also for sharing constraints to some extent. And eventually that led me to start the OCaml Special-Light project, which was a language and an implementation. So the language was the core OCaml Lite language, plus an implementation of this new approach to standard ML modules, using syntactic signatures and manifest types. And the implementation was reusing much of the OCaml Lite runtime system, including an improved abstract machine, the ZAM2, bytecode compiler and interpreter, but also for the first time a native code compiler. And that came out of some earlier experiments of mine on type-directed unboxed data representations, which were not completely positive. So, but I had to do a compilation to native code because with bytecode you can't really evaluate the impact of unboxing. So that was released publicly in September 1995. And again, here is the announcement. And actually, maybe this is the announcement we should be celebrating, or we should have celebrated last year, because if you look at OCaml today, it still has lots of things that date back to the OCaml Special-Light project, especially in the implementation and the structure of the implementation, which hasn't changed much. And this brings us to Objective CAML, and which is essentially an extension of OCaml Special-Light with some object-oriented features. And so I guess I have to explain why objects. And the answer is that object orientation was really a hot topic in the 1990s. It was kind of a wave that swept industry and software engineering. Many new programming methodologies were being developed on top of object and class decompositions. And industry has fallen in love with C++. So this is a great language. We will never need any other language in the future. And so non-object-oriented programming languages were seen as basically irrelevant things from the past. But it was not just fashionable. Object orientation was also a puzzle, a challenge for programming language theory. It's trivial to give untyped semantics to object languages, but it was extremely hard to explain object orientation in terms of types. And many surprises happened. For instance, in 1990, this paper at the top, Inheritance is Not Subtyping, came as a complete surprise to many. It found an unsoundness in the first version of the Eiffel language, and for software engineering people, it couldn't be that inheritance and subtyping were not the same notion. Also, there were issues of structural versus nominal types. There were failed attempts at encoding objects in terms of subtypes, existential quantification, etc. So much so that Abadi and Cardelli, for instance, developed a whole new formalization of objects, kind of a lambda calculus of objects. The basic notion is not lambda abstraction, but object abstraction. There was also this full series of workshops. It was held along Popple conferences. So FOOL is Foundations of Object-Oriented Languages, and it was initiated by Benjamin Pierce and other luminaries in type systems. And so every year we would basically see attempts that didn't work at giving foundations to object-oriented languages. So that was really a hot topic. And in the OCaml group at INRIA, so Didier Rémy and his PhD student Jérôme Bouillon were working on an approach to objects based on row polymorphism. So row polymorphism is something that Didier worked on earlier to reason about extensible records. And rows give a way for a type system to keep track of the names and types of methods. And row variables can keep track of the other not yet known methods. Okay, so for instance, you could say, well, I have a method m of type int, and maybe some other method o1, and someone else could say I have a method k of type bool, and maybe some other o2, and they can reconcile their viewpoint by saying, okay, we have m of type int, k of type bool, and maybe some other o. Or they could also close the method, the type, saying, okay, all I have is m of type int. And this approach is perfect for inferring the type of an object from its use, like in Damas-Milner type inference. As you see here, this function that takes x and invokes name and rank methods has this type, a method name of type string, a rank of type int, maybe some other methods, and then in return a string. And so this gives a form of polymorphism over objects, which is parametric polymorphism. It's not subtype polymorphism, but subtyping can be recovered by explicit coercions. And that was the basis for ObjectiveCaml 1.00, which was designed by Bouillon and Rémy and implemented by Bouillon, taking Caml specialized, adding objects with row polymorphism in the core language, and adding a sub-language for classes being viewed as object generators that supported a lot of features of object-oriented languages, multiple inheritance, self-type specializations, binary methods, pretty much everything was fitting quite naturally. So at the bottom you see how you can define printable colored points by inheriting from colored points and printable points, and making self-references and super-references and etc. And that was announced on May 96. And the reactions were interesting, as far as I can remember them. So from the full community, the PL theorists, there was a polite lack of interest. Basically, oh, that's nice, but it's not enough like Java, or not exactly what I would like to do. Or, and it started to be obvious that basically nobody would ever agree on a single approach to typed object-oriented programming. Early adopters of ML, including CAML Lite and CAML SpecialLite fans, showed some slight concern. You're not giving up on functional programming, right? And they had to be reassured. But we got many newcomers that were, I guess, reassured by the availability of objects, something that were familiar to them, but then could learn rather quickly how to do without objects and use functions and data types instead. So that led Eric Meyer to quit at OCaml with the rehabilitation clinic for object-oriented programmers. Why not? And that's also when we started to have serious users outside the relatively small community, French community and theorem prover community. There are two influential early uses of CAML SpecialLite and OCaml. The first is ActiveVRML. That was a project at Microsoft Research to develop a domain-specific language for animated 3D scenes. And the second was initially called OCaml and then became the Ensemble project, developed at Cornell and later at IBM. It was a toolkit for building distributed applications. And those two examples are important because, well, first, they managed to convince in RIA's management that CAML was a serious language, not just a toy to be used internally to implement theorem provers. And second, both applications were quite demanding in terms of implementation. ActiveVRML, well, they actually ported parts of CAML to Windows and then had to encapsulate everything into a DLL. And for OCaml and later Ensemble, they managed to achieve excellent performances by controlling latency and garbage collection poses very precisely. I think that was the beginning of an unexpected at the time affinity between OCaml and systems programming, which still exists today. You can still see a strong systems programming culture at OCaml Labs, at Jane Street, at OCaml Pro, and I think that among the high-level languages for mostly intended for for symbolic processing, OCaml has been one of the most successful for systems applications too. So then, well, the language and the system matured over the years. I've listed the major evolutions of Objective-CAML, which at some point became known as OCaml. Version 2.00 in 1998 was a complete revision of the class language for objects, using something that was putting something that was more flexible and enabled more interactions between the core language and the class language. Version 3.00, which I will talk about just next, was introduction of labels, labeled and optional arguments, but also polymorphic variants. 3.05 was about polymorphic functions as first-class values, provided they are put in record fields or methods of objects. 3.07 was experimental implementation of recursive module definitions, which actually stayed, but it's still not very good. And I can say that with confidence because it was my design. 3.08 was about immediate objects, so the ability to build objects in the core language without going through the class system. 3.12 introduced polymorphic recursion and also first-class modules. I'll say a few words about that. And perhaps the latest really big evolution was 4.00 in 2012, which was the introduction of generalized algebraic data types, known as GADTs. And well, let me zoom quickly on three of those extensions because I think they kind of illustrate how and why we were prompted to extend the language in various directions. So for the labeled optional arguments and the extensible variants, so this came from the work of Jacques Garrigue, a prototype called OLabel, which we decided to merge in OCaml 3.00. And Jacques' motivation was very much to better support libraries, especially complicated libraries with functions that take many arguments, so it's important to be able to name them, to distinguish them, or optional arguments to reduce the clutter at invocation. And polymorphic variants were an attempt to mix and match data constructors more freely than declared constructors, and in particular have functions that can only take a subset of a set of constructors. And those extensions were very much motivated by libraries, and especially graphical user interface toolkits. OCaml Lite had a binding to the TK GUI that was pretty awful, with functions that would take lots of arguments and lists of options and would fail at runtime if you gave the wrong option to the wrong function. So that was one of the motivations for this line of work, which continued with label TK and label GTK. A second extension I'd like to mention is modules as first-class values. That was implemented by Alain Frisch, but the design came from Claudio Russo for Moscow ML. And the idea was to give more flexibility to modular programming by encapsulating as first-class values modules and manipulating those encapsulated modules by the core language. And of course, there was a desire to do more with modules, in particular, like runtime selection between several implementations of a structure, etc. And we could have added more constructs to the module language, like an if-then-else, maybe a pattern match, maybe something else, but that would only kind of increase that would create redundancy between the two languages, core language and module language. And this device of encapsulating a module as a first-class value, and then manipulating just like any value of the language, putting it in a hash table, as in this example, recovering it by name found at runtime, and then projecting it back to a module. Well, this device avoided all that redundancy and gave a lot of power to modular programming. And finally, the last extension I would mention quickly is generalized algebraic data types. So that was implemented by Jacques Lenormand under supervision by Jacques Garrigue and Alain Frisch, based on old ideas by many, as you will see on the next slide. And in retrospect, it's a pretty obvious idea that constructors of parameterized data type, alpha ty, may not all produce alpha ty results. For instance, for a type alpha compact array of memory efficient arrays, you can have a default case which takes an alpha array, works for any alpha, and you can have special cases when that takes a byte and it implements a char array, and when that takes a bit vector and implements a Boolean array. And the devil is in the details of pattern matching, and in particular on how you type pattern matching and how you infer the type of the result of a pattern matching. And that took many years to be solved, actually. So ideas, well, maybe first ideas for GADDs appear, well, first in the theorem proving community, in COC, for instance, the calculus of inductive constructions. But in the programming world, well, there's the work of Laufer in 1992 on existential types, which is a special case of GADTs. Then in 1995, Augustson and Peterson write a draft that would never be published called Silly Type Families, where they basically say, okay, it would be interesting to have GADTs, but there will be problems to infer the types of match. And that was largely ignored, in particular by the Haskell community, until, well, 2003, when Chen and Chen reinvented pretty much the same ideas as Augustson and Peterson 9 years earlier. And then the community started to work on algorithms for partial type inference around Simon Peyton-Jones in the Haskell community and around François Petit and Diane-Régie Gianas in the OCaml community. And so GADTs were introduced quickly in Haskell 2007. And we waited a little more for OCaml before the design and the typing rules really stabilized. So just to emphasize that good ideas take time to emerge and take time to actually be ready for integration in a programming language. So, so since 4.00, we had many additions to the language, but much more incremental in nature. It's not to say that they are not useful. For instance, the match with exception construct introduced in 4.02 is great. And extensible data types are pretty nice. We also have inline records, more recently injectivity annotations and type constructors. Well, that kind of small enhancements. And in progress, where we've been working hard at merging multi-core OCaml, and that will be the next big thing, and provide basic support for shared memory parallelism. And there's work in progress, but still not quite ready on having some forms of algebraic effects, in particular to simplify, to give a nicer interface to parallelism, and modular implicits to build some kind of bridge between modules and type classes. All right, so, well, this is what I wanted to say for this retrospective. So a few remarks to conclude. First, OCaml is a language that evolved gradually. In 1996, Guy Cousineau wrote a short history of CAML up to 1996 and concluded that certainly, seen from 1996, the story of CAML could have been more linear. And well, since for 2021, it could also have been more linear. But that's the way languages evolve, I guess. I would claim that the language is still faithful to its roots. It's a mostly functional language, but has imperative and object-oriented power when they are needed. It is very much built on structure around the types. Types provide the skeleton of the language, give it structural strength. And well, this is a line of programming language design that says that basically languages with no types or weak types don't have a structure, they don't have a spine, they look like jellyfish. And JavaScript is, I guess, a good example of that. And finally, there is a lot of respect for type inference and the existence of principal types. In the early days of CAML, it was really fanatical devotion, and these days it's more like lip service. But I think it's an important aspect of the design that we use types, but we are trying to also support type inference and make sure that the inferred types are always principal. There is no better choice. That can sound like an arbitrary constraint, and that limits us. We could have many more features that just don't fit in a type inference framework. On the other hand, I would like to recall you that beauty can come out of formal constraints. Think of the sonnet, think of the still life, think of the fugue. These are all very constrained forms that kind of forced artists to come up with new ideas. And I think type inference is also one of those constraints that forced programming language people to come up with new ideas. And finally, when I prepared this talk, I really wanted to also talk about the emergence of an active community of OCaml users, because programming languages don't go in a vacuum. And then I realized that I had really very little to say except platitudes, so I'd rather stop here and discuss those aspects in the questions. What is obvious is that there have been much collective effort, exemplified in this OCaml workshop and in many other places of exchange in the community. And well, thanks to all for the many contributions, and please keep up the good work. So thank you for your attention, and I'd be happy to take questions now.
Many thanks, Xavier, for that wonderful retrospective on the 25 years of OCaml. So if we go to the questions now, the first one is, from Yan. How did you manage to impose camel light in universities? Where did you get the power to do so?
I didn't impose anything. I mean, I had zero power at the time, and even now. But at the time, I was just a PhD student who liked to program. I think the big breakthrough was thanks to Thérèse Ardin and Véronique Donzo-Gouge. So they were professors at CNAM, Conservatoire National des Arts et Métiers, and they were charged with redesigning a CS curriculum. And that's a big curriculum, with thousands of students in several sites in France. And so they really wanted to do something new with a functional language and an imperative language. And they were also quite close to Gérard Huet and to the research group where I did my PhD. And that's how they ended up doing a curriculum with CAML Lite and Ada. And that was really bold at the time, but it worked very well. And then it kind of snowballed from there, and especially preparatory classes. So teachers from preparatory classes learned about that and invited Pierre Weiss to give them tutorials in OCaml at their summer school, and eventually were sufficiently happy with CAML that they asked to have it in the preparatory class curriculum along with Pascal. So again, one new functional language and one old imperative language. And I should also thank Pierre Weiss, who was extremely active in, reaching out to teachers and professors. Himself was a former math teacher before he did his PhD. So that's how basically it worked, kind of a snowball effect, and I guess we were lucky.
Wonderful. I think we can combine two questions. The first one is from Sam Lindley. And Sam asks, what is your current take on the OCaml object system? Do you routinely use OCaml objects in your own code? And the second one is from Thomas Gassier, which is, did we ever remove any feature from OCaml? And do you want to do this? And if yes, how?
You're loading the questions by putting them together. But so for Thomas, well, the mutable strings is one thing that comes to mind. But it's true that we are quite conservative and, quite respectful of backward compatibility. Okay, well, you can take OCaml code from the late 90s and it will compile most of the time with a tons of warnings. So for the objects in OCaml, I'm still relatively happy to have objects in the core language, in the sense of extensible records of functions with self-application. I think it's something useful. I've used it in a couple of libraries, for instance, my kind of I/O library or data transforming library, like my CryptoKit cryptographic library. And I think that's one reasonable use. There may be others. What I don't like very much is the class system, which feels a bit ad hoc and bolted on the side, and well, it's not subsumed by the module system, but it's a bit redundant at the same time. So I think if we were to do again, perhaps we should do a different class system, or maybe no classes at all, just a pure object language like module F3, for instance.
So this ties into one question from Gabriel Shearer, which is, if you're starting from scratch, would you design a language implementation differently today?
Okay, so this is specifically about the language or specifically about the language implementation? So for the language, I think there's really a central question, which is, well, there's a known question. It should have types and be structured around types. This is a given. And for me, the turning point is whether it should have type inference or not. So with inference, I think you kind of end up with something like what we have today, perhaps with fewer features or better integrated, but well, it leaves you less flexibility. So and maybe some more Haskell-ish features in it. But well, that type inference doesn't leave you that much freedom. And if you leave type inference out, I guess I would end up with something that looks like Coq or Agda or F star, or those languages with rich types and a well delimited pure subset. So and for the implementation, I'm not sure. Well, I certainly understand the importance of targeting JavaScript. So we were lucky to have JS of OCaml as a side result of the Oxygen project. But I think that played a very important role. And so today this would probably have to be taken into account from the beginning. Maybe I would try to, I don't know, make something a little less complicated with respect to bootstrapping and so on. But I'm still kind of not happy with the existing infrastructures. Like I'm still not tempted to compile to the JVM or to .NET or maybe even to WebAssembly. I think all these frameworks don't leave enough room for really implementing the language you want. Not sure this answers the question.
Well, there's a related question from Matthew Fluid, who says that CAML's special light module system was developed as a type theoretic account of SML features, which at the time didn't have one. So are there now existing OCaml language features that you'd like to have a more formal theoretical account from the research community?
That's a very interesting question. I think we have kind of reasonable understanding, theoretical understanding of most of the features, but in a very simplified form. And I'm always afraid that what is actually implemented is actually a lot more complicated. And if you've seen Jacques Garrig's talk at the ML workshop on the how to avoid ambiguity in type inference, this is kind of a delicate formal treatment. It's also a delicate thing to implement. But likewise, so I'm not too happy about the recursive modules. I mentioned it in the talk. They sort of work, but it's kind of hard to describe exactly in which case they work, in which case they don't, and to understand what we could do better. So I think there's still room for better understanding of recursive modules, maybe mixing modules. That's all that comes to mind right now.
I have one question coming in from IRC, which is interesting. Similar to the theoretical side, on the implementation side, you have done lots and lots of high performance implementations on many different native bits of hardware. Are there any hardware features you would like to see in new CPUs, like RISC-V, for example, which would greatly improve the implementation of the language as well?
That's an interesting question, because I've always tried to kind of adapt to what the hardware and the operating system gives us. In the 90s, there was hope that we could do that. The runtime system for a programming language could do interesting things if it had more control over virtual memory and memory protections and that kind of things. And at that time, and I'm afraid still today, those like changing the permissions on a table and a page is just too expensive. So we can't really use that. But yeah, some kind of more lightweight way to control accesses to memory and then catch access violations and so on. And maybe the capability-based architectures like Cherry have something to say in this respect. So quite frankly, I'm intrigued by what you could do with Cherry beyond security. Okay, but as a way to implement high-level programming languages. I think, and very recently we are experimenting with prefetching and that kind of thing. So trying to take better advantage of the memory hierarchy, and maybe there's a whole lot of things that should be tried here. I don't know.
I'm supervising a Cambridge undergraduate project on Cherry porting, so I'll get back to you on that in a few minutes.
Sounds good.
Continuing to talk about the implementation, Edwin Torok says a common criticism of OCaml is the forced static linking, and this doesn't work well with system package managers and security updates. So what can be done to improve this? And do you think there's a type system solution for safe and partial linking?
Yeah, that's a good question. Indeed, at the beginning, I was not expecting dynamic loading and plugins and so on to be that important. And at the same time, I'm really not happy with the shared libraries or we have under Unix or the DLLs we have under Windows. I think they are not a good match for strongly typed languages. Okay, they're just too lax. So perhaps one of the things we should collectively think about is better loading and linking mechanisms, and that maybe one aspect where the JVM or .NET are somewhat better than what we have today. So you see, I can concede that. But still, I mean, look at the JVM. I mean, in the end, it's doing very late type checking by code verification, just to gain some assurance that everything is consistent, and that is super expensive. So I'm still hoping for more efficient and maybe slightly more static mechanisms. The downside of doing everything dynamically is that also you get a lot more failures dynamically. Okay, and so yeah, we'll see.
And so just so we don't have only criticisms about the implementation, Enguerrand Decorn asks, from where do you think stems the success of OCaml as a systems language, and what sets it apart from other alternatives, be it in academia or industry?
Okay, well, I think among the functional programming languages, the implementation was, I think, more efficient than many others. Efficient in execution speed, but also efficient in memory usage, and that's perhaps even more important. And also latency. So it's not only speed and throughput that is important in systems programming, especially in projects like Ensemble, it's also latency. So the ability to, in Ensemble, they played very clever tricks to control when garbage collection can occur, for instance. So that GC will occur when a packet is in flight and the CPU is free. But while the CPU is making the next packet, it should not garbage collect. And so they were able to control that pretty closely. And I think the general architecture of Damien Deliget's GC was also oriented towards low latency. And we see this obsession for low latency in Go, for instance. I think the systems community like that, and I agree it's important. Yeah, I think these are the important things. I mean, if you look, at I don't know, early Haskell implementations, if you look at standard ML of New Jersey, these were quite fast but extremely memory hungry and hard to know when they would garbage collect, and even in the case of Haskell, when they would actually compute. So yeah, OCaml also has a significantly simpler cost model. You have a pretty good idea when things are being evaluated. And even the JVM, for instance, has always been plagued by high startup times and that kind of things. Okay, and I still don't understand why. Probably because of their insistence on just-in-time compilation and everything. But that makes Java less applicable to many systems applications than it could be. And then they invented subsets of Java and so on. But yeah, so I guess yeah, several characteristics of the implementation were very useful. And I also think that in these days, in the 90s, many systems persons were looking for better languages. So many started in C, then tried C++, and were not happy with it, especially because the first C++ compilers were bad. And so I think there was some kind of awareness that they wanted to try new programming languages.
Got it. And whenever you have done all these implementations, Jan asks, was there a feature that you implemented and you found surprisingly useful, but you just did not anticipate? Some emergent property out of this implementation?
I'm sure. Well, I mentioned the match with exceptions in the talk, and indeed, this is something very, very nice, and we should have had that much earlier.
First class modules also leap out as
that. Well, yeah, small additions to the module language that makes it a lot more useful. I'm thinking of local opens, for instance, which make name control less and scope control a lot less painful. But yeah, it's interesting. I think it would be interesting to look at the features and see how universally used they are today, and how fast they were adopted.
Related to that mention of the module system, Jason Zhu from Bloomberg asks about this. He feels that the module system of OCaml is more flat compared to those of other languages, which can have deeply nested namespaces. So do you have any thoughts on improving this or other aspects of the module system?
Okay, yeah, that's interesting. So we have nested structures. Okay, it's one of the characteristic features of the standard module system, standard ML module system. It is true that we have a flat namespace, or mostly flat namespace, of compilation units, and yes, this is a bit of a problem. So we have ad hoc solutions around that. So maybe we should have thought more about managing the namespace of compilation units. I agree with that. So yeah, I'm familiar with Java and how they use fully qualified domain names for that. Why not? Although at some point I was working at a startup company, doing Java at a startup company called Trusted Logic. And so I must have spent like 6 months of my life typing fr.trustedlogic, blah, 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 at the beginning of every Java file. But never mind. So yeah, probably the namespace of the compilation units should be rethought, yes.
Now, we've had a number of questions from Eduardo and from Edwin Torek from Citrix, asking about the future of OCaml. And specifically, Edwin's question says, how do you see OCaml evolving over the next decade? So are there any particular features from other languages you wish that OCaml had? And do you see more evolution towards proof of correctness, performance, and new language of type features?
That's a tough question. I mean, I don't have a big vision for OCaml. As I said earlier, I've been very much into dependent types and programming in the Coq proof assistant and proving purely functional programs written in Coq. So certainly that's one direction for my own programming, but I also recognize that, well, that may not be the way we want to follow with OCaml. I mean, it's also good to have a language with more conventional types, and but which is also a lot more usable and still has some built-in effects, for instance. So in my programming practice, for instance, I'm very happy to have CAML for some projects and Coq for others. I guess that's what I'm trying to say. So yeah, I will pass. I think I don't have personally big plans, but I think some other members of the community actually are really thinking of what we could do better or what we could do next. So, yeah, I mentioned the merge of multi-core OCaml. It's not just a question of, well, there's a big aspect, which is runtime system, memory management, etc. But there's also an interesting aspect on using algebraic effects and making interesting things with it. So that might be, that's a plausible evolution, let's say. Yeah, I think I will stop here.
That sounds good. We just have one last question on that topic from Fabrice Lefesson from OCaml Pro, who asks about your thoughts on ownership tracking through types as seen in Rust or Mezzo.
Say that again. Oh, okay. Well, it's certainly extremely interesting. I mean, Rust is a very impressive design that I think we should all study what they've done, because it's both a very advanced type system and a very systems language. I mean, very close to the hardware and explicit memory management and resource management. Part of me says that, well, we have a garbage collector, so we need fewer types and fewer less ownership tracking and so on. And the other part of me says, but we also have other resources, especially in a concurrent setting, where we need to do stuff. I would say that the chances of having, well, we really need to come up with new ideas if we want some kind of ownership tracking through types that would fit the rest of the type system. I'm afraid we can't just borrow that from Rust, and even, well, maybe a little more from Mezzo, but even Mezzo had kind of a lot of new machinery. So I'm not saying it's impossible, I'm saying it's going to be tough.
Thank you. So thank you for all those answers and discussions. I had one question for you to close with. Your career is characterized by you building ever more ambitious pieces of software built over the previous one. So we have Camel Lite to OCaml to Coq, and then CompSert is certified C compiler, and everything depends on the previous thing. Do you have any advice for young researchers who are just starting out now, who want to do something equally ambitious over a few decades? Did you start off with a plan to build CompSert? Did it emerge
No.
as you walked through the path? How would someone getting into research look at this now?
No, not at all. And well, I would say it's also okay to use other tools, okay, in your own research. And Coq, for instance, is not at all my design. When I was a PhD student, I kind of hated what they were doing with Coq. That was completely incomprehensible. They sounded like, you know, a new church of constructive logic. So, and it took me like 20 years to really understand what they were doing and saying, yes, this is great. So the advice I would give, basically my work was mostly curiosity driven, and well, driven by really a love of programming languages and a desire to implement them well and play with them and make them useful. And so I would encourage that kind of curiosity and yeah, and staying alert. I mean, trying to see if there's an opportunity, if there's a need. As I said, at some point there was this need for teaching in a strict functional language, and that triggered many things. But yeah, my career hasn't been planned very well, I must say. I'm more of the opportunistic kind.
Thank you. It gives me hope that it took you 20 years to learn Cox. I have time yet to figure it out.
There is still hope. There is still hope for you.
There's always time. I have a few years. On that note, thank you very much for being here with us.
Thank you.
Thank you.
Hello, welcome to the fourth session of the OCaml workshop. We have 3 talks, and the first one is Thomas Lerner that will present his experience with effect on multi-core OCaml.
Leonard, and I've recently been looking at the new effect system proposed for possible inclusion in OCaml. In this talk, I'll be giving a brief introduction to effects, and then reporting on our experiences using them over the last few months. Just to put this into context, there are 3 branches of work going on here. There's the domains work, to allow using multiple cores simultaneously, the runtime effect system, which this talk is about, and the typed effect system, which I won't be talking about at all. Support for multiple domains and for runtime effects are both in the multi-core repository, and you can install them with OPAM today. The structure of this talk is going to be a brief introduction to effects for people who aren't familiar with them, then an example using effects to simplify the Angstrom parser combinator library, and finally a look at EIO, a new effect-based concurrency library. Effects are essentially resumable exceptions. You declare an effect in much the same way as you declare an exception, as you can see here. The difference is an effect also has a return type, and that is the type of the value that will be passed back to the code when the effect is resumed. So here's a simple example program, just prints step 1, step 2, step 3. We enter a try block, we print step 1, we perform an effect very much like raising an exception. So here we use foo2 as the payload. That is handled by the nearest enclosing handler. But unlike with an exception, we also get this continuation value k, which we can use to resume the code later. And so here we'll print step 2, and then we resume the effect, passing in the value 3, which comes back to here and becomes the value of x, and the program continues. And this example is fairly useless. We could just have used a function here. But what's really powerful about effects is you don't have to resume the effect immediately. You can store it somewhere, or return it from the try block, and you could then resume it much later, or resume a different continuation first. And this makes it really easy to use effects to build schedulers for running cooperative lightweight threads concurrently. It gives you the ability to have multiple OCaml stacks active at once, even on a single core. And this allows us to write concurrent code just the same as we would write sequential code. And you might ask why we need to do that. We can already do that using LWT. But there are some nice benefits to using effects. It ends the distinction between sequential and concurrent functions. So a lot of OCaml libraries at the moment provide a sequential version and an LWT version, and maybe an async version as well. But with effects, you can just write one piece of code and have it work in all cases. You don't need a special monadic syntax, and it means you can use all the standard features of OCaml in concurrent code. For example, if you're using LWT and you want a try block or a while loop, you can't. You have to use equivalents provided by LWT. And that's fairly simple, but it would be nice to be able to use the language's built-in features directly in concurrent code. Using effects is also faster, because we're not using the heap to simulate a stack. And having a real stack means that backtraces and profiling tools work properly too. So that's a very brief introduction to effects. Let's look at how they can help in a real program. So Angstrom is a popular OCaml library for writing parsers. It's designed for concurrent applications such as network services, and it has a really strong focus on performance. So as a warm-up, let's look at a toy parser first. The idea here is we've got some input stream of characters, and we'd like to read a value from it. And in this very simple toy parser, we'll say that an alpha parser is just a function that takes the state of some input stream and produces a result value of type alpha. Here's an example of a primitive parser, anychar, which just reads one character from the stream. First of all, we're checking that the buffer contains at least one character, and maybe at this point we'll stop and wait for some data to come in over the network. And then we get the character, we update the state of the input stream, and we return the character as the result of the parser. And the idea is that these simple parsers can then be combined. For example, this right star combinator combines two parsers, A and B. First of all, it parses with A, then it throws the result away, and then it parses with B and returns that as the result. Maybe A consumes some white space and B parses the actual value we want. And that's fine if you want blocking code. The problem is if you want to run, say, a web server, and you don't want your whole system to stop running, waiting for data from one request. You want to be doing other things while you're waiting. And because of that, real parsers can be more complicated. So now let's look at the real parser, Angstrom. We'll look at the equivalent to this type. So instead of saying that a parser is a function from a state to an alpha, Angstrom says this. You don't need to read all this, but what I want you to notice is that it's got more complicated. Roughly speaking, a parser in Angstrom is a function that takes the state of the input stream, a continuation to call if the parse fails, and another continuation to call if the parse succeeds. And it returns, well, it might return success and the value you parsed. It might return failure, but it might also return this partial state. And that indicates that Angstrom didn't have enough data in the buffer to be able to parse your value. The application code now needs to get that data somehow, put it in the buffer, and when it's ready, call this continue function to resume parsing where it left off. And using this API, we can define any char. It's a bit more complicated than before, but here it is. It takes the state of the input, the failure continuation, and the success continuation. And in the case of any char, it always succeeds, so it calls the success continuation with the character it read. And in the case of the right star combinator, we run A with a modified success continuation, which discards the parsed character and then runs the B parser. We could have made this code look a bit nicer using a monad, but that would also have a slight performance cost, so Angstrom writes everything in this callback style. So we got to thinking. A lot of this complexity is about trying to suspend parsers, and this is something that effects can allow us to do very easily. So we made an effects branch of Angstrom, and this is what we came up with. Well, this is just the toy example I showed you at the beginning, because that is exactly what you can do when you have effects. On the effects branch, a parser really is a function from an input state to an alpha. In fact, I didn't have to use any effects at all to implement this. You could run this branch on an ordinary non-effects version of the compiler, and it would just be a boring blocking parser. But when you set up this state parameter, you provide a function to refill the buffer. If you provide a function that performs an effect, and you run the parser within an effect handler that implements a scheduler, then you now have a concurrent parser. And Angstrom itself doesn't need to be changed in any way to support that, which is pretty nice. Okay, so that's a lot simpler, but what about performance? Here's a micro benchmark. The parser we're using here is skip many any char. Skip many is a combinator that just runs its argument repeatedly and throws away the result. And we're processing some long string here. These are results from core bench. And we can see that using the effects branch, it's 13 times faster than upstream Angstrom. But perhaps more interestingly, when I was doing the conversion, once I'd written the skip many combinator as plain OCaml code, it was really obvious that it wasn't tail recursive, and it was also really obvious how to fix it. So for a slightly more fair comparison, I went back and I modified Angstrom with the equivalent fix. And with that change, we're only 3 times faster. That's still pretty good. You'll also notice that the effects version doesn't allocate any memory, or at least it doesn't allocate any memory on the heap. It's only using the stack. This benchmark's nice, but it's not very realistic. People don't really write parsers that parse individual characters because the overhead is pretty high. A more realistic parser is parsing an HTTP request. And this is one of the benchmarks in Angstrom's test suite. And here we've gone from 60 milliseconds with the original Angstrom to 50 milliseconds with the effects branch. And we've also gone from 102 kilowords to 600 words allocated on the major heap. It's not a huge speed up, but it's quite impressive for a well-optimized library like this. So it's a little disappointing that we haven't actually used any effects yet. I mean, just the mere fact that effects exist allowed us to make all these simplifications. But I did find one place in the code where it was actually useful to define and handle an effect in Angstrom itself. And that was to provide some backwards compatibility with the old API. Angstrom has an existing buffered API that provides a simple abstraction for feeding data in. The effects version of that API is much simpler, but to avoid breaking existing software, I wanted to continue offering the old callback API too, while internally using the new effects-based parser. And this is the simplified version of that code. I define a read effect to be called when Angstrom needs more data, and then in the parser itself, we create the buffer as before. We call the effects-based parser, passing in our read function that performs the effect. And when Angstrom needs more data, our effect handler is called. And that returns the old partial object to the application code the same as before. The application then fetches some data itself, and when it's ready, it calls this continuation function, which then continues the effect. So the user just sees the old callback-based interface, but internally we're still using effects and getting the performance benefits of that. The refill event happens relatively rarely, so this callback wrapping isn't performance critical anyway. So in summary, using effects here made the code go slightly faster, but more importantly, it made it much, much simpler. We didn't need to use any effects at all in the interface, or in the main implementation. We only used them in the backwards compatibility layer. The public API looks very similar to before, except now it looks like we also offer a simple synchronous API. Except that with effects, that synchronous API can also be used asynchronously. And combining effects code with callback code is also very straightforward. Now, so far we've been assuming the existence of some concurrency library using effects, and I'd like to talk about that next. We've been building an effect-based alternative to LWT or async called EIO. It provides a generic API package which performs effects and that libraries can program against, and then there are various backend packages that handle the effects. We've got two backends at present. There's a libuv one that works on Linux and macOS at least, and probably other platforms as well. And we've got a high-performance IOU-ring backend for Linux. IOU-ring is a new way of writing applications for Linux where you share a ring buffer with the kernel and write the operations you want to perform there. Linux performs them asynchronously and writes the results back to another ring buffer as they become available. And that avoids the overhead of using syscalls. So here's an example of a little EIO program. This is a web server. Here we're using the HTTP AF library, which is a nice high-performance HTTP library using Angstrom to parse requests. And we've modified it a little to work with EIO. And this setup is essentially the same as you'd have with the LWT version. Then we've got the main function, which takes access to some network as an input. It creates a listening socket on some host and port. And then in a loop, it accepts connections and handles them using the handler. And we can see that this loop is written as a normal OCaml while loop. There's no need for any special library function or PPX here. So how does EIO perform? Here's a benchmark. We're using the work2 load testing tool to open 100 concurrent connections and then make requests as fast as it can on those connections. On the horizontal axis, you can see how fast it wanted to issue requests, and on the vertical axis, how fast the servers were able to go. At the bottom, we've got LWT with the co-HTTP library at around 40,000 requests per second, and then Go is a little higher at 60,000. We can go quite a lot faster by using LWT with HTTP AF instead of co-HTTP. That's around 130,000 requests per second. And using AEIO, which is a very simple effects-based library that reuses parts of LWT, we get around 140,000. Then near the top, at around 190,000 requests per second, we have Rust with the Hyper framework. And right at the top, at about 200,000 requests per second, we have HTTP AF with EIO. I should say this benchmark is a little bit cherry-picked, because if you run this with 1,000 concurrent connections instead of 100, then Rust is first and EIO is second. And also, Rust has recently released their own IOU-ring version, and we haven't benchmarked against that. So I suspect Rust will soon be in first place again. But in any case, effects give OCaml very competitive performance, and much better than we've had before. I should also say that in these benchmarks, we limited the servers to 1 core, because some of these servers can only run on 1 core. But Rust, Go, and EIO can all use multiple cores when available for a nice speed up. Before I wrap up, I'd like to mention a few other interesting features of EIO. It uses structure concurrency, so you can tell from a function's type whether it can create any threads or file descriptors that outlive it. It uses the OCaml security model, so if you're writing a web server and you want it to serve only files within some directory, you can just pass the function access to that directory and it won't be able to access anything outside of it, even if the user tries to trick it by passing a path containing ... or by following a symlink that points outside of the subtree. We have tracing support that integrates with Mirage Trace Viewer, and we have support for multiple cores. The library is still very experimental, and it's not ready for general use, but if you'd like to help us refine the API, then please give it a try. To conclude, our experience has been that using effects for concurrency works extremely well, and that effects have very good performance. Even in the benchmarks, the effects system didn't seem to be the bottleneck. Now, I didn't work on the effects feature in the compiler itself, but congratulations to the people who did. I've not found any bugs in the effects system during my testing. I did find a few bugs in the multi-core support, which have been fixed, but none in the effects. It seems really robust. And if you'd like to try out the effects feature or the EIO library, there is some getting started documentation on GitHub in the OCaml multicore/EIO repository. And thank you for listening.
Thanks, Thomas. If you are, yeah, you are here. We have some questions. Hi.
Hi.
So the first question is from Gabrielle. So, so for Engstrom, much simpler code is cheating a bit, as the data stuff in the original code tracks effects statically, while you compare with untyped effects.
I'm not sure what the question is. Does it matter? I mean, when you're using something like EIO, you're always running it in the context of some event loop that's going to handle the effects. So it doesn't matter too much. You're not going to get an unhandled exception for this use of effects. I'm not sure I'm not sure what other difference it makes. I mean, you can see that it might suspend, but if you're using the effects version, you know what you passed into that state parameter. You know whether you set it up with something that's going to perform an effect. So I thought you could guess pretty easily. I'm not quite sure what the question is. Sorry.
Gabriel, if you want to precise your question, you can ask another one. The answer. Anil responded as it's okay. They are working on it, but the version just makes it harder to interpret. So another question from Edwin. So what is the best way to deploy the effects version while still supporting old compilers?
Well, in the case of something like Angstrom, as I say, we didn't actually need to use any effects. So that code would actually work on both, except for the compatibility layer. If you wanted to do that, you'll need some kind of conditional compilation, the same thing as you would need with any other library, really. Something like CPPO or whatever. There is one problem with the effects compiler, which is it extends the syntax of OCaml. So there's an effect keyword, but there is work underway to get rid of that and just be able to access the whole thing using standard OCaml syntax, which will help a lot with things like using tools like Merlin and ODoc and all that kind of thing.
Yeah, and tiny question from François. So there will be an academic paper about I/O. Is it in the program?
I wasn't planning on writing one. It's got a long way to go before we're ready to write about it, I think. I mean, it's a nice test vehicle. It can do various things. At the moment we've got a web server, as I've shown. There's also a little Gemini client, which shows it working with OCaml TLS and NoTTY. So we've got a few basic integrations. A few things work, but it's not ready for general use. If you try and use it, you will very quickly run into missing features, and you will have to go into the library and add support for things. So I think probably it's going to be like a year away or so.
Okay. And we have time for even more questions. Geoffroy asked, are the effect continuations single shot, or they can be invoked multiple times?
They are all single shot. That's the only kind that OCaml supports, which I'm very happy about. I think writing code to handle concurrency is fair and reasonable. Trying to write code that works correctly when anything can perform an effect and you might get resumed multiple times, it's really hard to reason about the correctness of your code if continuations can be multi-shot. So I think this is the right design decision, but it does mean if you want to do things like incremental compilations, you'll still have to use a monad for that. You can't do that with effects. I think there is an experimental feature actually in the obj module. There's something like clone stack or something that can simulate this, but it's not a supported thing, and I don't think it should be.
So there is no more question from participants. I had one question about the platforms. You say that the I/O library is usable on Linux. Do you have, not for the moment, but for further plans to support, for example, Windows?
It may work on Windows already using the libuv backend. I haven't tested it. If someone wants to try that, that would be very interesting to know. But we would like also to have custom backends, because Windows, for example, has its own native I/O support, which we should use. And on macOS, there's already a PR adding support for Grand Central Dispatch as a draft PR that needs some more work. But yes, we're definitely, and also on FreeBSD, it'd be really nice to take advantage of Capsicum as an easier way to implement some of the security stuff. So that's definitely something we're very interested in.
Yeah, it's a good to hear. I don't know if other participants have questions. Seems no. So I think we thank Thomas. Thank you for the talk. Maybe. Thomas asks if you know why the Go version is so slow.
No, I don't. I was surprised by this. I have looked at the code in that repository, which if we got any Go programmers here, please do go to the repository and try and make it faster. It's just using the HTTP server in the Go standard library, and it's using it in a very straightforward way, so I don't know how we could have done that wrong. I suspect what it's really telling us is that people don't really care how fast static web servers are. It's not usually the bottleneck whether you can do 60,000 requests per second per core or 200,000 requests per second. I mean, my blog doesn't get that much traffic, so. But yeah, and also Rust. If anyone thinks the benchmarks are unfair of their thing, please do go and look at it. It's in OCaml multicore / retro HTTP benchmarks, I think. I would love for someone to double check the stuff there.
If you can share the link on the chat, it will be.
Yeah, well, I'll do that.
Okay. Thank you for the talk and answering the questions. We can go to our student talk. It will be Fabrice Lefesson that will present how to build binary OPAM packages with OPAMBin.
I am Fabrice Lefesson from OCaml Pro, and this talk is about OPAMBin, or how to use binary packages with OPAM. Let's start with some motivations for this work. So there is a very nice feature of OPAM called local switches that is very useful. If you are in a project, you can call OPAM switch create dot in the project to create a switch that is local to the current directory, and you will be able to install the dependencies of the project on the project packages inside that switch. That's very similar to what other package managers like Cargo or NPM do. However, the problem is that you end up with many copies of the same compiler or packages, the popular packages like Dune or libraries that are used by many packages. They are all installed in every local switch that you create, so you end up with many such directories. So the problem is that for every copy, it takes a lot of time to build, and it takes a lot of time and a lot of space on disk. On my computer, one switch is usually more than 1 gigabyte. Also, if you don't use local switches, but only one switch, you will anyway spend your time building packages, removing packages, reinstalling other packages, and then if you switch back to the initial project, you need to reinstall the former packages, and every time you do that, it takes a lot of time to build the packages. Of course, it takes less disk space, so it's a compromise between them. Also, there is a nice interaction between binary packages and continuous integration. For example, if you have a CI that creates nightly builds of your project every night, you can use it to create binary packages and push them on a repository. That way, users can download these binary packages and use the most recent version of the project every day without needing to build it. That's a quite popular mechanism used for some other languages like Java, and I think it could be very useful to use it when, for example, you use OCaml as a small part of a bigger project. Then it makes it easy for all the developers and all the users to use that part without needing to build it and to have a toolchain installed. Finally, there is already a script called OPAM cache in the OPAM sources, but from that point of view, it's not good enough because the binary packages that are created are not relocatable, so you cannot use them in different switches, for example, in different local switches, and also there is no easy mechanism to share these packages between different users. So we did OPAM-bin to try to solve all these issues. So when a package is installed using OPAM-bin, it is automatically patched. So there is a patch found in a set of patches that is found on GitHub that is applied to the package, and it makes it relocatable, so it can be moved on the disk and installed anywhere. A binary archive is automatically generated also from the artifacts of the project. When the package is reinstalled, then the binary archive is used instead of compiling again the package. Then OPAM-bin also creates an OPAM repository where it stores all the generated binary packages so that other users can use these packages on their computer, and even without using OPAM-bin, just by using OPAM. Finally, OPAM-bin has a mechanism to detect identical files installed in different switches and makes hard links for them so that you only have one copy of every file in all your switches. So it saves a lot of disk space. So let's see a few steps of a standard usage of OPAM-bin. The first step is to install OPAM-bin and configure it. So usually you just need to use OPAM and install OPAM-bin from the official repository of OPAM, and then call OPAM-bin install for OPAM-bin to configure itself. So here we can see that OPAM has installed OPAM-bin, and then when OPAM-bin is started, it's going to create a configuration file. It's going to copy its executable within the .opam plugins directory, so that it doesn't matter in which switch you install OPAM-bin, it will be able to use it from any switch. It's also going to check for OPAM hooks and change the configuration of OPAM to call OPAM-bin every time a hook is called. Finally, it downloads the current set of patches for relocation of OCaml packages. Now we can check the configuration. So we can call opam bin config. The reason for that is that OPAM uses it now as a plugin, so it can be called from anywhere using this notation. And this command will display all the options of the current configuration of OPAM-bin. Of course, all these options can be configured, can be changed by calling these options, this subcommand with the correct arguments. Now let's try to install a switch with OPAM-bin. So here I'm just calling OPAM switch create with a version of a compiler. So OPAM-bin is going to print a message showing that it is active, that it has the option to create binary packages and the option to share files between switches. Then OPAM is going to install, to build and install all the packages. And OPAM-bin at the end is going to print a message showing what it did during those installations. So it created here a set of packages, binary packages, and for every package, so there is a bin package that has been created with a version containing 2 hashes, 1 hash for the sources and 1 hash for the binary part created. So we see that building all these packages took a lot of time, a bit more than 3 minutes. just for building the compiler. Now let's reinstall this switch. So we remove it and we create it again using opam switch create. So we could have called it with a different name, it wouldn't have mattered. OpenBean is still active. And now let's see what has happened. So here OpenBean tells us that instead of building the packages, it used the archives that it found, the binary archives that it found in the cache. We can also see that it took very little time, a little more than 30 seconds to install all the packages instead of more than 3 minutes. So it's quite efficient. So now let's have a look under the hood. So OpenBean benefits from a feature of OPAM called hooks. So these hooks are currently mostly used for sandboxing. There are commands that are called at different steps during the installation and removal of packages. So there are 4 families of hooks. There are session hooks. So these hooks are called before and after a session. So before any OPAM command, whether you install, whether you update, whether you remove. There are hooks for build commands that are in the OPAM file. So there are commands that are called before, after, and for every command in the build file, in the build list, there is a wrapper called the command. And that's the part that is, for example, used for sandboxing. So there is commands like that for the build steps. There are commands like that for the install steps. And of course, there are commands like that for the removal steps. OpenBean uses most of them. I put in parentheses the free ones that are not used. So you can see that it makes a very high use of this switch, these hooks. So if we have a look at the configuration of OPAM after installation of OpenBean, we can see that, for example, for the pre-build hook, OPAM is going to call OpenBean the pre-build subcommand with a name, the name of the package, the version of the package. If the OPAM file is defined for this version of OPAM, then an argument for that, and the list of dependencies of the package, and so on for all the hooks that OpenBean uses. Now, if we have a look at every step, in the pre-build step, the OpenBean is going to check simply if the package that it's trying to build is already a binary package, in which case it has nothing to do. So for that, we have a file that we put in every binary package that is called beanpackage.version. And if that file exists, then OpenBean doesn't have anything to do. If it is not the case, then we are going to locate a patch for the relocation of the package. So if there is one, we check the version and we try to use a patch that has a smaller version than the current version, so that, for example, if you have many versions of a package, you may only need one patch for all of them. So that's quite often the case for many packages. Now that we have patched the sources, we are going to check that all the dependencies have been installed as binary packages. That's very important because for the consistency of binary files, we need a binary archive to be created only if all its dependencies have also binary versions. Otherwise, we'll end up with inconsistent assumptions. Then we also need to have the OPAM file for that package. So either it was provided as an option, or we will call OPAM to get the current version of the OPAM file that is being used for the installation. So using this command OPAM show. Now we compute a source hash. The source hash is composed of 2 parts. There is one part that is the package UID, which is the hash of the sources on the OPAM file. So that's the part that is related to the package and to the internals of the package in some way. And then there is the dependency part, which is composed of the name, the version of the package, and all its binary dependencies, including their source and binary hashes. That way, we have a unique identification of the package, of the state of the package, and we can try to see if for that source hash, we have currently a binary package that exists in the cache or in the repository of binary packages. If we found an occurrence, then if it is remote, we can download the archive, and then we extract the files in a local directory called bin cached. And then, because OpenBin is going to be called at every step of the installation, we need to save the current state in a file, what we call a marker, and that is stored in the local directory. That will be used for the next steps to know what OpenBin has to do. So for the wrap build subcommand, which is called for every build command in the OPAM file, we just need to check that we will only execute the build command if they are needed, which is that if there are no binary archive that was found for this file, for this package. Now that we have built the package, we are going to check in the pre-install step if there is a bin cached subdirectory. If it is the case, it means that we have found a binary archive in the cache for that package. So we just need to copy all the files from the bin cached subdirectory to the OPAM switch prefix directory. Now, wrap install subcommand is the same as wrap build. We only execute the commands if it is needed, which is if there is no binary archive in the cache. Then, in the post-install step, we only do something if there was no binary archive. Then we have to create a binary archive for this package. To do that, we start by building the archive of the files. There is a very convenient feature of OPAM for that, because it knows which files have been installed. So we can ask OPAM to provide the list of files to include in the archive. Now we also compute the binary hash of the package, which is the binary hash, the hash of the binary archive, and we can generate the final name of this package, which is the package, its version, plus the bin suffix, the source hash, and the binary hash. The first part, until the source hash will be used to locate binary packages in the cache, and the other one is used to make unique the dependencies between binary packages. Now that we have everything, we can create the OPAM repository part of the package so that it can be used by other users. So for that, we need to build a package directory in the OPAM repository. We create an OPAM file for the binary package, and we only add two small meta information files. One is the bin package version that is used as a marker for binary packages when calling OPAM bin, and one is some meta information that is, for example, used by the OPAM bin search command. Now, if we want to share our repository of binary packages, we need to configure two options. One is to tell the user where they should download the archives, the binary archives. So we need to provide the URL of the website as the base URL. So this command is going to patch all the OPAM files in the repository to use this URL as a source for the archives. We also need a second option to tell it where it should copy the repository, but this time using rsync and SSH instead of a URL. So these two URL actually are for the same server, but one is the website and the other one is through SSH. Now we can use OPAM bin pool. It's going to download the current state of the OPAM repository as it is seen by other users. We can install some packages. The binary packages for these packages will be added to the repository automatically. And then we can use OPAM bin push to push the new packages to the website using rsync. So if we have a look at what does OPAM-bin push, for every subdirectory so there is a directory store where OPAM-bin put the OPAM repositories it creates, and then we can, for every one of them, it will call OPAM-admin index that creates an index used by OPAM when it has to download a repository. We will generate an index.html file to make it easy to browse the content of the repository, and it will push the files to the website using rsync. So if we have a look at the index.html file, you can see that all the packages that we created before are there. Actually, for every package, there are two packages created. One is the binary version of the package, and one is a package plus bin. That means that, for example, if you want to really force the use of a binary package instead of a source package, you can use this new package name so that it will force the installation of the binary version. Because depending on the dependencies, you could have a case where you download a source file, a source package, and there is no binary package with the dependencies. So if you force the binary version, it will install packages for which it has no binary version, and it forces the installation of binary dependencies. So for a given file, for example, if you look at OCaml-based compiler, you can see its version. You can see the archive is about 200 megabytes, but it will install about 500 megabytes on the disk and more than 2,000 files. Using the meta information files, we can use the OPAM-bin search command. With this command, you can search files, a bit like apt file. You can see which archive contains a given file. You can see which archives depend on a particular package. And you can also know the size of the packages when they will be installed. There are a few limitations. For example, today there is no support for side effect packages like the confstar packages. So we think that OPAM needs to provide a way for OPAM-bin to deal with such packages. It's not clear what we have to do also. OPAM-bin also uses the hooks, but for now, when it does it, it disables sandboxing. So we need to find a way to be a little more clever, to have OPAM-bin and sandboxing working together. And finally, most OPAM packages in the current repository do not correctly tag their dependencies as build dependencies. So actually, binary packages could have much fewer dependencies than they have if these tags were used correctly. So thanks a lot for listening to this talk. So I hope you will try to use OPAM-bin and see if it works well for you. And if you want to contribute, the repository, the project is on GitHub, and so you can help us by providing feedback or contributing new features. Thanks a lot.
Thanks, Fabrice, for the talk. Don't know if you should be here. Yeah.
Can you hear me?
Yeah, very well. Hi. Thanks for the talk. We have a question from Edwin. So, are the binary builds reproducible? There are several questions. About the first one about the build reproducibility. And so let's answer to the first one.
So no, there is nothing done by OPAM-bin for reproducibility though. So if there's nothing done for that. So it really depends on OPAM and how the package has been done for reproducibility.
Okay. And also, how do you ensure that a binary produced on one distribution is not used by accident on another distribution?
Again, there is nothing done for that. Of course, it's a very important problem. So I think that it's something that we would have to do at some point, either in OpenBean, or maybe we can find other tooling that can extract from binary files their dependencies. I mean, their system dependencies, like LDD or this kind of tools. My idea was more to choose, for example, a Linux distribution or some operating system, and then to provide a distribution of packages, binary packages for that distribution. And then, of course, that would give some consistency on the system dependencies that are used. But on the other idea is that, as I said, there is a limitation about conf files. So if we can provide binary packages for configuration files, then we would be at least able to check that the library that we are using as a dependency is installed on the system, which is not the case currently, because since conf file do not install any files, so they are actually empty binary packages. So we have to think about a good way to solve this problem.
If I can add on the open part, we have in mind the reproducibility of open packages, and there is some work done by Hannes on a plugin to check the reproducibility of package that afterwards OpenBean may use it. So we have a question from Anil about the build dependencies. So it says, I didn't understand the last about build not being used in the OPAM repo. Can you give an example of this? And in most cases, using build is unsafe since you don't know if a future version of the package will affect semantics of the build.
The idea is that when you know that dependency is already only used for building, then you don't need to add it as a dependency for the binary package. So, for example, if your package is an executable, if you want to distribute Altergo or a very simple tool like that, you don't need to have any dependencies. Unless what you are interested in is the library. So currently, almost well, of course, since OPAM is a source package manager, most dependencies are not tagged, and so they are not tagged as only build dependencies, which is well, maybe we have to find different tags for dependencies, some of them for source packages and some of them for binary packages, so that when we infer the binary dependencies, then we can correctly remove the ones that are not useful, so that the set of dependencies should be as small as possible. I'm not sure, I don't know if it replies to the question or not.
Anil, if you want to add something on the answer. And I have a question about the binary repositories. Are they signed, or there is a plan to check to check there is no man in the middle when you get the binary from a repo and when you upload it from OpenBean?
So there is the mechanism provided by OPAM, since it's a standard OPAM repository. So that there is nothing more done. So you have hashes in the OPAM package, OPAM files, and then when you OPAM checks that the binary archive that is downloaded corresponds to the hash, but otherwise we don't have any clever mechanism to edit the repository with signatures and so on. I assume that something that is going to be done at some point in OPAM. Well, there are already things that have been done and are in progress, so I expect them to be useful for OPAM bin.
Okay. There is a discussion on June as a build dependency on the chat. If anyone have another question. So we can thank Fabrice for the talk and all of them for the work.
Thank you.
Thank you. And we will go to our last talk, which is Steven de Oliveira will present Love, which is a language for smart contracts.
My name is Steven de Oliveira. This talk is about the Love smart contract language developed at OCaml Pro. I will start this short talk by an introduction of blockchains. A blockchain is a tool for independent and untrusted users who will work on the same network. Their goal is to agree on how to order a flow of messages, and this must be done as quickly as possible. Even though they are not trustworthy, they must not rely on a third party or centralized authority to agree on the message's order, because all users, especially third parties, are considered not trustworthy. In order to do so, every user has a copy of the chain. They all work on their own data and share it under a given consensus protocol. Emitting and validating a message on the chain modifies the global state of the chain. In the case of cryptocurrencies, messages are usually called transactions or operations, and executing a transaction modifies the balance of the sender and receiver. As everyone has a copy of the data and must agree on the validity of the transactions, cheating can be prevented. For example, it prevents double spending, which is the process of spending twice the same token. So modifying the state of the chain is a thing, but a more interesting approach of blockchain is not only to provide modifications per se of the chain state, but to provide a pseudo-user allowed to modify the state just like a real user would, but whose behavior would be encoded in logical and public rules. This is what a smart contract is. A smart contract is basically an algorithm deployed on the chain by any user, and it will act just like any other user on the chain. It has a balance, it has a memory, and it has logical rules on how to handle transactions it was sent, on how to modify its own memory, and how to emit transactions. Everyone on the network has a copy of the smart contract code in its memory, which means that everyone can replicate the execution and update its personal data accordingly. While the consensus protocol allows users to agree on how the chain modification must occur, smart contracts are defined by users, and as we said, users are not trustworthy. That's why smart contracts must be auditable. There are two kinds of smart contract languages. First, there are low-level languages that are executed on the chain, like Michelson for Tezos or the EVM for Ethereum. As contracts in such a language are executed on the chain, any proof on their code will be a proof of what actually happens on the chain. The issue is that the level of expertise required for even reading such contracts is much higher than the expertise required for writing them in a higher level language, which is the second kind of language used in blockchain. While they are easier to read, specify, and verify in general, they must be compiled to a lower level language that the chain will be able to execute. So our objective was to get rid of this constraint by providing on the chain the interpreter of a high-level language. So with Love, we wanted a high-level WYSIWY language. What you see is what you execute. We wrote it in OCaml for several reasons. Tools for developing a language, from a parser to an interpreter, and all the logic in between is mature and secure in OCaml. Also, as we targeted WYSIWY, we preferred to use the language already used for the blockchain protocol, which was OCaml. In Tezos and Dune, the chains initially targeted by Love, smart contracts are written in Michelson. We wanted our language to be at least as expressive as Michelson, but we also wanted to have decentralized libraries. Libraries are contracts with no storage, but only pure function. That's why we needed polymorphism. And in the meantime, we wanted to avoid a type inference. The idea is that inferring type is harder than just checking if they are correctly provided. Also, we did not want two semantically equivalent programs, only differing in their type annotation, to be checked differently. Having a strongly typed language with no type inference led us to use the systemf type system, just like the Scila language. Love defines several built-in types. Integer and naturals are embodied arithmetical values, preventing overflows. As there is no operator for subtracting two naturals and that would return a natural, it also prevents underflows. Operations are the messages. They can only be generated by the primitives of the language, and they work as black boxes. Addresses have their own type, different from integers, so there is no arithmetic on on addresses. Love provides multiple collection types similar to OCaml's, plus a big map system that is proper to Tezos and Dune. It has tuples, functions, and the main component of systemf, the for-all type for polymorphism. In this demo, I will present what a Love smart contract looks like by implementing a voting algorithm. So Love contracts are built from two components, type declarations and values. So for voting systems, we'll need a type vote, which will be either a blank vote or a vote for someone. Then we'll need a type for the memory of the contract, what will be stored. So let's say type storage equals votes of type address map vote. Vote, and an end of vote, which will be a timestamp. So the type storage is actually a reserved keyword that represents what specifically the contract will save in its memory. There will be no actual value of the storage in the contract. All we know is its type. So we need three things now. We need a way to initialize our contract, a way to read it, and a way to write it. So first, let's see initializers. So there can be at most one initializer in a contract, because you can either initialize it with the actual value or through this function. So this function is called storage and takes one argument of any type. So let's say the duration of the contract. So we need an empty map for the votes, map.empty. So map.empty is actually a function that expects two arguments, which will be the type of the key and the type of the binding. Here is the type of map.empty. For all key, for all binding key binding map. So in order to fulfill these two constraints, we need to set that the key is an address, the binding will be a vote, and now we have an empty map of address to votes. So now we have the end of vote, which will be current.time plus duration. So this is an operator for adding timestamp and natural, because as we said in love there is no type inference, so we have one operator for each arithmetical values. And now we can return the storage and of vote. So the initializers return a value of type storage, which will be used as the first storage of the contract. Alright. So now let's see how to access the storage. So to do so, we'll define a view. So a view, let's say getVote, takes at least one argument of type storage and any number of argument of any type. So let's say here a voter of type address, and we want to return the actual vote of the voter. So he may not have voted already, so let's say that it's a vote option return type. So when you call getVote, you won't actually need to provide the first argument. It will be replaced during the execution by the current storage of the contract. So if we consider that storage is the current storage, we just need to access the map in the variable. So as for empty, find expects two arguments, address and vote, plus the voter and the map. So here the view takes an address and returns a vote option. The storage is just replaced by the current storage. Now let's see how to update the storage. And to do so, we'll introduce entry points. So entry points with initializers are the only functions and values of the contracts that must be accessed with a transaction. So you will send a transaction, for example, for voting, and this will trigger the execution. So just like for views, it will have a storage argument that will be replaced by the current storage. There is a second argument representing the number of tokens sent in the transaction invoking the entry point. And we'll have an argument of any type, so here let's say a vote. And now let's vote. So we need a new storage in which the new vote is added. But first we have to check that the vote hasn't ended yet. Otherwise, we want the execution to fail. So if current time superior to storage end of vote, then so this operator is polymorphic, so we have to specify its type. Then fail with is also polymorphic. We don't know the type of its arguments, so let's say we want to fail with a string. Voting already ended. And the return type of fail with also is polymorphic. So we'll say that it's unit. in, and now we can set the new storage. So let voter equals to current sender. In, let new storage equals storage with votes. Add. As for empty and find, we need to specify the types. Voter, vote, and storage dot votes. So if you're familiar with OCaml, this syntax won't be much of a problem. And now an entry point actually returns two values to return a list of operations that will be put on a heap to be executed after the current execution. So here we don't want to generate any operation, so an empty list. And the new value of the storage. So this second element of the tuple will simply replace the current storage if the execution is successful. Then, as I said, all the operations in the list are put on a heap to be executed after. If any of them fails, then all the executions fail. So this empty list is polymorphic, so we have to specify its type. This is an operation list. And now we have an entry point that expects a vote. And that's it. To briefly conclude this talk, we compared the love contract implementation size on the chain with their Michelson equivalent. The bigger a contract is on the chain, the dearer it is to deploy in terms of CPU, but also in tokens, because the actual cost of deploying a contract is proportional to its size. That's why optimizing their size on the chain was one of our priorities. Love contracts are about 60% smaller, hence 60% cheaper to deploy than Michelson contracts. One main drawback is that they are in general dearer to execute. This is mainly due to the storage serialization that is expensive when the storage is a record, because records hold strings for identifying the different fields. This cost is reduced by replacing records by tuples. In the future, we want to continue our optimization on gas consumption, especially when deserializing storages. Identifying efficient coding practices that would optimize love contracts is one of our targets, as well as introducing tail calling in recursive function. We would also like to extend the language with cryptographic primitives for zero-knowledge proofs, and also extensible records and pattern matching exhaustiveness. Thank you for your attention.
Thank you, Stephen. Hi.
Hello.
So if there is question, you can use the Q&A tab. Well, I have a question about the high-level language for smart contracts. Yesterday we saw an example of liquidity, which is a high-level language over Michelson 2. So what are the difference and why this new language?
Okay, so first of all, liquidity is not executed on the chain. It must be compiled in Michelson, which is one of the issues we wanted to solve. Actually, we had liquidity, and we wanted a sort of liquidity that would be directly executed on the chain. So that's why we went in that direction. Also, another difference that were mostly in the older version of liquidity is that there were no views and pure function because there were not such no such things in Michelson in the past. So that were the main difference between the two languages.
Okay. And on the smart contract themselves, what are the kind of smart contract that you deployed, if you have deployed some?
So yeah, in Dune we deployed a few contracts for a playground, which was a service for playing multiple games. The idea is not the games in themselves were not the most interesting part. It was more like the framework where everyone could contribute to add their own games and their own frameworks to play something. So that was maybe the biggest project that we had with Love.
Okay. We have some time if you want to point out something that you didn't have the time on the talk.
Like this, I'm not sure what would be very interesting for the audience. Maybe leaving a little sooner would please everyone. I don't know. If anyone has questions, we have some time now.
Yeah, maybe we can share on the chat the link to the documentation or the main website of Love.
Yeah. So, is there? Will the slides be shared? Because I can send them with all the links in. But let me.
Yeah. Yeah, you can send them the slide and we'll make it available on the website of ICFP. So yeah, on the last
great.
We have other links. Okay. So thank you, Stephen. You can thanks, Stephen. And we can end up quite early this session. I have more time break, and the next session will begin at 6:30. So see you later.
Hello, everyone. I hope everyone's having a great day or night, depending on where you are. Welcome back to the second to last session in the OCaml workshop. My name is Ashish. I'm chairing this session, and I'm pleased to introduce our first talk, which is by Dandor Licker and Timothy Jones from the University of Cambridge. Their research centers around Duplo, which is a framework for post-link optimizations of OCaml programs. And in this talk, titled From 2n+1 to n, they will be discussing one of their optimizations. So we'll go ahead and start the video now.
Hello, my name is Dandor Licker, and today I am going to talk about work I have done under the supervision of Dr. Tim Jones at the University of Cambridge concerning the integer representation of OCaml. As part of my degree, I am working on a Duplo framework to perform whole program optimization on applications built using both OCaml and C. This talk is concerned with the integers and pointers of OCaml. Relying on a type-agnostic representation, the language allows identical locations to refer to both integers and pointers, distinguishing the two using a tag bit. In the compiler and code generator, the val type is used to identify such locations, aliasing integers with pointers. However, instances exist where the type can be disambiguated, proving the location stores only pointers or integers. In such cases, 63-bit integers represented as 2n+1 could be converted to n, possibly improving performance. Duplo lowers OCaml sources and external C components, including the runtime, to a low-level intermediate representation, abbreviated with LLIR, applying a wide range of transformations in addition to the optimizations already performed by the high-level OCaml compiler. We will discuss the complexities of a type analysis implemented in Duplo that disambiguates pointers and integers aliased by the value type. The analysis was built primarily to distinguish overloaded instructions, reducing the problem size for points-to analysis. In addition, we have noticed that simple people transformations can be built relying on type information, improving performance. Similar transformations could be performed in the OCaml compiler instead, without necessarily requiring another analysis, exploiting high-level information by simply improving the granularity of types carried by the compiler. While our transformation has its uses at the stage it operates at, we also argue that similar information could be used earlier to improve performance. We are first going to talk about why tags are necessary in OCaml. The need for them originates from the type-agnostic object representation used by the language and its runtime. Heap-allocated blocks are composed of a header describing the size and type of the object, followed by a set of fields of fixed size. The fields can store either integers or pointers. To distinguish the two, integers are 63 bits in size, with the last bit always set to 1. N is represented as 2n plus 1. Pointers end with 0, as allocations are aligned to an 8-byte boundary. While such a scheme is advantageous, since the heap can easily be traversed during the marking phase of the garbage collector, in practice the val type is often used to classify integer-only registers, preventing optimizations. In the OCaml compiler, information is lost during the generation of CMM due to ambiguities in the CMM types. At a minimum, types solely for odd integers and heap addresses are lacking, with the value type confusing both of them. Heap addresses can further be refined into function pointers, lazy pointers, infix pointers, and others, although all information is lost. The information which can be retained can enable additional transformations. For example, tag checks on pure integer or pointer types can be folded at compile time. Registers storing integers alone can be omitted from the metadata blocks required by the garbage collector. Knowledge of the parity of values can power people optimizations, ameliorating the overhead of tagging and untagging. The presence of these additional instructions is ubiquitous. Since an integer n is practically represented as 2n plus 1, it must be packed whenever necessary using a shift and an AND or instruction, and unpacked through arithmetic right shift, preserving the stand bit. Regular arithmetic operations also incur an additional cost. A simple addition must adjust the tag, requiring a decrement by 1. Analogously, subtraction involves an additional increment. If it is possible to prevent tagging, the cost of arithmetic operations can be reduced as the adjustments through increment and decrement are no longer necessary. The overhead also occurs in performance-sensitive constructs, such as loop counters. Counters are typically incremented by 1 during an iteration, although the increment operation needs to adjust the number by 2 in order to maintain it in its properly formatted form. On newer AMD 64 processors, succeeding Haswell at least, increment is encoded in fewer bytes than addition by 2. While the redundancies are minimal, instruction cache performance is crucial and every byte saved counts. Furthermore, the simplification of counters might facilitate further loop optimizations, including strength reduction. Relying solely on information from the OCaml compiler provided at the moment, redundancies cannot easily be eliminated. For example, if a comparison orders 2a plus 1 and 2b plus 1, it might be tempting to replace the operands with a and b. Unfortunately, the tagging instructions eliminate the most significant bits of the originals, and it must be shown that both had identical leading digits. It is not always necessary to change the format of integers. Often it is enough to change the type of a register to improve the program. If it can be shown that the value is always a tagged integer, the type of register storing it can be changed to int from value. This enables a wide range of transformations. While typical address calculations cannot easily be moved around the program, integral registers are immediate candidates for loop invariant, code motion, and common sub-expression elimination. Additionally, integer-only registers can be hidden from the garbage collector, improving its performance. We can now look at some redundancies present in OCaml programs originating from the use of the standard library. In this LLIR code snippet, we see a comparison between an integer and a constant. The integer is produced by an add instruction, which is required to tag the value or adjust the number after subtraction. The code should be optimized, removing the addition and decrementing the constant by 1 instead. Unfortunately, in LLIR and on hardware, arithmetic instructions operate modulo 2n, so if the register contained the maximum integer, the addition would wrap it to 0. If the addition is omitted, the direct comparison returns the opposite results. Relying solely on the semantics of LLIR instructions, the transformations cannot legally be performed. However, if it is known that the original register contains an untagged even value, the addition of 1 to an even number is known to never wrap around, and the transformation can be performed. Besides comparisons, issues also occur when lazy values and the blocks marked with a forward tag are present. The virtual register with number 5 initially contains a heap pointer, and it might be tempting to fold the check of the last bit to false, since heap pointers are always aligned to an 8-byte boundary. However, a call is present prior to the use of the pointer. The collector can be triggered, and the lazy value can be resolved to an integer, which passes the test. This example highlights the clear need to distinguish lazy pointers at the IR level, as they exhibit different behavior compared to regular pointers. The previous examples showed that optimizations can be performed if more accurate type information was available, distinguishing the various kinds of values used in the compilation and execution of OCaml. A classification should go beyond delimiting pointers from integers, as the structure of both integers and pointers is relevant. Knowledge of even and odd numbers enables people optimizations. A clear classification of pointers is required in order to avoid applying transformations allowed on regular heap pointers that would break the behavior of lazy or infixed blocks. The required information can be obtained in two ways. It can either be generated by the compiler frontend, or it can be inferred. Due to necessity, we are going to discuss an inference method built into Duplo. However, we strongly advocate for the use of the former approach inside the OCaml compiler. Type inference on machine code is not a new topic. Both abstract interpretation and constraint solving has been used in the past. Unfortunately, neat unification-based approaches no longer apply, as types must be determined based on a set of values that can be assigned to registers. Prior methods are not particularly precise, especially on OCaml programs which contain a large number of indirect function calls, hindering the efficacy of interprocedural methods. The type inference method built into Duplo is centered around the full lattice shown here. LLIR, similarly to OCaml, does not implicitly distinguish pointers from integers. A virtual register as wide as a native pointer width can store both integers and pointers. At such a low level, the notion of types is also blurry. The elements of the lattice are effectively sets of values. If it can be shown that all values that can be assigned to a virtual register are integers or pointers, the register is typed as an integer or a pointer accordingly. The top to bottom ordering indicates subset inclusion. For example, all function pointers are considered to be valid heap pointers. The top element is the set of all 64-bit types, including pointers, OCaml pointers, values, and arbitrary integers. While the lattice can distinguish heap pointers from derived addresses, it cannot identify lazy or infixed pointers, assigning them to the generic heap classification instead. As a consequence, the transformations allowed by the heap type are somewhat limited. Initially, inference relies on a forward data flow analysis to approximate the set of values computable by instructions, assigning an initial classification to all virtual registers. This is a fairly regular interprocedural forward data flow analysis, reason why the lattice has a topmost element and pairs of types admit a least upper bound. Unfortunately, propagation is not particularly accurate, as the heap is not modeled and the types of load instructions are over-approximated with top. While the algorithm does identify a minimal solution, inaccuracies originating from memory loads and externally visible function arguments are ubiquitous. Overall, the results of this analysis on its own are not satisfactory. To remedy deficiencies, we rely on a backward pass, which converges to a local minimum starting at the least upper bound identified by the prior step. The intuition is simple. Instructions are not allowed to produce invalid values. As an example, we consider a simple function which receives an argument over-approximated to top, storing a pointer or integer. The argument is used as the address for a load instruction. If the argument is given an integer value, the program fails as arbitrary integers cannot be dereferenced. As a consequence, the argument can be typed as a pointer, narrowing the type and improving the classification. Refinement depends on the paths between definition and its uses. In principle, invalid values are not allowed to reach use sites that might result in illegal behavior. If all paths from the instruction building a value reach the use imposing a constraint, more precisely, if the use post dominates the definition, the type can be refined. Due to the post-dominance relationship, there is no path from the definition through which a value of an alternative type could exit the function. It must unconditionally reach the use and fail. In this particular case, the type of the register produced by the load is narrowed to a pointer. If not all paths lead to a specific use, refinement cannot happen at the definition site. If the load produced an integer, execution could bypass the second load without leading to illegal behavior that could warrant refinement. However, the block between the use and the definition is unconditionally reaches the use. If execution reaches it, at that point the virtual register must contain a legal value. The block on the path is a successor of the nodes on the post-dominance frontier of the use. Such nodes are the earliest ones in the graph which post-dominate the use sites. To represent refinement, the ranges of registers are split by adding no-op moves at the boundary, which are assigned the refined types. The use of post-dominance frontiers also ensures a minimal number of splits. A third rule involves split points. It might be possible that an individual use does not post-dominate a definition. However, there is a use narrowing the type to the same refined one on all successors. In this example, the type of the load is refined to a pointer type on all paths. No matter which path execution continues on, a pointer type is expected. Since execution cannot continue from the block onwards with an integer type, the refinement can be brought forward and it can be assumed that the type is a pointer type in the split point itself. Similar refinement rules can be applied to function arguments as well. If a function expects a pointer argument, all call sites that are direct calls can be refined to such a type, as the invocations with integral types would result in an error. The same cannot be applied to the values returned by a function, however, due to polymorphism. Even if one call site expected the function to produce a pointer, another might return an integer, and no refinement from the top type is possible. Due to the information about even and odd numbers, the transformation involving a comparison with a constant can now be performed. On AMD processors, micro-benchmarks indicate substantial improvements. Eliminating the addition by 1 can result in a 16% improvement in performance measured on the AMD Zen 2 microarchitecture. The latency of the tagging and untagging operations is occasionally hidden or eliminated by the hardware. However, in some instances the penalty is still paid for spurious shifts and adjustments, and eliminating even these simple instructions can result in benefits. In Duplo, we have built a minimal transformation to show the performance improvements are achievable. Unfortunately, performance improvements are orthogonal to our goals. People optimizations are useful, although secondary, as the focus lies on exploiting interprocedural information. Type information is most useful to distinguish instances of overloaded operators in Duplo. As an example, an add instruction can either perform integral or pointer arithmetic. Proving the instruction must operate on integers is beneficial, as it can reduce the problem size for points to analysis, which can omit the operation from their constraint systems, if relying on one. The analysis in its current form manages to demote 7% of the value types to pure integers, which also results in 2% less recorded roots. While the impact on performance is minimal, a 7% decrease in the problem size for a cubic complexity algorithm can yield a speedup of 20% in compilation types. However, we can still talk about ideas to further improve runtime performance. Tag elimination is effectively an optimization problem. Tagging and untagging operations are still required, as all integers written to memory locations or loaded from objects must be properly formatted. Additionally, arguments of functions called indirectly must also be tagged. A transformation should identify the optimal conversion points, guided by profile information that allow the highest number of intermediary arithmetic adjustments to be eliminated. Such a transformation can potentially yield a more significant benefit, as redundancies of this nature are observable in the implementation of several methods from the standard library involving explicit loops or Terry recursive functions, particularly ones on strings and arrays. While the type inference method at the LLIR level is sufficiently effective, better information could be obtained inside the OCaml compiler. First of all, the translation to CMM should not lose valuable types, particularly ones that cannot be identified at a low level. For example, lazy pointers are incredibly difficult to pinpoint on LLIR. Loads from the heap seem to constantly compile to the value type. This can trivially be narrowed to integral ones in quite a few instances. If the lowering produces accurate enough information, interprocedural analysis could be avoided altogether, saving an expense. However, sufficient transformations, including inlining and specialization, might reveal some optimization opportunities at the OCaml level as well, thus the possibility of rerunning the type analysis at some earlier stage should not be discarded. At this point, however, we can suggest only one action: refine the CMM lattice to better represent special values. Knowledge of signedness is important. Most arithmetic is signed, however, it will be valuable to know where unsigned partial results might originate from. Similarly, knowledge of parity is helpful for optimization policies. In the realm of pointers, the lattice on the left could do with some more granularity. Function pointers, lazy objects, and heap allocated objects are all assigned a value type, but their semantics are widely different, and optimization policies must rely on the most strict ones. Finally, objects have special tag fields, which are unpacked through a series of instructions. Occasionally, it might be valuable to know which instructions have computed these values. To sum up, we have shown the type analysis and the type system the transformation Duplo relies on, and we hope to have presented some evidence showing that even at the low level, type information can be exploited to improve both the compiler and the resulting binaries. While our use case in Duplo is narrow, we hope to have presented evidence to warrant a further investigation into improving type information inside the OCaml compiler to perform optimizations well ahead of reaching LLIR. Thank you for listening. Hello.
Hi, Nandor. Great. That was a great talk. Thank you so much.
Hello.
We do have a question from the audience. It's from Edwin Turok of Citrix. And he is asking if this optimization you presented can be done on other integers also, if you can prove it doesn't overflow.
I think that falls in the domain of separate analysis. So the transformation we presented there was the simplest one that was implementable based on the information available from this analysis. So otherwise, if another analysis reasoned about the bounds or intervals or integers can be placed in, then sure, overflowing operations could be simplified. It's just not with the current lattice, because in our implementation we model integers as bit masks, and we don't have an interval model in parallel.
Okay. Well, Xavier is asking a question. He says wait for it to post. He says he's now convinced that we should have used 2n for integers and 2n plus 1 for pointers, or even 8n for integers and 8n plus 1 and 7 for pointers. Would there still be a need for the kind of analysis and optimizations you presented?
In the way, yes, because the problem of using the value type to denote both integers and pointers is still there. And the main goal of this analysis is to identify registers which are either integers or pointers. And it doesn't matter what the integer representation or the pointer representation is, the valuable end result is being able to distinguish the integers from the pointers.
Another question from Victor Kuchta is, do you have a prototype implementing these changes in CMM? And I think a related comment I also saw was, can other people test this out right now in their own code?
Well, they can test the Duplo framework out, but we do not have an implementation in CMM. So the thing is that this analysis in Duplo is isolated to a single transformation, but inside the OCaml compiler, it's a representation problem, and changing the CMM, Mach, and linear representations involves a fairly that would be a fairly intrusive change, unfortunately.
Okay. anticipate it being possible to incorporate these kind of changes or optimizations directly into the compiler?
So I don't think that's a question for me to answer. In Duplo, there is certainly value in disambiguating integers from pointers, and we presented some examples where having more accurate information about the value stored in registers is helpful. But I think further benchmarking is necessary to show that such an intrusive change in the OCaml compiler would be worth the performance benefits from the people optimizations or from any other kind of optimizations that would be enabled.
Another question from Edwin. It is, give me 1 second. So could you pretend to have 2x registers, n integer and n pointer, and then worry about allocating them to true registers later on?
So understand this as having some kind of machine where we have one set of registers storing integers and one set of registers storing pointers. But compiling OCaml itself to such a machine would be quite interesting, as we can take a polymorphic function, for example, or we can just take an algebraic data type, and then it needs to represent one constructor can allocate a heap block with some elements, and then another constructor could be a scalar, which means that if this type is used as argument to a function, then that argument on one call is invoked with an integer and another call with a pointer. So if we have probably have an issue of having to use the integer registers. The integer registers would have to shadow the pointer registers implicitly, I guess, and then maybe on such hypothetical computer, if there's no need for some registers to shadow. So if there's no need for some registers to shadow others, then the remaining registers could be better allocated to only integers or only pointers.
Okay.
I might have misunderstood the question. But, yeah.
Okay. I saw a thumbs up, though I can't tell if that was from the person that asked the question. So, what's the long-term potential? Do you feel, is it a goal to be able to compete on numerical programs with other languages such as C or Fortran that traditionally are used?
So I think that my main motivation for implementing this was that OCaml, when compiled, contains code patterns that I don't like to see in binaries. So, for example, in the string.index function, what we see is that we have an index that's incremented twice in every iteration, and then it's divided, and the index is divided on every iteration. So effectively computing 2n plus 1 and then dividing it by 2. It kind of feels like this hinders other transformations. So, for example, if we wanted to do like strength reduction, then this transformation would be prevented because the index isn't immediately noticeable, or detecting the index itself is more complicated than it should be. So I think the main value of this transfer of such a canonicalization would be to just bring the IR in a simpler form that allows for other optimizations. But,
okay, great. We do have about a minute or two, so I'll just give people a few seconds maybe to ask another question if anyone thinks of one. Otherwise, we can. Okay, I don't see any more questions coming in. So how about we thank you very much for your great talk, and we'll see you hopefully next year in person.
Thank you. Goodbye. Goodbye.
Great. So I'm going to go ahead and introduce the next talk. I want to make sure our air meet is working. Give us a second.
Can I disappear?
You probably can. I think, yeah, our co-host, there we go. Okay. I think our co-host dropped out and came back, so I hope it's working out. Great. So our second talk is by Baras Bandari and Leonidas Lampropoulos from the University of Maryland. They're going to present a talk titled Property-Based Testing for OCaml through Coq. And this is inspired by some work. So the Quick Check library that is well known from Haskell, there's a port of it called Quick Check in Coq, which is also widely used. So they'll be talking about how we can leverage that as OCaml programmers. And we'll go ahead and start that video now.
Hello everyone, I'm Paras, a master's candidate at the University of Maryland's Computer Science Department. This will be a presentation on a tool that I and Leo developed to further support property-based testing in OCaml through Coq. Property-based testing is a popular testing technique used to ensure that a program conforms to an executable specification. In property-based testing, users write properties of a program under test, and the tool is in charge of generating a large number of random inputs. These inputs are executed with the property, and if a counterexample is found, the counterexample is minimized and reported to the user. Some popular libraries for property-based testing include QCheck for OCaml, QuickCheck for Haskell, and QuickCheck for Coq. As an example of property-based testing, let's take a simple function called reverse that takes a list of integers as input and returns the list reversed. For this function, we can define a property that checks if the length of the original list is equal to the length of the reversed list as shown. In fact, we would expect this function reverse to be validated against this property. In this case, a property-based testing tool would generate random lists of integers and run the property test prop reverse with these randomly generated lists until the property test fails or a sufficiently large number of inputs have been validated. But how are lists of integers generated? Generators for primitive types such as lists are usually supported by default. But what about user-defined types? Take for example a common data type tree. The code here shows a generator for a tree data type in OCaml. The details of the generator don't matter much. There is a bounded recursion given some size and a choice between generating a leaf or a node recursively. What matters is that users have to write this boilerplate. Worse, as properties get more complex, so do generators. Naturally, one wonders whether we can automate this process of getting generators for data types. The good news is that many property-based testing libraries provide this kind of automation. QuickCheck, for example, which is a property-based testing library for Coq, provides this kind of automation and quite a bit more, having a lot of work and research poured into it. The example in this slide shows how simple it is to derive a generator for the tree data type using QuickCheck. Define a data type in Coq and use the derive statement to get the generator. As a bonus, this also gives a minimizer and a printer. Now compare this to the code example in the previous slide of a manually written generator for a tree. As you can see, QuickCheck's automation makes it simple to derive generators for data types. Rather than replicating this effort for OCaml, we sought to see if we could reuse it and leverage QuickCheck's features to perform property-based testing for OCaml programs. Given an OCaml file containing the target program and the property test, we parse the file to get the input types of the property test. If these input types are non-primitives or user-defined types, we parse the OCaml file to get their type definitions in OCaml and convert these type definitions to Coq using the Coq of OCaml library. The Coq type definitions are then used to define the data types in a Coq script and derive generators for them, as we saw in the previous slide. Finally, the property test is extracted from the OCaml file into the Coq script and executed using QuickCheck. Let's look at each step in more detail. The setup consists of an OCaml file containing the target program, in this case mirror tree, which is a function that takes a tree as an input and mirrors or laterally flips the tree. The file also includes the type definition for the data types used in the target program as inputs, which in this case is just the tree data type. And finally, the file includes the property test called mirror property test, which states that the mirror function is involutive. That is, applying it twice yields the original tree. The OCaml file is parsed using regular expressions to get the types of the inputs to the property test. In this case, the only input is of type tree. Since the type tree is a non-primitive user-defined type, we parse the OCaml file to get the type definitions for tree. As you can see on the right-hand side, we have the OCaml type definition of tree here. The type definition is converted to coq using coq of OCaml. The code on the right-hand side is the coq type definition of the tree data type. In the last step, we construct the coq script, which contains some basic imports, coq type definitions that were parsed in the previous step, and the derive statements used to derive the generators and minimizers for the data types. We then hijack the extraction mechanism to make sure that when QuickCheck generates trees, they will be using the OCaml definition, and when QuickCheck executes the property, it will execute the OCaml property. The only code that is then produced from coq is the generators, printers, minimizers, as well as the glue code that puts everything together using type classes. Finally, QuickCheck executes the property test and reports any errors to the user. So I will be giving a demo of the tool we developed for property-based testing in OCaml through coq. We have two files here, file.ml, which is the file open on the left-hand side of the screen. This file contains the target program, which is, in this case, the mirror tree function. This function takes a tree as an input and laterally flips the tree. It contains a bug currently just for testing purposes. This file also contains the mirror property test, which is our property test that takes a tree and checks if applying the mirror function twice yields the original tree. And we are expecting this property to be validated. So I'm going to be running this executable here called OCaml QuickCheck. This is the executable of the tool we developed. So it takes two arguments. The first argument is the name of the file, which here is file. The second argument is the name of the property test. So running this executable with these two arguments, it generates a file called coqscript.v. I'm going to open this file, and as you can see, this file contains the coq script that we will be executing finally to run the property-based test. It contains the basic imports. It contains the type definitions of the tree type. It contains the part where we extract the structure of the tree data type. It contains the derive statements for getting the generators, minimizers, and printers. And finally, we extract the property test here from the OCaml file and run the property test using QuickCheck. So we're going to run this coq script now using the coqc command. So you can see on the terminal, the property-based test is running here. Here you can see that the test has failed after 4 tests and 3 shrinks. And it has also given us the counter example, which caused the test to fail. So I'm going to go to the file on the left, the file.ml. And in this case, the bug was that I forgot to add the recursion to one side of the tree. So I'm going to go here and add this recursion. So the bug should be fixed now. And I'm going to run the coq script again. And as you can see, this time the property test is passing. Thank you.
Great, thank Paras for that nice talk. Just wait for Leo. And is Leo handling the questions? I'm not sure if Paras is also joining.
Yeah, I am handling the questions. Paras was unavailable today.
Okay, great. Leo, thanks for that wonderful work. We do have a question from the audience. This is from Rudy Matella, and he is asking, he's first of all saying thanks for the great talk, and he's asking, you chose to use coq's QuickCheck to reuse its generators, but what would be the advantages or disadvantages of implementing it directly in OCaml?
Yeah, that's a great question. So the main thing I would say is that the main advantage is you don't have to re-implement the automation. That's it. That's the main thing. As a secondary advantage, I would say is that for the things that we showed here, just basic data types, it wouldn't really be hard to just re-implement the whole thing. But QuickCheck has a lot more support in terms of like some fuzzing stuff in the style of in a slightly different style than Crowbar, and has support for deriving constraint generators. And those things would be way harder to re-implement in another language for an entire new framework. So I would guess the second part is reuse the more advanced automation and also be able to benchmark everything that we do in QuickCheck against existing tools in OCaml, because they follow the same approach. They run on the exact same system after extraction. We should be able to benchmark against one another, but that hasn't happened so far. And instead of doing it by hand every time, we just wrote a tool to automate that process.
Okay. Great. And he also has a follow-up question. And he's wondering if you're aware of the QCheck library, and how does your tool compare to it?
Yeah, so QCheck, basically the examples I show that were shown at the very beginning of the talk, they were QCheck. The generator for OCaml that was handwritten was QCheck. And I hate writing those boilerplate generators. I'm not aware of any work that automates QCheck generator derivation. It might exist. I'm not sure how we would even go about writing it, but it shouldn't be too hard once you get a representation of the AST. But again, just like I said before, the main attraction of this is not, oh, QuickCheck is better, is it already has all this automation support. How can I avoid duplicating all the effort that has been done?
Okay. And how about Crowbar? How does this compare to Crowbar?
Yeah, so again, it's one of those things that it has an amazing, Crowbar is an amazing tool. I was talking about it with Steven, I think, back when things were in person. And Crowbar is a fuzzing tool for OCaml programs. QuickCheck has a variant of FuzzCheck, which is a fuzzing tool for Coq programs. And there's one slight difference in that Crowbar fuzzes the randomness that comes as an input to your generators, while FuzzCheck fuzzes, mutates the actual semantic inputs that come out. And when we did some experiments with FuzzCheck, we re-implemented Crowbar on top of QuickCheck, and it just didn't work well. But I think that was not really a fair comparison because they are good at different things. So, for example, Crowbar, if your properties are sort of structural properties that have inputs that are records and have like a field date, a date field, and an integer field, and a float field, where you can basically read a bunch of bits and just parse them into an input for your program, then Crowbar should blow QuickCheck out of the water because it's a one-to-one correspondence between your binary inputs and the generation. On the other hand, if you have much more structured generations, say, for example, well-typed lambda terms or something like that, where flipping a bit of randomness could turn your tree from something from a beautiful well-typed term to a completely unreadable garbage, then fuzzing the random bits is not really as effective as before. And this kind of work is just going to give us a way of evaluating these kinds of things where we couldn't before.
Okay, so you see space for all of these different tools to be used.
Yeah. So I think that QuickCheck, just like QuickCheck itself, is a library that is much more focused on how can expert users write generators, and all the automation has been built on top of it in the form of what if an expert user could be automated. Crowbar and some other tools like Python's Hypothesis are usually much more geared to let's get as much, make it as easy as possible for people to just use it out of the box as is. And there is definitely space for everything in that regard, and it's just a matter of being able to compare both against each other to figure out what to use when.
Okay. A small technical question. The talk mentioned using regular expressions to pull out type definitions from OCaml files. Would it any reason not to just use compiler libs and get the parse tree out?
So I think that was mostly just a choice made out of expedience, because that was just easier to do. I think it makes it much less robust. So I think that the next step would be to, once we encounter a problem with using regular expressions, which will probably happen if we play it with it more and more, I'm assuming that we're gonna end up using the Coq of OCaml library and use its parsing and typing facilities. But this was just a quick proof of concept in order to facilitate some benchmarking. And it seemed to be working pretty well. It's like extremely robust in a few things. You can do nested data types and nested user data types. It extracts everything so far. But if we ever hit a point where they don't work, as you say, it's probably better to just reuse facilities for typing and parsing.
Yep. Okay. Okay. We do have a few extra minutes. We're kind of running early. So if there's any other questions from the audience, please go ahead and post them to the Q&A. I'll just give a couple seconds to see if we get any more questions. And while I'm waiting, just one other, I guess, comment about reusing tools built in Coq. I guess from a lot of times in production use cases, people are concerned about extra dependencies, and it's just a little nicer if everything was just one little simple library they just installed from OPAM. I assume that's not a concern yet, but if you wanted to get to that level of usage, is that something you'd think about?
Yeah, definitely. So if at any point this was, again, as I said to Rudy's question, the my main concern was not showing how OCaml people would greatly benefit from only using QuickCheck. It's more of a way of linking the two worlds and being able to use both things and pitting them one against another. If it turned out that using this kind of the QuickCheck-based stuff is more interesting or more useful, then it might be worth re-implementing specifically for OCaml, because like a lot of the support that QuickCheck has is in terms of, okay, if you have an inductive relation written in Coq, I can generate stuff that directly satisfy this inductive relation. In OCaml, you don't have inductive relations, but you have types and you have properties written in OCaml. So maybe there is something to be done by targeting those directly, but that would have to do a whole bunch of work recreating what we have for QuickCheck underneath the hood.
Okay. We did get one more question from the audience from Peter Rukdal, and he's asking if Coq's QuickCheck is written in Coq, and if it is, can it be extracted to OCaml?
Coq's QuickCheck is written in OCaml. Like everything is done in OCaml underneath the hood. Randomness is obtained by extracting to OCaml. All the automatic generation and derivation is written in OCaml. Nothing. I would not even consider writing something like that in Coq. I'm not crazy. But the point here is that the meta facilities are targeting Coq data types. So it uses the OCaml representation of a Coq AST in order to generate everything. Not really an AST, the inductive type representation it has. That could probably be retargeted to OCaml if you're targeting the same fragment, or they could be some underlying embedding. But it's much easier to do this source-to-source transformation at this point, because the only thing we need for this kind of thing is types, type information. I don't care about the property. I just care about what the types are, what their definitions are, and what the type of the property is, so that the type classes of Coq can take care of the rest. But yeah, other than that, everything is done in OCaml anyway.
Okay, but that's implementation language is not the main point. Okay. Got it.
Yeah.
Okay. Okay, great. Okay, I don't see any more questions. So thanks so much, Leo and Paras, for your wonderful talk. And we'll go ahead and move to the next one. All right. The final talk in our session here for this session, not for the whole workshop. We still have another session. The third talk in this session is by Michael O'Connor from Jane Street. And as many of you probably know, Jane Street has some widely used serialization libraries, both binary and as expression based. And as with all serialization issues, a significant problem is related to versioning when you want to update your protocols. That always becomes a problem, and how to handle that is never quite clear. So in this talk, Michael's going to be describing some work he's done about that called trace types, and the title of his talk is Safe Protocol Updates via Propositional Logic.
I work at Jane Street. Thank you for having me today. I'm going to tell you about a library called trace types, which allows for safe protocol updates via propositional logic. I think it has some pretty interesting ideas in it, so I'm definitely excited to tell you about it. So the problem this library is trying to solve is, given a collection of just executables which are out there in the world, they're in production already, for any given type, there's some directed graph about how these executables talk to each other. Furthermore, we're compiling some executable locally, and all these executables might be compiled from different versions of the code. All the ones in production, our local branch is probably ahead of the ones which are already deployed. And we want to know if doing deployment is correct. So we want to know if we were to place 6 executable like this one, are all the arrows, all the serializations that this executable participates in, is that still going to be valid? And as you might be familiar with, in order to solve this problem of being able to talk to old executables, typically, like, what you have to do if you want to change a type is you have to put in various tweaks to the serializer or the deserializer in order to maintain that compatibility. To get your intuition primed about the sorts of things that I'm talking about, I have a list here of common ways that people might tweak a deserializer or a serializer to be compatible with older executables. By far the most common is the first one, where you add a new record field but specify a default value, meaning that if that record field is not present, then that value will be taken. But there's other ones as well, and we'll discuss more of them later in the talk. So the solution that trace types proposes is to offer a language for writing serializers and deserializers which is expressive enough to, that it allows you to write all the version bridging sorts of code that we discussed in the last slide, but is also restricted enough that you can perform static analysis on it, and you can actually verify that if you do a deployment that that deployment is going to be correct. The raw format that trace types uses for what's actually passed around between executables is something which is simple enough to, again, statically analyze, but also relatively expressive. It's either an atom, which is an unanalyzed string, or a dictionary, where you've got an A list of strings and nested raw.ts. For example, a natural encoding of a record here would be to store the the field names as the keys of the A list, and then the nested raw.ts will be like, so in this case, it's the variant stored as a singleton A list. In this case, it's a further record, which is, again, this record field is the key of the A list. The thing which makes this sort of a nice encoding is that all the deserializers and serializers that we want to express can actually be built up out of a couple of basic operations in a relatively straightforward way. For building up deserializers, the basic operations are take in a raw.t, assert it in its atom, assert it's an atom, and parse the string, or take in a raw.t, assert it's an A list, look up a particular key, and then recursively deal with the raw.t which you find there. We can display this in an actual OCaml interface. So this is wrapped up in what's called a decay deserializer.t. From such a thing, you can actually get out the function which takes a raw.t and parses it and returns a decay. These basic operations are the things I just described on the other slide. Atomic produces a function which asserts that the raw.t is an atom and parses the string with this function. Similarly, nested returns a decay t, where the raw.t is asserted to be an A list, and then the argument to nested is look up in that A list, and the resulting raw t is passed on to the other argument to nest it. And then these basic ones can be combined using these sort of more generic combinator functions. For example, return will produce a function which ignores the raw.t and just gives back its argument. Map will just run its argument and then post-process by running this function on the tick that's returned. Both runs both of its arguments on the raw.t. Either tries to run the first one, and if it succeeds, then it returns first of tick A. If it doesn't, it runs the second one, and then returns second of tick B. And then any takes in a list of tick ATs and basically tries running them until it finds one that succeeds. For example, if you wanted to write a deserializer for a record type with the two fields here, so one way you could do it is you could say, okay, I need to get the foo field and I need to get the bar field. So let me look up the foo field and parse what I find there with int out of string. Let me look up the bar field and just take the string I get there. I need both of those things to succeed. And then I'm going to take the pair that I get by running both of those things and just put it into the record field, the record. So this can be done in kind of a natural way for records and for variants. As you might imagine, it's fairly cumbersome to write this sort of code by hand. So TraceTypes offers a PPX. This PPX just produces like the standard encoding of records and variants that you would normally do. So now what if you did want to use something non-standard? So you wanted to write some code to bridge between old and new versions. So let's take a look at an example where you have a record, but you want to use a default value for one of the fields. In this case, we'll say bar. So the way you would do this is you'd write a deserializer, which is very similar to the deserializer we had a couple slides ago. The only difference is in the deserializer for the bar field. Before, we just looked at the bar field and took whatever was there. Now we use the any combinator and first try that. So we do take what's there if it is there. But if there's nothing there, then we use return and just say, oh, okay, well, doesn't matter what's there, just take this default string. So this is also something that you, would want some PPX support for, and TraceTypes does provide it. You can see here that TraceTypes also offers annotations you can put at various points in the type, where you can say, okay, so you can generate the deserializer and serializer for this type, but at this particular point, use the generated value, but wrap it in any, and if it doesn't succeed, then use whatever's in here. Here's an example which this sort of thing is actually relatively common, although I didn't explicitly mention it before. But in this scenario, we have, the code starts with the type is something. It actually doesn't matter that it's a record field. It could be anything. The code starts in something, and then like later you say, oh, actually, there's more possibilities. And the code gets changed to the type that used to be the entire type is now some other type foo. And that's an argument to a constructor, and then there's more constructors. So basically what's happening here is you used to think everything that could happen was this, and you say, oh, wait, there's other things going on here. And so you stuff the old type into a constructor, and you add some new constructor of something else. It doesn't actually matter what it is for this example. I think this scenario is sometimes called retroactive unionization, although I don't need to call it that for this, but so now the problem is, suppose that we want to roll a deserializer. How can we write a deserializer for this type, which will also succeed on the old type? So the way that we do that is like this. So you have the old type, which is also part of the new type here. You have the new type here, and you want to write a deserializer, which will both work with the old and new types. So you write a deserializer which says, well, first try the deserializer just generated by the PPX, the standard one. So what's generated by this? And then if that doesn't work, well, try the deserializer generated by this, which was also the old type. And if that works, take the value you get and stuff it in the foo variant. There's also a serializer module, as well as a deserializer module. I actually won't say too much about it. It's almost exactly just dual to deserializer. So, for example, what you get out of it is a tick A to raw.t instead of a raw.t to tick A. This arrow is reversed. The map is called lift, and this arrow is reversed. You have an all function instead of an any function. And I'll leave it at that. So now let's think about the static validation part of this, namely given a serializer and deserializer pair, how do we know that the serialization is always going to succeed? So the idea is to think about what is present in a raw.t in terms of what paths are there. And so a path is basically a list of keys or a list of strings in terms of like nested lookups in the A lists, which are in the raw.t. And the way that we will check validity is we'll say, well, what is the serializer serializing? And is it enough for the deserializer to deserialize? In particular, we'll associate to every serializer a Boolean proposition S representing the paths that it's going to deserialize. And to each deserializer, we'll associate a Boolean proposition D representing the paths that it needs to be present. And we'll check that S implies D is a tautology. And in these Boolean propositions, the atoms are going to be these paths, these list of strings. So, so they really do represent like what is actually present in the message which is being sent. It's actually relatively straightforward to see how the combinator portion of the deserializer and the serializer interface map onto operations on the propositional formulas, just due to their sort of abstract nature, I guess. So, for example, return is always true because it always succeeds. Map doesn't have anything to do with the structure, so it doesn't change the propositional structure at all. Both needs both of its arguments to succeed, so it's an and either and any both correspond to or because they only require one of their either requires one of its arguments to succeed, and any requires just one element of the list that's its argument to succeed. On the other hand, both of the basic operations in the deserializer module, atomic and nested, don't affect the structure of the proposition at all. They affect the paths that are the atoms in the proposition. So, for example, atomic corresponds to the proposition, which is a single propositional variable, which is namely the empty path, the empty list. And nested, again, doesn't change the structure of the proposition. It just goes through all the atoms and prepends its argument. So it joins it to the path. So, for example, is the deserializer for this type compatible with the deserializer for this type? Well, no, and we can answer it using this propositional logic. So the proposition corresponding to this is just the foo, the path foo. And the proposition corresponding to this is the path foo and the path bar. So foo implies foo and bar is not a tautology. And so this is not compatible, and that's correct because this deserializer, of course, requires this field, which is not going to be serialized. On the other hand, what if we used the default value trick? So if we take still the deserializer, for which it says foo, but now we have a deserializer which has bar, but uses a default value of NA, is that going to be compatible? And the answer is yes, because recall the serializer here tries to look at bar, and if it fails, uses this, and this always succeeds, so the proposition is true. So we have foo implies foo and bar are true. Bar are true is the same thing as true. Foo and true is the same thing as foo. So this is foo implies foo, and so yes, it's a tautology. So now we can see a little bit more clearly how trace types tries to solve the problem which it's supposed to solve. Given a potential deployment where you say, can I take this executable and replace this one with it? Trace types finds the directed graph of how this type is being passed around. It finds all the arrows. It finds all the appropriate Boolean formulas from all these executables, including this one. And for each arrow, which this executable would be involved with, it forms the appropriate implications and checks if they're tautologies. As an implementation detail, it uses C3 stat solver, although that, of course, that's not fundamental. And yeah, that's it. That's the core of how the library works. Finally, to just say a few words about the actual production use. So we have used trace types in production for a little bit over a year and a half. It's used in a handful of projects. The one that I'm involved with uses it the most pervasively, and it's definitely been, I would say, a pretty big win. Like, it's enabled workflows that we haven't been able to do before, and it's eliminated, more or less eliminated a whole class of bugs. And it's been picked up by a handful of other projects, but within JStreet as a whole, it's definitely still a niche library. I think partly it's because it's just a lot of new concepts for new users to pick up. And so we have some further steps that are aimed towards making it easier for new users to pick up. But on the whole, it's definitely something I'm quite excited about as a kind of robust solution to this problem. And that's it. Thank you very much.
Thanks so much for the talk, Michael. Thanks. Great. That sounds very interesting. So one question from the audience, from Hong Cheng Wu of Bloomberg. He's asking, how does this compare to well-known protocols such as protobuf or XSD?
Yeah, so that's a good question. It's pretty easy. The answer is, I don't know. I will say that, I never actually used those things directly. I will say that I didn't mention it during the talk, but one of the motivations for trace types was actually to interface with manually written config files, which is JStreet are done using S expressions. And so I definitely needed it to, I believe that protobuf and such work with sort of binary protocols that have sort of flat layouts and are optimized for performance. But one of the things to do with trace types was, so one thing is the layout's not optimized for performance. It's optimized for this kind of logical analysis. The other thing is it had to kind of work with both binary protocols as well as with human readable S expressions, so that we could kind of backport our use of config files using it. But I don't know too much more about it, so I can't say much more than that.
Okay. A technique that we actually use at our company, which is inspired by a technique that I believe was described by JStreet, is just takes a practical approach, which is we just tag the types by their version, the protocol version at the very top level, and then we just always know the version of any serialized value. Mm-hmm. And then we manually deal with writing converters between the versions, and then that lets us basically handle any sort of change of any arbitrary complexity while being somewhat simple to just implement. Mm-hmm. Is that a technique you guys do use at JStreet? How does this feel compared to that? Do you
yeah, definitely
not good enough?
Yeah, definitely we do use it at JStreet. And actually we still use it now. So one thing about trace types is it can work within such some frameworks. So we actually do still have the tagging of these versions. It's just in the project I've worked on, we haven't had to bump the tag in a long time because we'll be able to stay at this one version. But we do still sit within this larger framework of being able to, we actually did it in the first place because we weren't sure if we liked trace types. So we said, okay, we'll try it by bumping the version, use trace types. If we didn't like it, we'd bump it again to say, okay, we'll get rid of it. But the ways in which trace types kind of helps over that is that we found that as our types increased, the amount of boilerplate involved in kind of copying all the old types over and doing whatever change you needed, and that actually that would ripple. So if you had some type included another type, at each step you'd have to do this copying. That's one thing. Another thing is that there's also, when you write the conversion functions by hand, it's you leave yourself open to some bugs, which do happen sometimes, where I write a down conversion function which just raises an exception because I feel oh well, this never gets called. But in fact, it will get called if you do something. If you roll executables in a different order, or if you roll back something. And it's just people don't. I didn't realize that. Whereas trace types also will tell you in that case oh no, this is wrong in this situation. So what do you want to do about that? So that was another advantage. But definitely, yeah, we still have this escape hatch of this explicit tagging, where if we do need to break out of trace types for some reason, we'll fall back to that level.
Okay. There are all the stable types you guys provide in your libraries, and we've faced sort of a similar situation where we just have to keep these old type definitions around in our code forever.
Yep.
That's definitely a problem. Another question from the audience, from Edwin Truck of Citrix. he is asking, he's saying it would be interesting to integrate this with other PPXs that generate backward compatible protocols like Mirage's OCaml RPC. So could your PPX library be stacked underneath such a library?
Again, because I'm not sure. I don't know Mirage / OCaml RPC or the way that in which it generates backward compatible protocols. Maybe. I mean, I will say that, like, trace types is specialized to, like, like I'm generating some, like, dictionary of, like, nested records and variants, or just some nested dictionary, as opposed to, like, generally, like, protocols which could do anything. Like, so it doesn't, like, in a protocol you can have, like, somebody says this to this person and this person says this to this, and it doesn't, like, represent that entire, like, back and forth conversation. It's just like this person says something and this person can either parse it or not. So depending on, like, the type of protocols which are, like, to be made backward compatible, that may or may not be something which trace types can handle. But yeah, again, the question is, the real answer is I don't know. I'm not sure what the answer is.
Okay. And another question from Noah Bartel-Mangal is if he's asking if the library is publicly available, and if so, where?
It's not. I actually, like, just sort of didn't consider it, but, like, as part of giving this talk, I was thinking about, like, yeah, there's no reason why not. So yeah, I mean, I definitely plan to look into it. It like, it depends on other libraries which I think are not publicly available, but there's no reason why they shouldn't be. I think, like, there's no reason it couldn't be. So I'll definitely look into releasing it.
Okay. In your talk, you mentioned how you can do this with executables, talking to other executables. How does the library support reading from files?
Oh yeah, as I mentioned, like, one of the use cases was reading from files, even though I didn't mention that in the talk. But yeah, so with an executable, like I said, you check that, like, the proposition corresponding to the serializer implies the one corresponding to the deserializer. And with a file, of course, you can't query it because you don't know. It might not have been a program which wrote that file. It might have been a human. So it's just some file. So what you do instead is, when you replace an executable with another one, you check that the new executable can deserialize at least as much as the old deserializer. So you form a different proposition that involves the two deserializer propositions. And so that's a little bit less flexible because you have to, like, keep supporting more and more stuff, but it's conservative. It's safe. It'll ensure that you can always read whatever the file was, as long as it could have been read before.
Great. We are 1 minute over, but I'll ask a final question. I think we have a long break, so I can run a little over. You showed an example of a default serializer that ignores fields that it's not aware of. How could your library support a situation where you want the serializer to actually raise in that case?
Yeah, right. So there's right. So you don't always want to ignore fields which you don't know about. Like, if you are a deserializer and, like, there's some fields which you've never heard of, sometimes you want to raise in such a situation. One example is for manually written config files, maybe someone's written a typo. Another situation is if you're a serializer, you might add some new field and say, like, no, this is important. I don't want anybody to ignore this. So in the latter case, trace types supports this by just, again, doing the same trick, like forming another proposition where it's like you ensure that, like, everything that the serializer wants to be deserialized, all the deserializers will deserialize. And for the first case, there's a separate way to control this problem where there's actually another combinator for deserializer, which says, like, there's a disallow unused fields, take a deserializer to take a deserializer, which puts that property on a deserializer.t. And the handling for the propositions for that is a little bit trickier because you have to, well, it's a little bit trickier, but yeah, there is support for that as well.
Okay, great. Thanks so much. That was the last talk of the session. The next session starts in about 45 minutes. We'll see everyone back soon. Thank you.
Greetings, workshop attendees. I'm Rudy Grimberg from OCaml Labs, and I'll be chairing the sixth and last session of this workshop. And without further delay, let me introduce the next talk by Ivan Gotovchitz from Carnegie Mellon University and David Bromley. They'll be talking about the BAP framework, the binary analysis framework, which is the program analysis framework for binaries. And the talk will be about using tagless finally style for developing transformations in this framework. And now let's start the talk.
My name is Ivan Gotovchitz, and I'm a research scientist at Carnegie Mellon University, CMU. In this talk, we'll discuss tagless final style, TFS, and its application to program analysis. As our case study, we will use the CMU binary analysis platform, BAP. We split our talk into three main parts. In the first part, I will describe the context, BAP. In the next part, we will define the problem with which we will tackle. In the final, the most interesting part, we will gradually build the solution. Instead of a formal approach that prefers axiomatic exposition, we will stick to the example-driven, didactical one. We believe that our choice is justified. First of all, it suits better the format of the workshop. Second, there are plenty of tagless final style papers that give formal but complete non-intuitional explanations. Okay, let's get started with BAP. What is the binary analysis platform? BAP is a set of utilities, tools, programs, libraries, and frameworks that interact with each other for the sole purpose, developing an understanding of what programs are doing. BAP understands many hardware architectures, including x86, ARM, MIPS, and PowerPC. Even more, we plan to add support for middle and high-level languages such as JVM and C, consequently turning BAP into a universal program analysis platform. BAP's implementation language is OCaml, but it's possible to write analysis and interact with BAP using Primus Lisp or common Lisp like DSL. It is also possible to use C and Python via C types bindings. However, using BAP generally doesn't require any programming skills thanks to the powerful command line interface. BAP uses a single intermediate language for representing programs compiled for different architectures. This language is precise and faithfully depicts each operation, including flag updates and various hidden effects not otherwise representable as changes to the CPU and memory state. To translate a program in a binary form into a program in the intermediate language, we need to know the semantics of the machine instructions. The semantics is specified either in a OCaml EDSL or in a Primus Lisp DSL. Both representations are strongly typed and feature type inference. We can also leverage existing disassembling and decompilation frameworks to obtain semantics for free. For example, we use the NSA Ghidra, which translates binary instructions into P-code instructions, as the source of semantics. We achieve this by simply writing the semantics of P-code operations using Primus Lisp. BAP allows various intermediate representations of its language. Adding, modifying, or removing an IR doesn't require reinstallation or even recompilation. It is possible because BAP uses the plugin-based architecture with dependency injection. The modular design enables us to pack each feature of BAP as a separate PAM package and give our users control over the desired feature set. As a bonus, dynamic linking lets us link LGPL code and still keep BAP MIT licensed. On the previous slide, we were talking about the current state of BAP. But it took BAP 16 years to mature to this point. The old ancestor of BAP is a C++ program called SM2C. It was the first, maybe naive attempt to decompile an assembly directly to C. We quickly realized that C is not suitable for the intermediate language, as it makes implicit too many things. We addressed the issue by encoding all side effects of a machine instruction in a specialized IL. It was our grandfather, Vine. This project is still alive and lives in the Berkeley BitBlaze project. The BAP was born then. It continues the tradition of Vine and also used intermediate language. BAP 0.x was an in-house development that was not publicly available. We removed all dependencies on proprietary or copyleft code and released the first beta version of BAP in 2014. After several iterations, in 2016, we released the first stable version of BAP, BAP 1.0. We are proud to say that since 2016 we maintain the stability of the interface of BAP. Even in 2019, when we switched to the tagless final style, we preserved backward compatibility with the existing code. As of today, BEP has a vast and diverse user base. It features dozens of ready-to-use analysis, integrates with the modern state-of-the-art tools such as Gidro or IDA Pro, and easy installable via OPAM. But let's go back to the timeline of BEP. We can see that from version to version we have a switch in intermediate languages. Each switch was painful, resulting in a hard fork of the platform, essentially letting the old version die and the user seek a new platform. In 2017, we were facing the same problem. We had to change our intermediate language as we needed support for new features. Floating point operations, instruction level parallelism, hardware parallelism is an incomplete list of features that were not representable in our current version of IL. We also were dreaming about accommodating bytecode and high-level runtimes, but we couldn't afford to lose our users by yet another hard fork. We had to find a solution to this problem. However, before solving a problem, we have to define it. We have a concrete list of requirements that constitute an ideal solution. The first requirement is extensibility. We want to be able to extend the language without breaking or modifying any existing code. But this is only one facet of extensibility. We also want our language to be independent of analysis. In other words, the language shall not dictate how to analyze itself. Together, these facets are known as the expression problem. But more commonly, we need another kind of flexibility than extensibility. Rather than extending the language, we often need to modify its representation to suit our needs. We may need to add hash constant or add to the language post and precondition guards to leverage our weakest precondition analysis. Some of the tasks are easier to solve using a semi-graphical representation, while for others, syntax trees work better. In other words, we need to relinquish control over the language representation and give it to the users. That means that our language shall be abstract and allow multiple representations. Another requirement is that the prospective solution should be retrospective. That means that an implementation of this solution shall not require a complete rewrite of the existing code. We still want to maintain backward compatibility with the currently used language. We want static type guarantees in our language that prevent the construction of field type programs. Ideally, we want to employ the meta-language type system to enforce the well-formedness of the target language. Eliminating ill-formed programs on the construction phase also contributes to efficiency, as we could skip unreachable branches and focus our attention on real programs. As our output is a binary program, we'll build our intermediate representation by parsing that program. In addition, we want to store intermediate results for later processing and for distributing to other machines. That means that the proposed solution should enable serialization and deserialization of the program representation. Last but not least, our representation will be efficient in all senses of this word. It should have an efficient memory representation, both runtime and on disk. It should be portable across machines to enable parallel processing. The cost of abstractness should be zero or close to it. Finally, it should be easy to use and understand, which contributes to the efficiency of the language user. We have several constraints as well. First of all, the solution should fit into the vanilla OCaml type system. That means that we don't have type classes or module implicits. Another constraint is that we shall maintain close ties with the text-put abstractions. Many of our users are students who use BEP to learn program analysis, and they should be able to follow precisely the textbook algorithms. Finally, the solution shall play nicely with the BEP plugin-based architecture. It is well known that a plugin in OCaml can change the type environment of the host program, which is a heavy constraint. Let's start our search for the solution for what we have. The pre-2.0 BEP intermediate language called build had two representations, an abstract syntax tree and the semi-graphical representation in which control flow edges were made explicit. The AST representation uses OCaml algebraic data types, also known as variants. Maybe it is good enough? Many OCaml programmers will answer yes to this question. Just add a new variant and the compiler will gently guide you through the rest of your code where you need to address the newly added variant. To issue the abstraction requirement, we can decide on the set of possible representations that we need and write corresponding translators. This approach is valid and sometimes even optimal for monolithic projects that belong to a single authority. In other words, when you have access to all code which is affected by a change and have the right to modify it. Indeed, this approach is commonly seen in compilers and program analysis tools. However, history shows that it doesn't work for projects like BEP and other libraries and frameworks with a diverse and distributed user base. Every time we broke the interface, we had a lot of tools and analysis left behind. This situation is common for the academic community, where researchers, most commonly PhD students, develop tools until the paper is published and then abandon them. As a result, new researchers have to start their research from the beginning, which inhibits the progress. Okay, maybe turning it to an extensible variant or using some GEDT magic will help. Extensible variants might look like a solution to the expression problem. Indeed, adding a new branch will not break the existing code. We can even employ open recursion and a little bit of mutability to write extensible operations without modifying existing code. And adding GEDT will eschew ill-formed programs. But this solution doesn't match with the other requirements. First, it's not abstract. It is a concrete representation that doesn't permit change in implementation details like adding hash constant, for example. Some projects might relax this requirement, though. But let's move forward. Another problem with this solution is that extensible variants are not serializable. The same is true for GEDT. Neither can survive a serialization-deserialization cycle. And writing analysis in the open recursion style turned to be non-intuitive and error-prone. Therefore, we have decided to abandon this approach. Of course, the expression problem is a well-researched topic with plenty of solutions. We excluded solutions that do not fit into OCaml or are too convoluted, and ended up focusing on object algebras, also known as tagless final style, TFS. The approach is attractive in its simplicity. A language is a many-sorted algebraic signature, ID as a collection of sorts, types, and operators, functions, which perfectly maps to the OCaml signature. And the representation is an algebraic structure, or algebra, which perfectly maps to OCaml structures. We can see the signature as the syntax of the language, essentially a set of constructors, but in the functional form. To represent terms, TFS uses church encoding. A language term is a function that takes an algebra and returns the interpretation of this term in that algebra. In papers about TFS, they commonly use Haskell, where such encoding is implicit. In OCaml, we have to make it explicit and encode it as a function. And we immediately can see how type scopes complicate our life. To use a value, we have to extend its type scope by creating a local abstract type. It's tedious, especially when the number of sorts in our algebra becomes large. Another limitation of OCaml is that it can create only ground local types. In this example, we use multi-sorted algebras to model terms of two sorts, Boolean and integers. But we can't introduce a polymorphic type constructor on the expression level, as OCaml lacks higher-kind polymorphism on that level. We can try to stick with ground types for our sorts, but this will lead to an explosion in the number of operators and won't work if the number of sorts is not finite. Another option is to use the high library. It gives us a way to represent higher-kind polymorphism without functors, but I found that the resulting solution is still heavyweight. We also can't rely on functors for our terms, as a packed functor will have the same problem of escaping type. And remember that we need our language term to be a value, not a top-level definition, as we build terms from arbitrary input. The solution is to factor the type from the signatures and move to the global scope. It immediately resolves a lot of problems. We no longer need to write local type annotations and can fully encode multi-sorted languages, even with an infinite number of sorts. We still need to figure out how to encode the alpha T type in a way that preserves its abstractness. We know that abstract type have existential type, so we can finally employ extensible variants and GEDT. Don't worry, we will solve the serialization problem later. We use an existential type to capture the algebra carrier set type. The sort is still captured, which is what we want. But there is still an issue with our representation. It's still church is still a function. Despite all our love for lambdas, we still prefer to use data types for represented program terms. Because we want to save them on disk, send over network, compare them, store them in sets, and otherwise use them as regular data types. The performance of the church encoding is also a big issue for us. Recall that we are not representing terms as EDSL, but parse them from the binary input. It is an inherently non-total and expensive process. We want to do it once and never repeat it. The solution is also on the surface. We can represent a function from algebra to the notations as a finite mapping indexed by algebras. In real applications, we always need all or some subset of representations at once. To compose several algebras into a single superalgebra, we define functor join. We perform pairwise join for each operation. And we can take a list of algebras and create a concrete algebra that we will use to create program terms. Now we have a term and we want to analyze it. First of all, we can't use the good old we can use We can use the good old initial style with pattern matching. For that, we can extract a concrete representation, like a term in Bill AST, analyze and transform it, and then inject it back. Yes, it's not extensible, but it enables the textbook style and backward compatibility. But what about the final style? Oleg Kiselyov's lectures and tutorials on tagless file optimizations show that we can implement many transformations in TFS, including non-distributive analysis. In fact, after implementing a few algorithms in TFS, we can see an emerging patterns. Each implementation defines a specialized domain language. For that, we use common algebraic data types and pattern matching. The defined language is very tight and optimal for the task it solves. And what is valuable from the perspective of software engineering, the language is hidden under the abstraction barrier. In the end, we can claim that TFS facilitates the creation of new representations, and does this without compromising modularity and extensibility. Another emerging pattern is the use of the state. Most, if not all, operations can benefit from the state, so it looks like a good idea if we would turn our universal term representation into a state manette. Now the final piece of the puzzle. There is a particular kind of analysis that requires special treatment. We are talking about mutually recursive analysis, or more generally about the denotational semantics of non-structural recursive programs. The approach that relies on a state plus some specialized encoding is not sufficient here. We need to add fixed point computer to our state manette. And to ensure termination, we need to impose an extra constraint on our algebras. They shall have the structure of a domain. Idea is to have an empty value and a join function. Besides, having join and empty makes it much easier to write the join functor that we wrote a couple of slides above. And in the end, we can pack all these ideas in a single library, which is independent of BAP and could be used by everyone. The library is called knowledge. Well, it is BAP knowledge, but ignore this namespace prefix. In addition to providing abstractions that we described above, it also takes care of serialization. In the presence of GADT and extensible variants, it's a non-trivial but doable task. But this is a topic for another discussion. Thanks for listening, and please ask questions.
Thank you, Ivan, for this presentation. And now let's take up some questions.
My pleasure.
All right. So I guess the first question is by Ohad Kumar. Are you familiar with Frex?
I haven't been, unfortunately, until I saw this question. I already Googled and I'm looking into it. It's not that we have intersecting tasks, but I think that in the future, BAP can benefit from Frex, not other way around.
Okay, thank you. Another question by Gabriel. Can we see an example of a specific ADT in back?
Well, basically, like there are two approaches to that. Like non-final approach, you can just extract a representation, transform it, and then inject it back because we use universal types to represent our values. The problem with that is that if you transform somehow a representation, it's not reflected anyway with the other representations, so we have mismatch between them. So another approach is basically using an initial representation, so-called initial algebra. That means that an algebra so universal to say that you can go from this algebra to any other algebra in your algebra set. Basically, it's the same as AST, a representation of the signature, like the syntax on signature. Then it means that if you will apply your transformation on this AST, you can then replay and reparse the transformed AST and got a completely full final term. To be honest, we're using the first option. When we need to do this, we're actually just injecting and projecting and injecting back. I hope this answers the question. But for better examples, you can visit BAP, GitHub, and there are plenty of examples there. I can provide a link for necessary.
Yep. So the next question is asking for more examples. I think Ivan already said that you can check the website for some examples.
Just like BEP is used by many. Like for example, like there is a Forall Secure company that is CGC winner. I don't know. It's kind of a niche company, but they're using BEP underneath the hood. There are several, like Siemens is using BEP, and there are several companies that are using BEP. This is like as a users. Speaking of examples, like what BEP can give to me is that, well, you can take a binary and analyze whether it has any weaknesses, for example, whether it has any use after free problems. You can use BEP to emulate, evaluate a binary. You can use BEP to just understand its structure. You can use BEP to analyze dependencies of the binary and build the tree of dependencies between libraries and so on and so on. It's basically, it's a huge project with hundreds of thousands of lines, and it does whatever you would expect from your program analysis tool and focuses on binaries.
Right, thank you for that. Another interesting question from Peter Urkedal. He's curious if it's possible to use your experience to somehow apply it to providing this, to solve the problem of PPXs and the stability between them.
Yes, definitely. It's I haven't talked with the developers of PPX about that a couple of times. So I'm proposing that final style may eventually solve this problem of the upgrades. There are other solutions, and there are always trade-offs. My belief is the answer is yes.
Very cool. All right, one more question by Ihao Sun. Can you talk about how Primus works? Does it do something like symbolic execution? Is it sound analysis?
Primus is a framework for writing your own interpreters. The idea is that you take a binary, translate it to intermediate representation, and then evaluate it. And Primus as a framework gives you a lot of options to control the process interpretation. You can watch what happens. You can change the semantics of instructions. You can re-execute, because Primus underneath the hood is actually a continuation monad. And all this stuff. Using Primus, we're building different analysis. For example, there is a symbolic executor that uses Primus that basically does normal symbolic execution driven analysis. There are promiscuous mode analysis that just total and sound breaks all the laws, but it works fine with taint analysis and understanding data flow dependencies. You can pick one or another, and you can develop your own modes of execution using Primus. I think I answered all the questions. Yeah.
Yep. Thank you for that. Right. So feel free to write more questions. Yeah. I suppose in the meantime, Ivan, could you elaborate a bit on how this could be used for solving the PPX issue? I can see how it can be used for constructing, I guess, the parse trees, but when writing PPXs, pattern matching is usually a big component.
That's a common misconception that final style prohibits pattern matching. In fact, I would say even it facilitates it. It makes it easier to use pattern matching, because you can pattern match freely without being afraid that in the future the code on which you pattern match will change and it will break your code. The idea is that you define your own DSLs for your own PPX, for your own ASC transformation, and then you maintain your own DSL and work with it and pattern match on that, and you can wrap the foreign representation inside of JDT. Basically, long story short, it actually enables you pattern matching.
All right, great to hear. So I guess there's no more questions. I suppose this one here, I'll shoot another one then. I bet you get asked this one quite a lot, but I guess why not free monads?
I believe the same problem with other approaches. That's right. It's performance.
Mm-hmm.
It's still like underneath the hood will be a function, and we need something concrete.
I see. All right. Well, let's thank Ivan once again.
Thank you for having me.
Oh, Gabriel gave us one more question. Have you looked at modular implicits? Could they help?
Definitely, like the main design of how we design things is that OCaml lacks modular implicits. If it will have, it will be completely different approach. Like right now, it's too late to have them for us because it invalidates what we did. But basically, we actually sort of implemented our own version of modular implicits. The thing is that we are storing the structure, like the type class instance. We actually implemented like type classes in OCaml for BAP. We store the structures, the first class modules, implicitly in the knowledge base, and whenever you instantiate a term, you request the currently used in the context instance of the type class and evaluating it. This is how it works inside of BAP. It's actually basically the same as the modular implicits, and you can control the instantiation of what kind of model you need by specifying requirements and context of the model, and then the system will automatically pick the most suitable instance.
Okay, it looks like Edwin has another question. Would BAP or part of BAP be useful in a compilation pipeline, like Duplo or something similar?
We are currently on one of our projects is currently actually focused on code generation and binary writing, and yes, indeed, it could be used for taking an existing binary and understanding its dependencies and writing it back.
Right. Thank you for that.
Okay, thank you.
Thank you. Right, and now is time for the second talk. The second talk will be by Ioan Padiulu. He's going to be presenting the SemGrep tool, which is a fast and lightweight static analysis tool. Right, let's start.
Hello, my name is Ioan Padiulu, and today I'm going to talk about SemGrep, a polyglot bug finding tool. And so, what is SemGrep? So SemGrep is a fast, polyglot, customizable, open source static analysis tool to find bugs and enforce code standard. And so it can do many things, but its main goal and where it really shines is to write custom rules to find bugs, and especially security bugs. And the main idea behind the tool is that to express code patterns, to express rules, you can use the syntax you already know, because the patterns looks like regular code. And so to make things more concrete, here is an example. So SemGrep is a command line tool. So in a terminal, You can type semgrep, and then with the -l flag, you can specify the language you want to analyze. So here, OCaml. And then with the -e, you can specify the code patterns on the command line itself instead of inside a configuration file. And so here we are looking for all the code to list.map. We don't care about the function. And then we care that the second argument is a list literal. And the last argument is the directory so here dot for the current directory. And so then when you type this command, the tool will go through all the OCaml file in the current directory, and each time it finds a match, it displays it on the standard output, a bit like grep. And so here's a match at the line 2667, and actually the tool will also highlight in white the subpart of the line that was matched. And so semgrep supports currently 17 languages. And so most mainstream languages like Python, JavaScript, Go, and also less mainstream languages like OCaml. And the reason for OCaml, the main reason for OCaml is that the core engine of semgrep is written in OCaml. And so we can run the tool on its code itself, on its own code. And so a few words about the history of semgrep. And so many of the ideas behind semgrep can be traced back to a tool I co-developed in academia with Julia Lawal called COCaml, which was a domain-specific language to express program transformation. But this tool was just for C. And then later, I joined Facebook, where I developed a similar tool called grep for syntactical grep, which was a simplified version of COCaml, and it was just for PHP this time. And then later I joined R2C, where we designed a new tool called semgrep for semantic grep, which was designed from the start to be polyglot, to handle many, many languages. And so because internally we designed a generic EST that can cover many languages. And it's called semantic because the tool knows about the semantic of the languages. And so you can write one code patterns, and even if some code are syntactically different, they will still be matched if semantically they are equivalent to the code pattern. And in 2021, actually, GitLab chose semgrep as the official static analysis tools to find bugs in Python, JavaScript, and TypeScript projects. And actually, we are working with them now to extend that to other languages. And so quickly, how to install semgrep. And so it's pretty simple. So if you're on macOS, you can just type brew install semgrep. Otherwise, you can use the Python package manager, pip, to install it. And so the reason we use pip is that because the core engine of semgrep is written in OCaml, but there's a small wrapper around it written in Python. You can also use a Docker container. And once it's installed, you can use locally. And so you can either use rules that we developed, our company developed, and as well as the community. And all those rules are available on what we call the registry, the rules registry. And so here you can type semgrep --config, and this argument is a tiny URL that corresponds to a set of rules, and then a directory to check. And you can also use your own local rules that you can store in a YAML file. So here --config equals semgrep.yaml, which is a local file. And you can also you don't even have to install semgrep to try it. You can also try it online, because we developed a rule editor, a playground on the web. And so if you click here, I can do a quick demo. And so the tool is, so here in the menu, here you can choose the language you want to write the rule for. Here you have actually at the top, you have the semgrep rule with a set of fields. You have the identifier of the rule, you have the code patterns. So here we are looking for call to list.find. And then you have the message to display when there's a match was found, and the languages, here just OCaml. And then at the bottom, you have the testing code, and then you can click the button run, and then we will run semgrep in the cloud and return all the matches. So here, this match. And so there's some good tutorial in this playground, and you can actually also click on rules to explore the set of rules available within semgrep. So for example, if you type OCaml and list, you will get the set of rules oh, sorry, didn't work, list, you can get, you will get the set of rules for OCaml. So here, if I click on the first one, this is a rule that said you should not use list.find outside of a try. You should use list.find underscore opt. And the way it's encoded is that you have the first pattern here that look for list.find with whatever after, and then it's composed with another pattern with a formula called pattern not inside that checks that we are not inside a try. And so if you are outside a try, you should not use list.find. And so back to the presentation. So the main features of SemGrep, so if I take back this simple example from the beginning, is that the main feature is that we use the concrete syntax. That is, the user doesn't have to, it's easier to use than a regular expression. And actually, you cannot even express these code patterns using regular expression because the function argument to list.map can be arbitrarily complex with nested parentheses, and already regex are out of their reach for that. And the other way, the traditional way to write a linter for a programming language is to use a visitor that visits an abstract syntax tree, an AST. But the problem is that you have to know internally how each construct of the language is represented internally. And so it's okay maybe for one languages, but for 17, each time it's like a significant load on your brain. And so it's far easier to just, you already know the syntax of OCaml or Python if you want to write a Python rule. So we can just leverage that. And so you don't need to write a visitor on an EST. But internally, the tool works on an abstract syntax tree. And so, for example, in this example, there's one space between the map and the function argument. But in concrete code, you could have a new line, you could have comments between after the list.map. It doesn't matter because the tool internally works on an abstract syntax tree. Another important feature is the use of meta variables, which are prefixed with this $sign. And they are used to abstract array things like expression, patterns, types. Another feature is the use of the ellipsis operator here inside the list literal. And ellipses are used to abstract away a sequence of things, a sequence of parameters, statements, characters. And both of those features really are used to make the pattern more general. So the rule can apply to more code. Another important feature, and hence the name of SemGrep, semantic grep, is that the tools know a lot about semantic equivalences of the languages. And so, for example, in OCaml, you can call list.map, but some people may have aliased, rename the module locally with a shortcut, for example, module L equal list, and then they will write L.map. And actually, SemGrep knows about this equivalence. And so if you write L.map, we will still find a match, even if the pattern is list.map, because we know syntactically they are different, but semantically they are the same. And so the tool knows lots of knows a lot about semantic equivalence. It does a limited form of constant propagation. It knows about the commutativity of certain operators. It knows about keyword arguments. For example, in OCaml or Python, you can write a function call with keyword arguments that can be put in any order. And if in the code patterns you chose one order, it will still match code that was written in a different order because the order doesn't matter. They are all equivalent. And the last important feature is a Boolean composition of patterns that I showed briefly before, where you can write one pattern and combine it with not another pattern and another pattern or another pattern. So with Boolean operators. And so a few advanced features of SemGrep. And so there's limited time, but an important feature that actually works only for OCaml, because it's a prototype, is to use a -lsp flag. And in that case, SemGrep will communicate with OCaml LSP, the language server for OCaml. And so here you can actually write more complex patterns like list.map, where the function argument must have this type to take an int and return an int. And so you can use type and meta variable actually in OCaml rules. And another use of LSP is that it allows us also to handle code that use open list. So sometimes people open list and then they can just call directly map. And the code pattern is list.map. And so it's not exactly equivalent, but by querying LSP, we can know that actually this map is list.map and we can report a match. Another important feature is tainting mode, where you can specify source, sink, and sanitizer using code patterns and actually Boolean composition of patterns. And internally, the tool will do an intra-procedural data flow taint propagation. And so this is especially useful for JavaScript code, for security bugs. And you can plug multiple matching engine. You can also analyze multiple language in the same file. For example, in HTML, you can have strings that actually contain JavaScript code. And so what you can do is that you can write a pattern to match a specific part of the HTML, bind it to a meta variable. So here, for example, $x. And then you can apply another pattern on this meta variable using a different language, possibly. And so, for example, in OCaml, you can have strings that contain SQL. And so we could combine the language of OCaml and the language of SQL and make a powerful semantic query on the SQL part. And so there's also a whole ecosystem around SemGrep. So I talked a bit about the registry, but there's also a dashboard with some insight. You can manage easily a set of rules on a huge set of repository. There's an agent to make it easy to run SemGrep in CI. So there's a lot more features. So I'm not going to have the time to talk about how it works internally, but something that may be of interest to the OCaml community is our use of the Tricitor library. And so Tricitor is a library that was developed at GitHub and that actually powers code highlighting in github.com, in the Atom editor and the NeoVim editor also. And so Tricitor is a GLR parser generator. And the good thing is that the community around Tricitor developed lots of grammars for lots of languages. And so for C, C++, and actually we use the Tricitor OCaml library grammar for parsing OCaml code. And so, and on top of Tricitor, we developed, actually Martin Jambon developed OCaml Tricitor, which is a tool to help generate typed EST from the untyped CST. And so hopefully we will release soon OPAM packages so that each languages of Tricitor can be a separate OPAM package so that you can easily write a custom tool for where you don't have to reinvent a parser for Python or JavaScript or whatever. And so, yes, so we are actually hiring. And so that's part of the reason of my talk. So we are a San Francisco based, we were actually San Francisco based, but now with COVID, we are quite remote. And so if you love OCaml and if you have a passion for dev tools and security, please contact us. And so we have full remote position. And so you can contact me, Pad at Return to Corp, or Martin Jambon, who joined us last year. And that's it. Thanks for watching. And so SemGrep, I just put here a few comments to make it easy to install and use. And we have also a Slack channel. And so if you have questions, we can interact through the Slack channel. And that's it. Thank you. I'm going to take questions now. Yes.
Yeah, thanks, Jan, for the presentation. And now I see there's a few questions queued up already. So let's start with Edwin's first question. So this question is about general OCaml support. So which parts of OCaml can it parse? Is there a subset of OCaml that it fully supports? And does it need to parse the whole program? Or can it make partial queries about the parts it understands?
So right now, we actually use now the Tricitor OCaml grammar. And so the support is pretty complete. So I think we have like on the website, we have parsing statistics. And so I think we are at maybe 99% of correct parsing for popular OCaml projects on GitHub. So the OCaml support is pretty good. The pattern, the kind of pattern you can write is more limited. So there's parsing the pattern and parsing the actual code. It's two different code paths right now for OCaml. And so regarding the whole program. So the Tricitor library is actually pretty cool. It does lots of error recovery. And so if there's an incomplete program, you will have some certain error nodes. And so in theory, we could still find, if the pattern is on code that was parsed correctly, we could still report a match. But we will also say, oh, there was a partial error in this file, by the way. Maybe there will be more in this file, but. Rudy left the stage. So I don't know if I need to do his job now. And so, will it be? It's back. She's back. Sonia, sorry.
Yeah, sorry. Rudy is having a technical problem. He's coming back now.
Okay.
Maybe in the meanwhile, I mean, you can see the questions.
Yes.
If you want, you
the
can.
other question is by Ivan. Would it be possible to abuse semgrep as a documentation search tool? And do you think it will be practical? So I'm not sure I understand what it means by documentation search. So right now, we don't actually analyze comments. And so we will not, the patterns will not be able to find stuff in OCaml doc, for example. And so, but I'm not sure that was a question.
Right, if Ivan wants to clarify, let's feel free to do so. But for now, let's proceed to the next question. All right, so Edwin, oh, there's Ivan.
Yep, I'm here. You basically answered my question. The problem, like, it was actually OCaml specific. The problem that we currently have is that there is no really good search tool like Google in Haskell, for example, that will enable us to find functions by their prototypes, I would say, by their signature. And it would be nice if you will be able also to parse a live file and parse the comment sections and give back the location information so that we can abuse semgrep as a documentation search tool.
I mean, regarding Google, so I've shown there was this -lsp flag. And so in theory, you can use, you can abuse semgrep to find function by signature. And actually, you can even use a meta variable in the type. So you can say $t return int. So
awesome.
Yeah. So, but it's quite a prototype, this part. So Rudy is actually, Rudy, you're the one implementing OCaml LSP, no?
Yeah. Yes, I am.
So it's stressing a little bit the OCaml LSP server, which was not designed for that, because we are basically asking at every node in the EST, what is the type of that? What is the type of that? What is the type of that? And so, yeah, it was not
that's right.
that.
Yeah, the LSP protocol, it should be possible to do this efficiently, but doing it through the LSP protocol adds a little bit of overhead. Yes. All right. So let's proceed with Edwin's question. Could we define crowdsource a set of semgrep rules that looks for bugs and C bindings? For example, if I find a particular bug in one C binding, can I easily grep for that same bug in all C bindings in OPAM?
Yes, I mean, there's some support for C in semgrep, so C is one of the language. And so, yes, in theory, we could, actually, that's often what we do. We find a bug in some code, and we try to make it more general, to make the pattern a little bit more general, and then we can look for the same kind of code in other code base. So, yeah.
All right, that's affirmative. So Thomas is asking, why do we need Python at all? What does the Python wrapper does that OCaml can't?
So, so there's other developer in the company, and they were more familiar with Python. But actually, every month we reduce the part of Python, and so now there used to be some part that were done in Python, and the Python part is getting smaller and smaller and smaller, to the point where yes, yes, I mean, we don't really need the Python part almost. But it's easier for people to install. Pip install is more common than OPAM install, and so.
Yeah, so looks like we have a trend in the right direction here. So that's great. So I guess initially you mentioned that SemGrep takes an inspiration from earlier tools like OCaml, but those allow modifying the source as well semantically. So is there like a SemSed counterpart that lets you make changes across code bases with these rules?
So actually, I designed Coccinet with Julia. So, but so it was just for C, and when I made SemGrep, I wanted to handle multiple languages, and that makes more difficult the transformation part, because in SemGrep we try to move, we try to abstract away certain features to go to a common representation, but that means we simplify the code, we remove some sugar sometimes, and that makes it harder then to replace, to allow transformation. And so we allow some form of transformation. We have this auto fix feature where basically you can find some code and we can replace the whole expression. So it's not as powerful as Coccinelle, but in practice, I think it's good enough for many use cases.
Right. So you can do things like, let's say, renaming and.
Yes, you can. Yeah, you can replace. You can find you can put some context. Oh, I found a certain expression, and then just replace the whole thing. And in the replacement, you can use meta variable that match some code in the pattern. So in theory, Coccinelle, you can really do minus and plus. It's a bit complicated, but you can really do complex transformation, very complex transformation. That this is not the goal of SemGrep. The goal of SemGrep is mostly to find bugs and occasionally fix bugs. And yeah, but that means it can be more general, like that. Coccinelle is just for C, and it will be hard. I mean, actually, Julia extended it for Java, and it was very difficult to try to make the tool handle Java. And when instead SemGrep, it takes like 2 weeks or 1 week to add a new language. So
I see. So I guess to follow on that. So what does it take to add a new language? I assume a tree sitter parser, an existing tree sitter parser, has to be already done.
I mean, you can. I mean, some of the languages are supported by parsers. I wrote actually in Menhir, but yeah, now like if there's a tree-sitter grammar for it, it's easier. Yeah, and actually for people also to contribute, it's easier. They don't even need to know OCaml. We had a few contributions for people who didn't know OCaml, and they just we just included the tree-sitter grammar, and then they wrote the code to transform the concrete syntax tree of the language to the generic AST that we have. We have a generic AST that accommodate all languages, and so they were able to do so. So yeah.
So if I'm getting this right, one can use either tree sitter or Menhir to write the grammar.
Yes, but yes, yeah. I mean, or whatever. You can use the Yak, or it's just that.
Okay, yeah.
But then the hard part. It's not very hard, but at some point you have a front end for a language, and you need to convert it into this generic AST. Yeah. And so there's a structure that define a generic AST that is a kind of factorized union of all the languages.
Yeah, and just I guess to confirm, you've mentioned this in one of the slides, but SemGrep does not support scoping constructs such as open without external help from LSP.
No, because the goal of SemGrep is to just to be fast. It's just analyze one file at a time, and so it doesn't. So we are extending it to handle multiple languages. To handle multiple files, but it was not designed for that. And so an open, you need like the -lsp flag, or it's the same in Java if you do import star, and then I don't know where does.
Yeah, that usually complicates query a lot.
But I mean, in practice, I mean, all those languages usually actually strongly say that, oh, you should not use this. You should not do an open in OCaml. You should not do an import star in Java, or in Python or whatever. So usually, or in Go, they usually say it makes the code more difficult to read. And so we are in the good trend, as you say. It makes our job easier.
Yes, indeed. Yeah, although a lot of local opens remain in use in the wild, that still make this a little difficult.
Yeah.
Yeah, I guess I'm wondering if you have looked at all into LSIF, which is the language server, I think intermediate format or whatever, but this is like a way to dump the results of LSP queries into a file that can be used without launching the server.
Yes, so yeah, I think it's great, the LSIF format, but it looks a bit dead, to be honest. And so the language support, the LSP is really popular, is really successful. The LSIF that I think SourceGraph pushed a bit, I'm not sure it's very successful right now. And so, but yeah, if I would love that LSIF gets more successful and that we could just leverage all this information. And actually, even for LSP, like for example, the OCaml LSP is great because it gives type information. But there's nowhere I think in the LSP protocol that says, is there a function that you can get to type type by overing on a specific place? For example, for Go, I would like, or for Python, I would love to query the LSP server and get the type at this location. But I don't think it's in the spec actually. So
yeah, the spec works for both typed and untyped languages. So yeah, things like this, unfortunately, are left out.
In many languages now, in Python, you have like some type checker, some type inference tool, and so in theory we could use MyPy and Sorbet for Ruby, and but it's not there yet. Hopefully in 5 years, I don't know.
All right, so Edwin has another question. Speaking of SourceGraph, can it use SemGrep's tree sitter?
Speaking of SourceGraph, can it use SemGrep's tree sitter? I'm not sure I understand
Perhaps
the question.
it would be good to clarify what SourceGraph is.
So SourceGraph is a company that pushed for LSP with Microsoft. So they pushed for this tool, command line tool that can be used by IDEs like Eclipse and VS Code, so that instead of reinventing the wheel each time, there was this language server protocol to factorize all this language aware tool.
So Edwin is here to clarify his question.
Yeah, hi. I was asking about SourceGraph's code search. So I think it needs to parse or understand OCaml in some way. So does it use its own parser, or can it be made to use SemGrep's tree sitter to parse the OCaml files?
So SourceGraph, so there's different. I'm not super familiar to SourceGraph, but there's a code search tool, but a lot of it is just regex.
Right.
Then there's a tool that was made by an OCaml programmer, Rijnar van Tonder, that is called Combi. That is a pretty cool tool, and I think SourceGraph can use Combi, and Combi itself parse the code, but it's mostly a lexer for many languages, so it's not really. It doesn't understand really the syntax. It doesn't really understand the semantic of the language. And beyond that, I'm not aware of. I think SourceGraph rely then on LSP to index the code. And so, but it's more to go to a place that go to the definition, go to the users. And so you can really, for having a code patterns, it was not really designed for that SourceGraph. It was more like for general code search.
I see. So it wouldn't really cover all the use cases that SemGrep wanted to do. Okay.
I mean, it's like grep in the cloud, to be rude.
Yeah, but I think the tree sitter
that is great.
Yeah, I think tree sitter is still nice to have. Like, I think wouldn't the latest version of NeoVim also support tree sitter in some way? So could we get like native highlighting into NeoVim via SemGrep, maybe?
I mean, tree sitter is independent of SemGrep. So yeah, for GitHub is using tree sitter internally for code highlighting. and they don't need us. What we provide then is more like, for the code search part, where then you can write simple code patterns or composition of patterns, and with meta variable and ellipsis, and then and semantic equivalence, and we'll find the code.
Okay, thank you.
You're welcome.
All right. So I guess speaking of the uses at GitHub, do you find, are there any performance I guess problems with running code searches across so many code bases? Is there any indexing that you guys do perhaps to speed that up?
Right now, no, we don't do any indexing because, I mean, first, we don't do very sophisticated static analysis. Like, we just analyze one file at a time, parse it, and then do some local semantic analysis, but we don't do anything fancy. So it's fast enough, even and on large code base. And code is small. Like, even if you're like Facebook and you have millions lines of code, all of that can still hold in memory. There's no problem, right? It's a problem of scale of Facebook. It's not about the code base so much. The size of the code is still small. I mean, it's if you don't do sophisticated interprocedural, interfile, static, context-sensitive static analysis. So we are fast enough for large code base, but yeah, and so people didn't complain yet about, oh, we need indexing, because then indexing means you need to build an index, takes time, and so we just go through. So we have some optimization to try to not analyze file that we know when the patterns contain certain strings, we analyze the pattern, and if it's not even in the file, we don't even really parse the file. So we do some simple optimization, but no indexing yet.
Yes, I remember an old search project, code search project by Google that allowed for, I guess, regular expression queries, and it did rely on indexing to have good performance. But I suppose regular expression queries are a little different from what you provide here.
Yeah, I don't know. I mean, they have huge code base over there. It's true. Yeah. In Google, and they have lots of developers.
All right. Any last questions? I suppose not. Okay, well, one thing that I guess I'm curious about is how do you handle, I guess, slightly complicated patterns, such as, let's say I want to search for field occurrences in an OCaml code base, right? I want to search for a field foo, but this access can occur, with .foo, with a projection, or it can occur with some pattern match and some pattern position. Do semgrep's meta variables allow you to write exact patterns like that?
So in your example, you can write a code pattern that will match a pattern, that will match an OCaml pattern, or a pattern that will match an expression like $x.foo. So you could write $x.foo or pipe and braces and ... and foo equal something. So you could write. You will need these two code patterns because there's multiple ways to access fields in OCaml, in expression, in a pattern. But in all the languages, sometimes we try to have some these kind of equivalences where you because sometimes it's just some features are just sugar. They are just syntactic sugar, and so sometimes we try to have the patterns to able to accommodate all, to unsugar the code and then run the pattern on the unsugared code. And so, but it's not always available. Or in this case of OCaml, we didn't see yet the need for this equivalence, but we could add it. So you could write $x.foo, and maybe we will also return matches when it's inside a field pattern or something else. But yeah, in to write a rule, you have this YAML configuration file, and so you can write a set of patterns. So in this case, you could write, I have this pattern, or this pattern, or this pattern, and not that, and then so you will encode yourself the equivalence in some sense.
I see. So there's a way to compose patterns as well with.
Yes, you can compose patterns with. First, you can have many rules, and in each rule you can have a Boolean composition of patterns. And then each code patterns can match any code. It can, so in OCaml, you can write an expression. So you can just write one, and it will find every places where you use one. I mean, it's not a very fancy pattern, but you can match OCaml pattern itself, OCaml types, OCaml expression, OCaml big function definition, model, whatever. You can write any OCaml code and put some meta variable there, some ... in some other places, and then we'll run the pattern, and then compose them together with Boolean, if you use Boolean operators, and do some set intersection and differences and so
on. Very cool.
Thanks. And so, yeah, if you have a other question, yeah, you can go on our Slack on semgrep.dev. And again, we are hiring. So if you love OCaml, please contact me.
Yeah, thank you, Johan, again.
Ciao.
Bye. Okay, I'll let Sonia finish off.
Yeah. So yeah, this has been the last session of this year's workshop. So thanks all for listening, and thanks of course also to all who have made this possible, like to Frederick Bow and the rest of the organizing committee, the program committee, the ICFP committee and volunteers, and of course the speakers. So yeah, thanks to all, and see you all next year. Bye.
Bye. Thank you.